It's 9:01. Ooh, nice. Is the audio good, or you folks can hear me echoing? Awesome. Perfect. I'm going to start shouting for people who are on the on the hallway. We're starting. Well, it is a Monday morning, so thank you all for joining us at RIPE 88 in beautiful Krakow. My name is Alex Swedish. I'm a principal networking specialist solutions architect with Amazon Web Services, AWS. I am based in San Francisco, but I'm originally from Romania. So it's great to come back to this part of Europe, which is very near and dear to me. I've been in networking for almost 13 years now, and my first encounter with IPv6 was not a fun one. But since then, I've gotten to love it. So I'm really, really excited to be here today with you folks talking about how to architect and build IPv6 networks on AWS. And I'm not sure how many of you folks are familiar with AWS or are familiar with how IPv6 works on AWS. So we're going to try to cover a lot in this 2-hour journey. So thank you for being here. Also, as an incentive, for those of you who are going to be sticking around to the end of the session, we do have a Q&A section, and we also have some very cool stickers here. Some of you who are following me on LinkedIn, perhaps you've seen them or at reInvent, so we have them for you here. Awesome. So let's get things started. And probably every single presentation about IPv6 starts with, why should we be doing IPv6? And I think all of you know why we should be doing it. However, it would be great to start with a review of why doing IPv6 on AWS, right? Well, first and foremost, IPv6 improves network scalability. And that is not only happening in the traditional data centers or on-premises networks, but also in the cloud. Second is it helps you start building experience in a really, really easy way. You can just go into an AWS account, start spinning up infrastructure, get all the advantages of the free tier layers of AWS services, and build that experience. See how IPv6 works. See how you can configure IPv6 addresses on different resources and different compute types. Then this goes farther away as we talk about the whys and as we sort of delve into the paradigm of IPv4. And minimizing NAT, network address translation, both public and private, is a very good reason to start looking at IPv6. AWS does provide a fully managed NAT service. It's called the AWS NAT Gateway. It does both private NAT, NAT 4.4, and public NAT 4.4, and minimizing the use of that by adopting IPv6 is a really, really good cost incentive. And last but not least, simplify global connectivity. Whenever we're thinking about the cloud and whenever we're talking about AWS, we're focusing a lot on the fact that we have presence globally, right? There's every day when I go and look at the list of regions that we have available, I'll probably get that number wrong. I think now it's like 24, 25, 27, something like that. So global connectivity needs to be simpler than what we can achieve with, for example, an IPv4 addressing plan that is made out of scraps left from what we have deployed on premises. And getting this routing simplicity in AWS is really, really important for scaling, back to the first point. Now, if we go even deeper into each of these, there are very good reasons to start with IPv6 on AWS today. And partially because of that experience, of that easy to deploy, easy to test, right? You don't need special equipment. You don't need to change your entire on-premises network to get IPv6 running, right? Um, the other part of it is we have been in this world where dual stack is the norm. And on AWS, it's really easy to also start testing what IPv6 only means for your applications and services, right? The fact that we natively provide IPv6 only subnets in the Amazon virtual private cloud, and we're going to get to that in a second, is a really important tool that helps you test and see how your application behaves, right, in an IPv6 only environment. Now, we've learned the whys, right? Let's look at how the approaches to adopt IPv6 on AWS look like. And we have two. We've defined them in really, really simple way. Outside in, so edge first, or inside out, internal network first. However, these two adoption approaches are not disjointed. They're actually complementary, right? And you can start at the edge and say, well, I am going to work my way all the way into the internal network, right? So I'm going to start with edge services on Amazon like CloudFront, which is our content delivery network service, AWS Global Accelerator, Elastic Load Balancing, and so on. The services that allow you to expose your applications to your internet users. And you work your way backwards into the internal network by enabling IPv6 on Amazon services in the Amazon VPC and in your internal routing network all the way to on-premises. So this is one way to start. And it's a way to start that gives you the flexibility of maintaining your internal network IPv4, right? Just adding IPv6 at the edge where it brings that value to customers, right? To your end clients. So why outside in? It gives you the IPv6 enabled end client experience, right? So clients don't need to go through CGNAT on the internet, right? They natively access your applications, deploy it on AWS using IPv6. Then you get an expanded user base in geographies with high IPv6 adoption, right? For the end clients. And you contribute essentially to the IPv6 adoption rate globally, right? Because you make your applications exposed externally on IPv6. Also, Hapnik does publish some cool stats around the performance of IPv6. I do highly recommend you check them out. Sometime in May 2020, the round trip time difference between IPv4 and IPv6 became negative. So it's a really cool stat to see. We do have also customers who've publicly shared their IPv6 adoption experience, and for the outside in, highly recommend you folks read their own home story on our AWS website. Now, inside out, the other approach, it's essentially saying, oh, sorry, pressed too fast. Come on, get back. Thank you. It's just, the inside in is essentially saying, okay, maybe I'm not ready to expose my services publicly on IPv6, but I want to start testing my internal applications deployed on AWS, and I want to see how they behave in either a dual stack or an IPv6 only environment. I want to see how I start building backwards compatibility with IPv4, right? Because there's not a magic button that we can click and all our environments are all of a sudden supporting IPv6, right? So the inside out starts with the Amazon VPC with connectivity, and we do have a lot of customers who've actually turned on IPv6 on their networks. However, no application actually supports IPv6 yet. And the network teams started building that network to be ready, right, for IPv6 and to be ready for application teams to now start prioritizing building IPv6 support. Then it continues with VPC services, what you can deploy in your virtual private cloud in AWS, and ends with the edge. However, I mentioned that these two approaches are complementary, and we're going to see in a second why. What does the inside out first give you? Well, first and foremost, we talked about the whys there and why do IPv6. Scale is one of the big reasons, and not scale just because you are a very big enterprise. But this scale, the term scale, has actually evolved a lot with container deployments. Containers use a lot of IP addresses, a lot of IPv4 addresses, right? And even enterprises that used to say, well, IPv4, private IPv4 exhaustion is actually not a problem for me. I've done my addressing plan really well. With the adoption of containers at scale, they do see their container platform teams coming to them and saying, well, I need, I don't know, 5/16s for tomorrow. And they are like, wait, what? 5/16s? I don't have that much IP space to give you. Or if I give you today 5/16s and then you're coming tomorrow and ask me again for 5/16s, how do I scale this, right? So the scalability problem is more acute with container deployments. Right? So scaling container deployments and platform deployments, unlocking scale for global network connectivity, as we've talked about, accelerate integration of mergers and acquisitions. This is one of my favorites. I do work with a lot of our AWS customers, and most of them are going through constantly this process of mergers and acquisitions. And it's always a matter or a question of we're using 10/8 and they're using 10/8 as well. How are we going to connect them? And then there comes this place of let's re-IP or let's do private NAT between everything, which is really, really complex and costly. So IPv6 makes that easy. Also, the inside out gives you the ability to build that familiarity with IPv6 without impacting your public facing applications, your end clients, in case your application has some issues with IPv6 and it's not supporting it. Netflix is one of our customers who has publicly shared their story around adopting IPv6 for their container deployments. So highly recommend you folks read more about it. They do also have a few reInvent sessions on this. reInvent is our the AWS conference, so highly recommend you you watch those too. Also, we've been on Twitch. We also have a show every Thursday. We talk all things networking on AWS, and they've been on the show, and that session is named "You Don't Have to Be Netflix to Do IPv6." So really, you don't have to. Highly recommend you read more customer stories and you watch more of our Twitch videos. We always try to bring more customers in to share their experience with IPv6. Last year, we've done the AWS IPv6 Day on June 8th. This year, we're preparing for the same, so stay tuned. We'll share some good news on LinkedIn shortly. And a key takeaway from this part of like, how do I get started with the adoption approach is that there's not one way door decision. You don't have to say, oh, I'm going outside in and that's it, or I'm going inside out and that's it. These two approaches are complementary. And we do have guides and steps for you to take to make sure you don't break your deployments, right? And you can easily work with both approaches, depending which one is the one best for you. Now, we've talked about approaches, right? We talked about inside out, outside in. However, there's usually this question of, well, IPv6 is this big topic. Like, where should I be focusing on, right? How do I start even thinking about it on AWS? And we've devised IPv6 adoption into 4 focus areas. So the network layer, the operating system layer, the application code, and services and tools. And this framework for thinking about adoption and for sort of dividing the work, the interaction with teams that it involves, actually creates simplicity, right? And it makes IPv6 not be this big mountain in front of us that we don't know where to approach from, right? So at the network level, the assessment goes into what are the networking and content delivery services that I use? What are the appliances that I'm using on AWS, right? Like virtual appliances. What do I need to do to ensure that I have IPv6 routing in place, right? Then operating system. If you're using modern operating system distributions that are probably not built 10 years ago, you do already have IPv6 support. The Amazon Linux, for example, has that enabled by default, so you don't have to do anything to change it. Right? Then app code. This is probably one of the biggest fears of anyone starting with IPv6, which is, I don't know how my application is going to break. I don't know if it's going to break. The short answer to that is that if you don't start and if you don't put it to test, you're never going to know, right? You're never going to know if your application that was written, I don't know, maybe 10 or 15 years ago, actually has some hard-coded IPv4 addresses into it. Or if it reads the client IPv4 address and the actual memory variable is for a 32-bit number versus a 128-bit number. So until you test it, you won't know. The more important thing, though, is that as customers adopt AWS and move to AWS and modernize their applications, and app modernization is essentially going back and saying, okay, how is this application, this monolith, how is it going to be broken down into microservices? How am I going to be using AWS compute services like Lambda and containers? And how am I going to modernize this application? So as customers go through this process, getting IPv6 adoption becomes easier because they are already scrutinizing the application code. They're already saying, well, how am I going to transform this application and modernize it? So IPv6 becomes part of that modernization process. Right? And services and tools. This is a place where on AWS, not all the AWS services today support IPv6. It's our goal. We're getting there. But it's very important for every one of our customers to work backwards from their needs. And we work backwards from their needs as well. So whenever you're assessing the services and tools that you use, starting from what you use for security and logging and management of your instances or your services, and working backwards from their support for IPv6 and for what you need to do to implement that backwards compatibility, right, gives you a really clear view of what's supported today, where we're getting with the roadmap, and what's going to be supported in 6 months, in 12 months. And it gives us also the ability to work backwards better from you, right? And say, cool, these services, we need to prioritize them, right? Because they're needed for these types of use cases that we want to enable. So we know what to focus on. Then where do we get started from? The first and most important thing, because we're talking about IP addresses, right, is addressing plan. So there's two very, very important pieces of starting on AWS. The first is creating an addressing plan. And the second is the dual stack Amazon Virtual Private Cloud. Now, these two work together really, really closely because the capabilities of one determines how you're going to design the other, right? And vice versa. So let's see how we get started with IP addressing on AWS. The first and easiest one, all of you can go into your AWS account today and try it out, is the Amazon provided global unicast addresses at the VPC level, right? So when you have your VPC on AWS, you get from Amazon pool of IPv6 addresses um, the GUA IP space. Now, um, the default IPv6 prefix size is a /56 for the VPC. You do have to have an IPv4 address associated with the VPC. So the Amazon VPC is a dual stack construct. The reason for that, and we're going to dive a bit deeper into it, is because partially the way in which you create that backwards compatibility is by leveraging those IPv4 addresses, right? And you can choose which services and for which use cases you deploy IPv6 only. Now, you can start by creating an Amazon VPC with an AWS allocated IPv6 GUA space. You can also later on edit your Amazon VPC and add IPv6 support to it. And you have a couple of options there. We're going to go through all of them, but the ones that are allocated by AWS are the Amazon provided IPv6 CIDR blocks. And yes, we know that in IPv6, we don't call them CIDRs, we call them prefixes. But for the matching the IPv4 experience to the IPv6 experience and making it easy for customers to start with IPv6, we've kept the naming convention. So this is how your CIDRs on the VPC look like. Very, very easy to get started with. And they're also free of charge. So you don't have to pay anything for them. Now, in your VPC, you will have subnets. And out of these CIDRs that you associate with your VPC, you're going to create further down. You're going to subnet those CIDRs and create the subnet prefixes. By default, the subnet CIDRs are /64. And it is recommended to assess really well if you need different sizes for your subnets. We do have customers who are saying, well, I do need different sizes for the subnets, and we're going to get to that in a second. And these are the use cases for which I need them, and they make total sense. However, there's a very, very important thing here to consider. IPv6 gets us to the place of not thinking about the number of hosts that we're going to have in a subnet. Like the VLSM mindset, right, is not there anymore. So it's more important to have a scalable addressing plan, right, an extensible addressing plan, rather than subnets that are, I don't know, /96, because I'm not going to have that many resources in that subnet, right? So /64 does match the RFC, and it is having the host ID 64 bits, so it does comply with the standards, and it's highly advisable that you use it as such. However, we do have also the tiered sizes for both the VPC and the subnets. So you can create larger than 64 subnets. You can't create smaller than 64 though. Now, there's a caveat to it. You can get started with Amazon provided IPv6 CIDRs, but they are randomly assigned by default. So this gets us to the place where we start considering a very important aspect of IPv6, which is that scalability of the addressing plan and extensibility, and how do we make it easily summarizable, right? So here comes the second way to start with IPv6. So let's say you started with the first one and you created your VPC, you tested, you played around, and now you're trying to get to the place where you have actually an extensible addressing plan. You can get from Amazon. Amazon provided contiguous IPv6 blocks. These blocks are assigned using the Amazon VPC IP address manager, and you create within IPAM a public scope. So you have there by default a private scope and a public scope, and in the public scope, um, you can create a pool, and out of that pool, a regional pool that has an Amazon provided IPv6 space. And it's a block that you can then take and use for your VPCs. So for addressing a larger number of VPCs. What this gives you is a very powerful tool to enable you to summarize. So if you have just a few VPCs, you can totally go by the randomly assigned ones because summarization perhaps is not a big consideration. However, with the contiguous blocks, you can think strategically, right? And you can say, okay, I'm going to design this the scalable addressing plan. Now, IPAM has two tiers. It has the advanced tier, which is a paid tier, and it has the free tier. Contiguous CIDR blocks are supported in both. So you can get started with contiguous IP space on AWS, Amazon provided, also in the free tier. Right? The difference between the free tier and the advanced tier is that the free tier is a per account per region level. So if in AWS you have multiple accounts and you wish to create a summarizable addressing block or plan for multiple accounts across multiple regions, you will need the advanced tier. However, there's no cost associated with the blocks themselves. IPAM is the one that has the free tier and advanced tier. Now, there are customers who are great with these two first options. However, there are also customers that for various reasons and various use cases require bring your own IP, right? So they do have their own IP blocks. In IPv6, reputation is something that's also important, same as it's in IPv4. So for these business use cases and reasons, bring your own IPv6 is also supported on AWS. So if you wish to get started with your own IP block, you can absolutely do so. So again, in Amazon, you can use bring your own IPv6 into flavors. You either bring it directly in Amazon EC2 and you create account level and region level pools, or you bring it into IPAM. And if you bring it into IPAM, again, you get that benefit of multi-region, multi-account scalability, right? Now, a very important piece or a very important question that rises immediately when we talk about bring your own IPv6 is the control that you get on those prefixes, right? And that is the most important piece that comes to meet those use cases, where customers are saying, I don't want part of this IP space that I've brought to AWS to be advertised on the internet. I want to keep it private and not advertised, right? Or I want to have full control over when I advertise and when I withdraw these prefixes, right? So that said, you get that with Bring Your Own IPv6 on AWS, both in EC2 and in IPAM, right? And last but not least, the size of the blocks are important. There are some restrictions of what sizes you can advertise on the internet. So /48 is still there because that is what we can also advertise on the internet. If you bring non-advertisable CIDRs, you can have those smaller blocks. Now, very important. I've had quite a lot of conversations with customers on this journey, at different stages of this journey. And I think probably the most important thing is until you get to create that experience and say, well, I know what I'm going to be keeping unadvertised, and I know what I'm not going to be keeping unadvertised, and I'm going to advertise, and I'm going to create public subnets out of those CIDRs and have internet-facing workloads. Having the flexibility of advertising or withdrawing the prefixes based on your need is important. So starting with perhaps a /48 per region might seem a lot, right, for your needs. But if you're starting on the path of doing bring your own IP and you want to get that flexibility of saying, I'm not really sure how my workload deployments are going to look like for now. I don't know exactly what's going to be advertised and unadvertised. You can start with that /48. You can start with it advertised and later on unadvertise it and vice versa, right? So you have full flexibility there. Now, let's see an example. So we have, for example, a top level pool in IPAM in the public scope. And from this top level pool, we can create regional pools from which VPCs are going to be advertised, right, or and addressed. We've kept the convention of /48 because we do want to have full control over withdrawing or advertising the prefixes. And from these /48 CIDRs, we allocate IP addresses to VPCs. In summary, we've talked a lot about IP addresses and where to get started. There's various options. There's also various considerations, right? There's a consideration of where do you want those VPCs to have internet access from? Do you want to give them internet access on AWS or do you want to give them internet access on-prem? Do you want to have the prefixes advertised or not, right? Very important there. There's a column that says NAT66 or MPTV6. We're just saying that if you're getting into IPv6, you should not need NAT anymore. However, we do have customers and we do have use cases for which customers require still NAT66, right? So it's not required, but you could implement it if you wish to do so. Also, the status of the prefixes being advertised or not being advertised is again really important, right? And we've talked about it. You do have control over bring your own IPv6. You don't have control over the Amazon assigned ones, right? Because they're part of the Amazon pools and they are advertised. Still with me on the journey? Cool, awesome. So we talked about where to get started, right? We've seen the addressing best practices, the addressing options. We've seen the drivers. We've seen the approaches outside in, inside out. Well, now we get to the most important part, right? Which is your foundational network boundary on AWS, which is the Amazon VPC, right? There's a lot of things that you can do without VPCs. There's more things. There's a lot of things that you can do if you use the Amazon VPC on AWS. So how does the Amazon VPC look like? First and foremost, we have an IPv4 only VPC here, and to dual stack it, right, we do add an IPv6 CIDR block to it. You can have up to 5 by default /56 CIDRs associated with the VPC. Associating a CIDR to the VPC does not mean that your subnets are going to become dual stack. You do have to do that, right? That's a step that you take because you have the choice to say, I want to dual stack this subnet and I want to keep this other subnet IPv4 only, right? Now, the next piece is VPC routing, right? So how does routing happen in the Amazon VPC? All subnets in a VPC can talk to each other by default. You can restrict subnet to subnet configuration or communication using network access control lists, and we're going to talk about them in a second. However, by default, the Amazon VPC has a default route table, a lot of defaults there. When you add an IPv6 CIDR to the VPC, that IPv6 CIDR automatically shows up in the default route table and in all the other route tables that you've created in the VPC. So that means that communication between subnets that have IPv6 CIDRs associated with them, either dual stack or IPv6 only subnets, will be able to talk to each other. So this is something that happens automatically. That local route shows up in all your route tables, the default one and all the custom one that you've created, and you can't remove it. So everyone can talk to everyone by default. Now, we get to the interesting part, DNS. It's not enough to have routing, right? It's not enough to have reachability. We also have to have the ability of resolving DNS names. And in Amazon, we have the VPC Route 53 resolver. Amazon Route 53 is the Amazon fully managed DNS service. And in each of the VPCs, right next to every single one of your workload in the VPC, actually, you have the resolver service. That's a recursive DNS resolver, right? And it essentially deals with resolving all your DNS queries from the VPC by default. And this resolver also supports IPv6 as well as IPv4. It has a really well-known address, making use of EC2. Now, this resolver can natively respond to queries for your workloads in the VPC, both in IPv4 and in IPv6. And subnet types. You can have in the same VPC coexisting all the three subnet types. You can have IPv4 only subnets, you can have dual stack subnets, and you can have IPv6 only subnets. Now, why is this important? For a very, very simple reason, which is flexibility, right? You get the flexibility to implement IPv6 wherever you want in your subnets, right? You don't have to say, oh, I've put IPv6 on this VPC, everything in it all of a sudden has IPv6, right? Also, when you go back and you create, for example, or you retrofit existing subnets to be dual stack, you will see that by default, you have a tick box on our subnet setting that says automatically allocate IPv6 addresses to resources spun up in these subnets. That tick box is not ticked by default because you get the opportunity and the flexibility of saying, well, I want to enable automatic IPv6 assignment in some subnets. And in some subnets, I want to have the full control over which resources actually have IPv6 addresses, right? Awesome. Now, we have the VPC. What's next? We have our network. The first thing is creating the network. The next thing is bringing in compute, right? Let's review IPv6 support for some of the AWS or Amazon compute services. Not all of them, there are much more. You can check all of them at the link at the bottom of the slide, but these are some of the most common ones. And you can look at them as being foundational for a lot of use cases on AWS. So let's start with Amazon EC2. We've narrowed down the diagrams to just one availability zone, but keep in mind that each AWS region has multiple availability zones. So for you to create highly available workloads, the recommendation is to architect using multiple availability zones in a region. Subnets in AWS in the Amazon VPC are bound to availability zones. So when you create a subnet, you have to say, I want to create a subnet in AZ1 or AZ2 or AZ3. So even though the diagram just shows one AZ, you do, it is recommended to use multiple availability zones. So Amazon EC2, it's the foundational compute service on AWS, and it supports all three flavors of deployment: v4 only, dual stack, and IPv6 only, right? So you have the construct on AWS of an elastic network interface. The elastic network interface is associated with EC2 instances, support all three configuration modes. Now, we have recently launched for Nitro-based instances. Nitro is our own hypervisor built and optimized for AWS. The configurable DHCP v6 lease times. The reason for that is because we do have a default, and by default, at half of that default, the renewal happens. We do also have customers who require longer lease times. And there's various use cases in telco, for example, for that. So we do have a configurable lease time that we just released. Amazon Elastic Kubernetes Service. It's the Amazon fully managed container service. It does make use of a control plane that's fully managed by AWS and the data plane that is based on Amazon EC2 and what we call worker nodes. These worker nodes in Amazon EC2 or EKS actually supports IPv6 in dual stack mode with IPv6 only pods. So very, very important. When you deploy an EKS cluster, you do have to deploy it in dual stack subnets. So your workers are going to be dual stack. However, every single worker node gets a /80 prefix that is delegated to it, right, or assigned. And it is going to use this prefix to allocate IP addresses to containers or pods that are spun up on it. Some very important reasons why we did this. One, scalability. Two, the /80 there actually helps optimize the number of API calls that you have to do as part of a cluster when pods come up and down. You don't actually have to update the cluster IPAM every single time because that /80 is already assigned to an elastic network interface. So when pods come up and down, the cluster already knows that it can reach them using the ENI of the worker node. So it helps you optimize that number of API calls. Also, very important, two things. The worker nodes provide native NAT6.4 and NAT4.6 capabilities. So you don't need, for backwards compatibility, right? Your pods are v6 only. So all of a sudden there's this question of, oh, how am I going to talk to my v4 world, right? Or how is my v4 world going to talk back to the containers, right? So the worker node, because it's a dual stack, right? It has that native capability of providing NAT6.4 and NAT4.6. So every time the pod, for example, needs to talk to an IPv4 destination, there's going to be a NAT6.4 happening, and that destination will see the IP address of the actual worker node ENI, right? Not the IPv6 address of the pod. Also, very important, the ingress load balancer controller, so the one that deploys for you application or network load balancers, depending on your use case, natively supports dual stack at the front end, right? For backwards compatibility, exactly for your v4 and v6 clients, and supports the v6 native integration of those v6 targets, right? Which are the pods that define your service, right? Amazon Elastic Container Service. Now, there's a bunch of customers who are saying, okay, cool, we want to manage our own EKS clusters. We build platforms on on Kubernetes, so that's our path. There's also container service where you get containers as a service, right? You don't have to deal with managing the cluster and everything that EKS in itself means. In ECS, we do have the construct of a task, and tasks are supported to be dual stack, both in AWS VPC mode for both EC2, where the tasks are in EC2 mode, or in Fargate, which is a fully managed mode. Now, these are very detailed aspects of how these compute services work. The important key takeaway here is that they do support IPv6, right? Also, AWS Lambda, right? The serverless, fully managed service that allows you to create functions that meet a certain goal. They also support IPv6 both when you deploy them in the VPC, so for egress purposes, and the AWS Lambda endpoint for ingress, right, does have the dual stack capability. So for both types of use cases, the IPv6 is supported. Now, Lightsail. This is one of my favorite services. The reason for it is because it makes it really, really easy to deploy on AWS, right? It provides you with bundles that you can deploy, and you get all the features that you need as part of that bundle, right? And it does natively support IPv6, and you have the full capability of choosing if you want dual stack or IPv6 only, depending on your capabilities, depending on your where you are on this adoption journey on IPv6. Now, how do we build that backwards compatibility for IPv6 only workloads that we deploy on AWS, and they do need to talk to the outside world? So we've built the VPC, we've built compute, and we're saying in compute, okay, I want to take advantage of the scale, and I want to also be able to not break my communication, right? And not break my services. So Amazon provides native backwards compatibility in the Amazon VPC using two core functions, NAT64 and DNS64. Let's see how that works. Let's say we have an IPv6 only workload, right? An EC2 instance. And this EC2 instance wants to talk to something that's v4 only, right? It does a DNS query. It asks the Route 53 resolver in the VPC about that domain. The resolver is a recursive resolver, right? So it's going to try to recurse through it, and it's going to receive an IPv4 address. If it would send back this IPv4 address to the host, that host is not going to even know what to do with it, right? So it doesn't do that. Here's where DNS64 comes into play. DNS64 is a subnet level setting for IPv6 only subnets on AWS. So when you create IPv6 only subnets, you go on the subnet, you edit subnet settings, and you enable DNS64. What this does automatically, like magic under the hood, is to essentially allow this host to query for whatever IPv4 destination, right? The recursive lookup happens, but the IPv4 address that is received by the resolver is not sent as such, right? Because there's no way the host would understand it. So the answer is actually made out of the well-known prefix 64FF9B::/96, and the v4 address, of course, translated into hexadecimal. I've put it here still into decimal because of us seeing it exactly that it's the same address. So that IPv6 address is sent back to the IPv6 only host. And that's an address that the host can actually understand, right? So now the host will use that address, right? And we'll try to actually talk to the destination. But the destination is a v4 only destination that only knows that it has the IP address 1234, right? So if we send IPv6 traffic to it, it's going to say, oh, I don't know exactly what to do with this traffic. So we have natively created on all existing and new NAT gateways in AWS the NAT64 capability. Very interesting here is that that NAT gateway is a v4 only NAT gateway, right? You don't have to, there's no construct of dual stack NAT gateway, right? NAT gateway is a specific construct for NAT44, right? But if we configure routing appropriately and we say that well-known prefix from the IPv6 only subnet, right, has to be routed to the NAT gateway, then traffic can go to the NAT gateway and through magic, NAT gateway takes that traffic and NATs it to a v4 native traffic. So it does both source and destination NAT, right? And as such, the IPv6 only instance can talk to any IPv4 destination. And when I say any IPv4 destination, I'm also talking about any IPv4 destination in the same VPC, for example, because you may be at a stage in your IPv6 adoption where you don't have all your workloads in the VPC supporting IPv6, right? Did I just say IPv4 adoption journey? IPv6 adoption journey. Cool. So native IPv6 to v4 backwards compatibility. Now, let's get to connectivity. We've deployed our workloads, we've deployed our VPCs, and probably the first thing that a customer is asking on AWS after they've done this is, how do I connect this VPC? By default, the VPC is a closed boundary around your workloads, right? In order for that VPC to get connectivity to anything outside of the VPC, right, you have to, right, configure it explicitly to say, I want connectivity to other VPCs or I want connectivity to the internet. It's not there by default because it provides you with security by default and it's an enclosed space. So let's see how we connect our VPCs, right? And first and foremost, what everyone does, including myself, every time that I spin up a new VPC, I put an EC2 instance, I give it an IP address, and I'm trying to SSH into it, right? So unless I use more advanced services like Session Manager or Systems Manager, I would probably go about putting an internet gateway associated to my VPC and giving my instance a public IPv4 address. The time for that is over. We can use v6 addresses now, right? So let's see how we get internet connectivity for the Amazon VPC. And we're starting here with the dual stack VPC with an IPv4 and a dual stack subnet. And in AWS, we have the construct of public subnets and private subnets. The difference between these two are made not by the name, like when you create a subnet, the subnet just has an ID and a CIDR or a set of CIDRs blocks associated to it, one in v4, one in v6. And what makes a subnet public is the routes in the route table to which it is associated, right? So we have for now the public subnets route table that is only the default, right? So it just has the local routes for the v4 and the v6 CIDRs. And we have some destinations on the internet with various capabilities, right? We have a v4 only, dual stack, and v6 only. So how do we get communication or connectivity to and from those hosts or services? Well, first, there's the Internet Gateway construct on AWS. The Internet Gateway is, as its name stands, right, a gateway that takes this VPC and connects it to the internet. However, by simply attaching the internet gateway to the VPC, it doesn't mean that we yet have internet connectivity. We do have to go through some configuration steps, right? So you fully control what in your VPC actually gets internet connectivity. And the first step to that is associating public IPv4 addresses, right, for v4 connectivity to your public resources. And here we see that we have an elastic IP associated with the 10.0.0.4 IP address of the first host in the IPv4 only subnet. So the right route configuration in the route table is what gives this host reachability, right? However, there are two constructs that we haven't talked about yet, but we will, which are network access control lists and security groups, and additional security that you configure in the VPC that will dictate if that host actually gets internet connectivity. So reachability is not the same thing with actually having connectivity, right? Now, how the traffic flows. The internet gateway is essentially doing one-to-one NAT between the private IPv4 and the elastic IP address that's associated with a resource. So it provides bidirectional connectivity, right, to and from resources with public IP addresses in the VPC. So pretty straightforward, right? There's no lines to the v6 addresses because our resource is v4 only, so it doesn't support. But we also have a dual stack resource, right? And in v4, we can associate an elastic IP address to it. And in v6, we don't need that, right? In v6, we have the native IPv6 GUI address that has connectivity to the internet. It's advertised, right? Remember that if you have your own, bring your own IP space, right? That bring your own IP space, if you don't advertise it, the internet gateway won't know about it, right? So if it's not advertised, it's fully private in the VPC. You won't get internet connectivity to and from it. So this is how the public subnet route table looks like. In IPv4, there's a default route to the internet gateway. In IPv6, there's a default route to the internet gateway. So the internet gateway is a construct that supports both IPv4 and IPv6 natively. Now, we have that IPv6 only subnet, right? And we can have public IPv6 only subnets. The same principle applies. The default route has to be in the route table to the internet gateway. And the resource will be able to natively talk to v6 capable endpoints in the internet. Both initiate connections and receive connections as long as security allows it, right? But what happens with that backwards compatibility? Well, we've just learned about NAT 6.4, right, and DNS 6.4. So we enable DNS 6.4 on the subnet, and we get that backwards compatibility with v4 resources. Now, you see that the arrows here are unidirectional, right? So we can open connections to those v4 only resources and we can receive the answer. The question that usually comes is, well, I want to SSH into my instance, right? And I'm v4 and my instance is v6 only. So how do I do that? The answer is very simple. You can use Systems Manager with an endpoint in the VPC, and through that NAT gateway that does natively NAT 6.4, you're going to get access to your instances, even v6 only, in the VPC using a fully managed service. And you don't need to actually manage SSH keys, which is even better. Now, I mentioned that there's two types of subnets in the VPC. There's the public subnets, which through their name, they're public, right? They have resources that should be publicly accessible, right? Maybe not those EC2 instances that we've seen, but maybe load balancers, to scale application delivery, and we're going to get to that in a second. Then we also have private subnets. Private subnets are usually hosting either app servers, databases, whatever other resources you deploy in the VPC that don't need to be directly accessible from the internet. In IPv6, though, there's the question. These are GUI IP addresses, right? They're on the internet route table. How do I make my subnets private? Well, we said that the internet gateway allows bidirectional connectivity to and from the internet. Well, in IPv4, we had that security construct that a lot of people like to call it security, which was NAT, right? It's not really. I truly believe that it's not. And if NAT is the only security construct that you rely on, you should absolutely consider not relying just on NAT. But the security posture still applies, right? Even if we don't have NAT in IPv6. And the security posture says, I want to have resources that are not directly accessible from the internet, right? I don't want to allow inbound internet connectivity to them. So we've created the egress-only internet gateway, which, as its name stands, right, it allows egress traffic, right, to go to the internet. In v4, we use the public NAT gateway. The NAT gateway translates our traffic, goes to these public resources. But in v6, there's no NAT, no need for NAT, right? So we can use the egress-only internet gateway as a next hop in our route table, right? And the same security posture is maintained, right? v6 addressed resources in the VPC can open connections to v6 endpoints in the internet and can receive the response traffic back. And not just in the internet. A very common use case for this is, for example, when customers need to access AWS managed services that support IPv6 from private subnets without the need to go through NAT across regions. We're going to get to private link in a second, but the keyword there is across regions. So this is how our egress traffic looks for private v6 resources. We also have those v6 only subnets, right? Same thing applies. Default route to the internet, to the egress only internet gateway. So traffic natively goes to the v6 resources on the internet, and the well-known prefix, as long as it's routed to the NAT gateway that we already have in the VPC, right? It is NATed natively and provides that backwards compatibility to v4 endpoints. Cool. We've done internet connectivity. We're good connecting to our resources, connecting from our resources, even SSHing into our resources. Now, the next question is, I've connected my VPC to the internet. I'm now creating more VPCs, and I want to connect between VPCs, right? I have a bunch of workloads, and I need connectivity between them. This is seen and understood as private connectivity, right? And you'll see that it's private connectivity even though we use GUA IPv6 addresses, right? So there's multiple ways of achieving private connectivity on AWS, and the key difference between them is scale and the scale at which we can use it. The first one is VPC peering. A peering connection is a connection that is established between two VPCs, is a non-transitive connection. So if you have more than two VPCs and you want all of them to connect to each other, you have to peer all of them to one another, right? So back to the scaling piece, that's important, right? If we have n VPCs, we will have n times n minus 1 over 2 number of peering connections that we need. However, it does support natively IPv6, right? So when we peer two VPCs together and we update the route tables of the VPCs, we can natively communicate between resources in these two VPCs on IPv6. There's a very important consideration there. When we peer VPCs together, the IPv4 and IPv6 space cannot overlap. Well, in IPv6, it's easy. It's GUA, so it's never going to overlap, right? But in IPv4, there's a very big chance for that to actually happen. So we'll see additional connectivity methods that allow us to route only IPv6 over that connectivity option and keep v4 local to the VPC. And the first one of those is the AWS Transit Gateway. Transit Gateway is a regional hub, regional routing hub. It's again a gateway, different from Internet Gateway, different from egress-only Internet Gateway. Those you still have them attached to your VPC for internet connectivity. And it brings the construct of attachment. So Transit Gateway attaches to your VPCs in the region, up to 5,000 of them in a region, also across accounts. So a multi-account, multi-VPC strategy allows you to scale horizontally on AWS. And again, I didn't depict it here on the diagram, but multi-AZ is again key for high availability and resilience. So when you create an attachment of a VPC to a transit gateway, you can specify multiple availability zones, right, where you have your workloads deployed. And the transit gateway natively supports dual stack routing as well, right? So it can route your IPv6 prefixes. As long as the attachment subnets in your VPCs are dual stack. So the fact that the attachment subnets are dual stack, it means that the elastic network interfaces that the transit gateway uses in the VPC are also dual stack. So the transit gateway becomes a dual stack regional routing hub, right? From route tables perspective, here is the first moment when we realize how important summarization is. So we know that in v4 we have those three cool routes of saying 10/8, 172.16/12, and 192.168/16, and that means private connectivity, right? Our private IPv4 addresses, and it's really easy to route them to a central routing hub. Cool. Well, in v6, we don't have those. So if you have, for example, hundreds of VPCs, or even not even hundreds, but tens of VPCs, if you would address them randomly, right, and then you would try to connect them through a regional routing hub like Transit Gateway, you would have to add to the route tables every single CIDR of every single VPC, right, that is connected to that Transit Gateway. So summarization is important, is really, really important when we start talking about scale. So addressing your VPCs in a region, for example, using a summary prefix, right, allows you to get that summary route in IPv6 pointing to the transit gateway, and meaning that every single VPC that has it will say, okay, cool, I'm going to send this traffic to the transit gateway, and transit gateway is going to be the one that is going to handle the route scale, right? Transit gateway route tables scale orders of magnitude higher than the route tables of VPCs. VPCs are not routers in themselves, right? So for that scale, the transit gateway will know for every attachment the IPv4 and the IPv6 address of or prefixes of those VPCs that are attached to it, right? So we get that scale. Another very important thing, let's say you already have your transit gateway in your deployment and it's a v4 attachment. You can easily go and enable v6 on existing attachments. There's no impact to existing IPv4 traffic. So you can easily go and dual stack your attachment subnets and then modify the attachment and say, I'm going to enable it for v6. And that's when your transit gateway attachment becomes dual stack, and the transit gateway learns the IPv6 CIDRs in your VPC. Now, transit gateway mentioned that it's a regional routing hub, right? So it centralizes your connectivity in an AWS region. But we did talk at the beginning, one of those primary reasons why IPv6, right, is because we do have global networks. And we do have global use cases, right? We do want to reach our clients globally. So scaling on AWS across multiple regions is a norm, right? It's really, really common. So you could, for example, go and deploy Transit Gateway in every single one of your regions and configure it to connect to all the other regions by peering those Transit Gateways together. However, that would be your do-it-yourself type of implementation, right? So we've made it easy by creating a fully managed global connectivity service, which is called AWS Cloud WAN. So Cloud WAN, essentially under the hood, is still transit gateways with more added features and functionality, right, that automatically and fully managedly connect to each other across regions. And what you as a user experience is the capability of defining end-to-end segments, right, across all the regions where you have Cloud WAN deployed, and get this global connectivity configured. So Cloud WAN is a fully managed service. When you deploy it, you just specify which regions you want it to be in and what your segments are, right? And it, again, the same as Transit Gateway, supports both IPv4 and IPv6. So you can have a mix of VPCs, a mix of attachments. We're going to see that not just VPCs can be attached to both Transit Gateway and Cloud WAN. We have multiple types of attachments. And you can have a mix of v4 only, v6, dual stack, and very importantly, you don't have to be fully dual stack, right? You will be on a journey, and both Transit Gateway and Cloud WAN and VPC peering support you through that journey, right? Because they natively provide both types of functionalities. Now, hybrid connectivity. We've connected our VPCs natively on AWS, and then there comes that use case of how do I get things back to on-prem, right? Or how do I get on-prem to the cloud? How do I accelerate migration? Get to that. So that's what we call hybrid connectivity. And there's a couple of ways of achieving it. The first one is using AWS Direct Connect. Direct Connect is a service that provides you with dedicated connectivity, physical connectivity, in the form of Direct Connect connections. And these Direct Connect connections being the physical piece, right? You do have to have a logical layer to them. That logical layer is called virtual interfaces. And you have multiple types of virtual interfaces. Now, what we see here is two of them. We have three in total. The first one is the public virtual interface. A public virtual interface is essentially a BGP peer that can be established on both IPv4 and IPv6, right? Through which you exchange public prefixes on both IPv4 and IPv6. So when you establish that peering, you essentially receive all the IPv4 and IPv6 addresses or prefixes on AWS. You also have filters that you can apply if you don't want to receive all of those. You have BGP communities, right, to filter on. And you also advertise your own public prefixes to AWS. That all is routed on that native connectivity that you receive, and that is also dedicated. And you can have sub 1 gigabit per second speed. You can have 1 gig, 10 gig, 100 gigabits per second with native support for MACsec encryption. So when you create this virtual interface, the virtual interface rides on top of the physical layer, right, which is the direct connect connection. So public virtual interface, public prefixes exchanged with AWS, supports both v4 and v6. What you send and what you receive on each of the address family peers is those types of addresses. The private virtual interface. Not everything on AWS is public, right? We do have the VPCs. We've talked about them and to them so far. So how do we get connectivity to what's inside of those VPCs, right? Without having to expose them actually to the internet, right? Without having to have an internet gateway or an egress-only internet gateway. Well, that is how the private virtual interface works. And you can associate it natively with either the virtual private gateway directly, but that would mean a one-to-one association, right? Or you can bring scale by using the Direct Connect gateway. So the Direct Connect gateway allows you to connect multiple VPCs across multiple regions in AWS to a single global Direct Connect gateway. And that Direct Connect gateway will be the one that would take your traffic over your Direct Connect connections. And again, native, both IPv4 and IPv6 peers are supported. So when you create, for example, a private VIF with both an IPv4 and IPv6 BGP session, and you have your dual stack VPCs in AWS, and you have on your data center side, both IPv4 and IPv6, you will be able to exchange routes both ways on both address families. However, there's also the other question of my data center is v4 still, and on AWS, I have both v4 and v6. What do I do? Well, you can choose to route all the way to the backend on your data center v6, and you can have the routing infrastructure ready for when your workloads on-prem are going to support IPv6, right? Or you can choose not to, and you can choose to say, I'm going to keep IPv6 routing only on AWS, right? I'm going to use Cloud WAN or Transit Gateway or VPC peering, depending on the scale, right? And if I need to go back to the on-premises, I will only have v4 peering. I will have those native backwards compatibility modes, right? With NAT64, DNS64, and dual stack load balancers, and we're going to talk about in a second. And on-prem can continue staying v4, right? So you have full flexibility of choosing how you want to implement each of these connectivity options. And we're talking about scale, right? And we talked about the fact that there's 3 virtual interface types, right? So we have the public one, we have the private one. The private one does get us connectivity for VPCs directly, right? So it's not for the scale where we have hundreds of VPCs across 27 regions, right? But we do have transit gateways. Those give us the scalable routing hubs within each region, right? So if we want to connect directly transit gateways to on-premises, we have the Transit VIF, as its name stands. And again, it supports both IPv4 and IPv6. So you have native end-to-end support here. And we talked about Cloud WAN, right? That fully managed service also supports IPv6 and IPv4 routing all the way to the backend. Again, through the same transit VIF, through the same transit gateway. So that said, hybrid connectivity is done. But that's just for the dedicated connections, right? So dedicated direct connect connectivity. It's not just though the only use case for hybrid connectivity. We also have site-to-site VPN connections, right? IPsec encrypted, folks very familiar with them probably. So to get IPv6 support end to end, you do have to create two connections, one for v4 routing and one for v6 routing. And these connections have to terminate either on transit gateway, right? Or on Cloud WAN, as we're going to see next. So on the inner tunnel, you will have either a /30 in v4 or a /126 in v6. And these addresses, you can either have them configured, or you can let AWS automatically configure them for you. The outer tunnels, though, will be v4, so outer tunnel IP addresses. And if you go global, right, and you have Cloud WAN implemented, you can have multiple site-to-site VPN connections terminating on Cloud WAN, and again, each of them will be configured with a specific use case in mind, either v4 routing or v6 routing. And we're slowly getting to the interesting pieces of innovation on AWS. And one of these areas in which we've continually invested in is how do we bridge the gap between network people and application people? And I've been in networking for 13 years, out of which 6 have been doing the cloud networking piece. The other ones were in the classical, as I used to call it, the real networking, networking on AWS, or in the cloud, which is more like just these logical constructs that you pair together, and then you ask yourself, where's my BGP? Where are my prefixes? And why don't I get communities, right? But usually, historically, for all of us network people at core, we build networks to meet the application needs, right? Like if there would be no applications, networks would be a really lonely place, right? There would be no one using them. So we build them with the user in mind, right? With who is going to be using that network. However, a lot of the times, we as network people don't really get to understand really well or be privy to a lot of details of how that application actually works. What does the application need? A lot of the times we go back and ask developers and we say, what are your throughput needs? They look at us and they're like, I don't know. So what are your latency needs? And they're like, there's such thing as latency? Like, what? Is it not instantly between the East Coast and the West Coast? Well, no, there's such thing as the speed of light, right? So we didn't beat that yet. But we do have a way of simplifying application connectivity. And this is done through a new paradigm in AWS, which is called application networking. And out of this application networking, there are a few things. Some of those you are already familiar with, and some of those are new. The first one is elastic load balancing. So application load balancers, network load balancers on AWS are part of the application networking world, right? Because they help scale application delivery on AWS. So let's talk a bit about how you can accelerate IPv6 adoption by using application networking constructs. So first ones are load balancers. And the first type of load balancer that we're going to talk about is the application load balancer. This is an HTTP, HTTPS optimized load balancer type, right? So for traffic that's at the application level, it's a layer 7 load balancer. And the way in which it's deployed is by making use of subnets in the Amazon VPC. You do have to have at least 2 availability zones, right, across which you deploy it for high availability. And it natively supports dual stack. So when you create your load balancers and you define their capabilities, you can choose if they're internet facing or internal, right? If they're internet facing, they're going to get public IPv4 addresses in IPv4 and IPv6 addresses. The IPv6 addresses are going to be from the subnet siders in v6. You do have to have dual stack load balancer subnets to be able to have dual stack load balancers, right? So if you don't have dual stack subnets, you won't be able to create dual stack load balancers. And to scale, the application load balancer makes use of multiple elastic network interfaces. So as it scales up, it will use more ENIs. As it scales down, it will use less ENI. Now, by default, this is a dual stack load balancer, but it does support both IPv4 and IPv6 targets. So what you can do easily here is you can say, I can leverage either of the two adoption paths, right? You can say outside in, meaning I'm going to make my internet facing load balancer dual stack, and my backends are going to continue being v4 because I don't even know if my application supports IPv6 yet. I haven't tested it, right? So the backend remains v4, and the load balancer talks to the targets using IPv4, but it presents the service to the clients in both v4 and v6. Or you can say, well, I actually want to leverage inside out, and I want to leverage the scaling power of IPv6. And I want to have, for example, IPv6 pods in Kubernetes, right? So you can have a dual stack application load balancer with v6 targets, right? It all depends on your use case. And we've just launched last week on Thursday, I think, or Friday, the capability of deploying v6 only public facing load balancers. v6 only is actually not the correct statement for them, or the correct description of their capabilities. They are still dual stack because they still need to talk to backends irrespective of the backend's capability, right? The backend can be v4, it can be v6. The load balancer has to be able to talk on their language, right? But what the load balancer is not going to have is the A records with public IPv4 addresses, right? So you will be able to access it from the internet using v6 only. Those are going to be the only quad A records that that load balancer is going to have. So it can help you optimize for your clients that support v6, right? Your application delivery and your public IPv4 usage. Now, the second load balancer type is the network load balancer. This is a layer 4 TCP, UDP, TLS capabilities load balancer. It works in a very similar way to the application load balancer. However, it does not scale horizontally by having multiple ENIs. It does leverage a special type of elastic network interface, which is called hyperplane. So it just needs one. But other than that, one per AZ. Other than that, it has very similar capabilities to the application load balancer in terms of IP addressing, right? So it can be deployed in public or private subnets, and it will get an A and quad A record for the entry point. Now, the third and really interesting type of load balancer is gateway load balancer. Now, what is this used for? We talked about layer 7, we talked about layer 4. We didn't talk, though, about a certain type of load balancer that customers do use a lot, which is a layer 3-ish load balancer. It's a bit above layer 3 because it uses Geneve encapsulation, so Geneve tunneling, but it allows you to easily integrate appliances in your traffic flow as a bump in the wire. And this is, for example, a very typical implementation for highly available appliance deployment of firewalls on AWS, like third-party firewalls, partner-type firewalls that can be natively integrated into your application flows without you having to maintain that high availability, right? Without you having to say, oh, I'm going to fail over from one load balancer to the other. Right? So this is natively taken care of by
by the gateway load balancer. And the way in which the gateway load balancer receives traffic is through the gateway load balancer endpoint. So um, if in the IP, in the route tables, you route traffic, for example, between the source and the destination, either on V4 or on V6, through the endpoint, so the endpoint is the next hop in your traffic path, that endpoint can be either V4 only, dual stack, or V6 only. If your sources are dual stack and your destinations are dual stack, you will probably want a dual stack endpoint, right, to match the capabilities. But if you only have IPv6, for example, you can deploy an IPv6 only endpoint, and your traffic is inspected. It goes through the inspection layer, and then it comes back, and the source and the destination IP addresses were never changed, right? That's the layer 3 bump in the wire. Now, I mentioned that application networking has some components that you folks are probably already familiar with, and also some components that are new. And I think one of my favorite, even though I'm not sure even that I'm allowed to say that because I am in networking and I do work with all the networking services on AWS, but one of my favorite services is Amazon VPC Lattice. And the reason why it's one of my favorite services is because it's the one that brings those application folks really close to the network folks and bridges that gap of understanding of like, what is the application doing and where is the application and what does it need to talk to? It also gives the native security controls that security always comes and says, oh, service 1 cannot talk to service 2 and service 3 should talk to service 4. And that zero trust paradigm, right? That a lot of enterprises are bound to implement it now. So let's look at VPC Lattice. And purposefully, I have two VPCs here in a region that can have whatever capabilities in terms of IP addresses. The power of Amazon VPC Lattice is that it fully abstracts the capabilities of the clients and the services. And VPC Lattice comes with some new constructs. The first one is a service network. You can think of it as a logical boundary. Like the VPC is a network logical boundary, your service network is a new type of logical boundary that helps you define what should be accessed and who should be accessing that what, right? So let's see what should be accessed. Those what should be accessed are services, right? In the VPC Lattice speak are VPC Lattice services, which you define. And these services are the ones that you're familiar with, deployed on various compute types on AWS, EC2, EKS, ECS, doesn't matter. And as long as you define them as Lattice services, you can then go and apply security policies to them, which are IAM, identity and access management policies on AWS. So auth policies that say who can access this service, right? And how that who is identified. So you define them as services in Lattice, you associate the security policies to them, and then you associate them with the service network, right? So when a service is associated with the service network, it gets the capability of being consumed, right? Well, I have service A through service D that are associated with the Lattice service network. That means that they can be consumed. Who can consume them though? I don't have consumers defined yet, right? So in order to have consumers, I associate VPCs to the service network. So the services that are deployed in the VPCs that are associated with the service network are now able to consume the services in the service network. So very easy and straightforward. The network boundary stops becoming an impediment in application connectivity, right? The fact that you have different VPCs, different accounts, no longer warrants itself a a blocker in establishing connectivity between services, right? And VPC Lattice automatically manages the fully qualified domain names of every single service that you register into Lattice or that you create. And by default, it has both IPv4 addresses and IPv6 addresses. So it natively fully abstracts the capabilities of both the clients and the service. Because depending on what the client supports, it's going to do a DNS query and it's going to use the address that it can use, right? And last but not least, AWS Private Link. AWS Private Link is a service that powers both AWS services and your own services to be consumed privately within VPCs. We're going to focus today on the private link for customer managed services, so for your own services. And you're going to see that it's actually very similar to VPC Lattice, but it gives you a narrower scope, which is essentially a service to a few VPCs. Now, the way you create private link endpoints is by front-ending your services with network load balancers. Network load balancer is the one that powers private link. Your targets could be EC2 instances, could be any compute type, could be an application load balancer as well, if that is the requirement. And as long as the network load balancer is dual stack, again, your targets could be whatever they support, either V4 or V6. When you create the endpoint service in private link, you create it as a dual stack endpoint service. And the interface endpoint in the client VPC or in the consumer VPC, right, can automatically be created depending on the capabilities of the client. So it could be a V4 only if the client is V4 only, because if the client didn't even get to adopt IPv6, it will be V4 only. It could be dual stack if the client has a mix of V4 and V6 capable workloads. And it can also be IPv6 only, right? So you have full flexibility of how you deploy and provide access to your service. And we've gotten to security. So we talked about connectivity. We talked about connectivity at scale on AWS. We talked about hybrid connectivity. We talked about application networking, which bridges that gap between developers and admins. Let's see how we secure natively on AWS. And I'm definitely not going to have time to cover all the security services on AWS, but I focus on the three ones that are probably the most common ones. And first, network access control lists. You have them created by default in the VPC. They're associated to every single subnet that you have in your VPC. You cannot delete them. You can modify them though. And they support stateless filtering, right? So they don't know about sessions. Stateless filtering inbound and outbound from and to your subnets. Now, they natively support V4 and V6. So you can have V4 rules, you can have V6 rules in them without any additional configuration. And we talked about network access control lists, which are stateless. However, stateless means that they don't know about connections. Security groups, on the other hand, they are your resource level firewall, right? So they are layer 3, layer 4 filtering mechanisms. And they are also stateful. So they know about connections, right? Connections in terms of like TCP connections. So they again allow you to filter inbound traffic and outbound traffic, and they natively support IPv6. And last but not least, AWS Network Firewall. We talked about Gateway Load Balancer that allows you to integrate your third-party firewall appliances on AWS, if you prefer so, or you can use the native AWS firewall service, which again, works through endpoints that are next hops in your route tables to route traffic to the inspection point. And they also support all three flavors of deployment: V4 only, dual stack, and V6 only. And because we talked about security, our last stop is scalable global connectivity at the edge. And here we have a few services that we're going to talk about. First one, CloudFront, our content delivery network. CloudFront distributions are natively dual stack, right? So you can connect to your distribution from both V4 and V6 clients and support origins like Elastic Load Balancers, EC2, S3 buckets, or custom origins if you wish to. And the second one is Global Accelerator. This is a service that I particularly like a lot because it taps into that networking geek inside me that helps essentially bring the client traffic on the AWS backbone as soon as possible. So to avoid the client traffic traversing intermediary internet service providers by the time it actually gets to the edge on AWS, to your application. AWS Global Accelerator makes use of Anycast routing, and it provides you for each of the global accelerators that you create with two Anycast routed IPv4 addresses and two IPv6 addresses if you choose to deploy it in dual stack. And it does support IPv6 all the way to the backend. So you can have dual stack Elastic Load Balancers or EC2 instances. Also, really, really important and differently from CloudFront today is that those targets that you have for application for Global Accelerator can be private in the VPC. So you don't need to have public IP addresses on them to be able to configure Global Accelerator. And with that, this is probably my favorite part of this presentation, where we go through a few lessons learned, war stories, as I like to call them, from a lot of conversations with AWS customers. And these challenges are in no way, shape, or form different from what everyone is facing on this journey, which is IPv6 adoption, because it's a journey and we're all on this path. And a few of them, which I particularly like, is find your supporters. It's really, really important to find some teams that are willing to go on this path. Helping leadership understand why IPv6 is important is super, super, super important, because IPv6 is a non-revenue generating, not directly revenue generating adoption journey, right? It's not like you're building a new feature or functionality in your application that's going to bring more users, right? You may be improving the end user experience, but it's not directly quantifiable like that. Although talking about revenue generating, NAT44, I mentioned that we use it in so many places, and especially for that use case of mergers and acquisitions. We do have customers who've gone the IPv6 path for that specifically, and they optimized on cost for NAT. Oh, also a very important one, the VLSM mindset. Not there, right? So I've heard a lot from a lot of customers. How do we make /96? How do we make /80 subnets? You don't need to, right? /64 actually helps you create a really clean adoption plan. Oh, and the last one was there, avoid analysis paralysis. That's really, really important. If you're gonna focus on analyzing everything, you're for sure gonna miss something. So start somewhere, start building that experience. We do have a service compatibility matrix. I wasn't even intending, but I wasn't able to actually touch on all the services in AWS that support IPv6. There's a lot of them, and they keep coming. So you will have a service compatibility matrix there that you can check out, and you do have a repost article that lists all the resources that you have available on AWS, starting with documentation, what's new, blog posts, white papers. We continue building those, and as they come out and get launched, we're linking them there. So that's the place. And if you folks like the sticker, we do have stickers here. So thank you. Thank you for sticking around for so long. And yeah, if anyone has any questions, we do have a good amount of stickers here. And who answers questions, who asks questions gets more stickers.
Not a question. I'm with a PC. Thank you, Alex, for that talk. It was super informative. By the way, she doesn't use speaker notes, and she's been speaking on this for 2 hours. So thank you for that. And if you have any questions, remember to state your name and affiliation. I'll be looking at the online Q&A. If you're following from MeTecho, just make sure you send your questions. Thank you.
Tom, thank you.
Hi, Alex. Yeah, Tom Hill from BT. I think it's an absolute testament to your commitment to IPv6 on AWS that you've spoken about that without any notes. That's incredible.
Thank you.
I'm in awe. I did have a question from a peer of mine, actually. By the by, they've been working on doing some, using some application load balancers to front a DHCP v6 service. But apparently it's not working. So I wonder whether or not, it seems like a bit of a niche thing to do, but I wonder whether or not you are aware of whether there is a limitation there at the moment.
So you're using, let me see if I got that right. You're using application load balancers to front end the DHCP service.
I'm not doing it.
Okay.
A friend of mine is, but yes, I believe that's what they're doing.
I think we should talk a bit more about those. I'm not sure how you target them, meaning do they get the targets, they receive HTTP traffic?
I wouldn't know, but I can set up a conversation.
Awesome. Yeah. So I think we're connected already on LinkedIn, and I would love to dive deeper into that. And there's no direct limitation into the application load balancer talking to v4 or v6 targets on the protocol that you define. However, having DHCP v6 behind the load balancer is a new one for me, so I would love to talk a bit more about that.
I have my suspicions, but it'd be great to talk about it.
Awesome. Thank you.
Sipeng Xiao from Huawei. Alex, you mentioned that your VPC is still dual stack. So I wonder, does your IPv6 actually reduce IPv4 address usage? Because if you still have IPv4, then will the IPv6 reduce IPv4 address usage?
Yes, okay, got the question. I'm going to repeat it. So if IPv6 actually reduces IPv4 usage, absolutely. One of the use cases where that happens is, I mentioned that you have all these routing constructs like Transit Gateway and Cloud WAN or through which you can route both v4 and v6. You can choose to have overlapping IPv4 space, or you can continue with your existing overlapping v4 space. And as long as you get unique v6 space, right, you can keep local that v4 space and route v6 on your internal network. That's one way to do it. The second one, your v4 CIDRs in the VPCs, because you get v6 only instances and v6 only pods in Kubernetes, you can have much smaller CIDR blocks in your VPC in v4, right? And those CIDR blocks are going to be used for the things that provide that backwards compatibility, right? So for your NAT gateways to provide NAT 6.4, for your dual stack load balancers, because your clients are going to be probably on v4 for quite some time now, right? You won't be able to say tomorrow, all my clients are v6, and I'm going to put only v6 only load balancers or v6 only resources. So you do still need that backwards compatibility. but you can achieve it with a much smaller IP space in v4 because v6 gives you that scale of deploying the workloads that don't necessarily need to be accessible one by one, like IP by IP, right? So you put them behind load balancers, you put them behind the ingress controller in Kubernetes and so on.
Thank you.
Awesome.
Can we easy enable dual stack on the existing infrastructure?
Sorry, can you repeat that question?
Can we easy enable dual stack on the existing infrastructure?
Absolutely. Yes. We do have a guide, actually. If you scan that, let me go back on this one. So in that list of resources, there's a page in the EC2 documentation of how to dual stack your existing infrastructure. And we looked at the beginning in how you dual stack your VPC, right, and your workloads. And step number 1, add v6 to your VPC sliders. Step number 2, create or retrofit existing v4 subnets to dual stack. And then go to your workloads, your load balancers, your EC2 instances, whatever those workloads are, and choose if you want to dual stack them in place or if you want to create new ones that are dual stack, right? And then configure DNS. That is the path to get IPv6 supported. One very important lesson learned that we haven't talked about actually is getting DNS in place for v6 before getting routing, which is tricky, right? Because if your workloads start resolving DNS, they support DNS, they support IPv6 and they start supporting DNS resolution on v6, but you don't have the routing in place, right? You will see increased failure rates in connectivity. So we've actually published a guide on how to deal with DNS in that space and to filter DNS queries if your routing is not in place already. But the best practice is to get routing in place and then add DNS support for Quad A records. I hope that answered your question. And if you have more questions, please reach out.
Hi, Marco Davids, SIDN. Thank you for the presentation. I was wondering, does AWS also have plans to actively discourage the use of IPv4? I mean, I know you're charging money for IPv4 addresses, but maybe to go beyond that, to actively discourage?
So we work backwards from our customer needs, right? That's our stance, and I think that's the right thing to do because we do want to allow customers to meet their needs on AWS. And I think by providing the IPv6 capabilities that we keep doing, right, and we keep building on, we will slowly encourage customers to use IPv6 rather than discourage them from using v4, right? So I think that's probably the mindset that I would have around it. Thank you. Any other questions? Everything was clear or nothing was.
Okay, thank you so much,
Awesome.
Alex. That was
Thank you.
great. And thank you for all your questions.
And please come grab stickers.
Yeah, they're really cute. The cat over there is one of them. So we're gonna go to the coffee break now, and we'll be back for the newcomers introduction.
Hello, hello. Yes, this works. Good morning, everyone. This is the newcomers introduction session. If you don't want to be here in this, then you're in the wrong room. But I think this is the only thing that's going on right now. So it's great to see so many newcomers here at this meeting at Vibe 88 in Krakow. My name is Miriam Kühne. I am the Vibe chair. Well, welcome. I just said this. This is your first. You should all have a little sticker of my first Vibe meeting so people can find you and then help you out if you have any questions. I'm Miriam Kühne. I am the Vibe chair since 2020. I've been involved in the Vibe community for a very long time, and I also worked at the Vibe NCC on and off a few times in different roles. And yeah, so I've been, I have a lot of, I know a lot of people have a lot of experience, so please don't hesitate, come to me and ask me any questions you might have about the Vibe meeting or the community at large, or if you want to meet anybody in particular. We also have the vice chair. Oh, there you are, I'm like right in front of me. Yeah, if you want to introduce yourself.
Thank you, Miriam. I'm Neil O'Reilly. They even have a photo of me, and I've been coming to RIPE meetings even longer than Miriam has. I started in 1989, and in the intervening, at the time, internet in Europe was still mainly present in universities and research institutes. The commercialization was only beginning. So like most of the other people who were coming to RIPE meetings then, we were getting the DNS sorted out. We were getting all sorts of initial infrastructure done. And I was delighted to have RIPE meetings to come to because I could learn stuff because it was all new. And in the intervening years, I've led a couple of RIPE working groups, DNS related ones. And in 2020, like Miriam, I was selected to join her and be vice chair of RIPE. And it's still great fun. And there we are. I'll hand the mic back to Miriam.
Thanks, Neil. Yeah, maybe just a bit more information because Neil mentioned where he's from. I'm from Berlin originally. I'm from Germany. I studied computer science at the Technical University in Berlin. And now we have quite a number of people from Germany usually at these meetings. So I'm happy to meet you all as well. Just a bit of a blast from the past. I mean, this is just a bit of fun. I don't know if any of you have seen or even had one of those machines in the back. Yeah, I see someone. But what I find more fascinating is actually that graph here, a diagram on the other side, which shows the internet in Europe in 1990, roughly around the time when the web community started. And you probably won't be able to read this, but they're mostly the research networks that were connected at the time. Interestingly enough, we had a couple of weeks ago in Athens at the Southeast European meeting, we had a special session with the 40th anniversary of the EARN community, which were actually the academic networks at the time that started a lot of the internet developments in Europe. And it was really fascinating to meet those pioneers. And so for a longest time, we had a connectivity working group at the beginning of the RIPE community. And those people would keep track of those maps and would add, when a country was added to the internet or a new network was added, it was a big deal. And then a new graph was produced and was published on the website. You can still find some of those earlier diagrams as a RIPE document in the RIPE document store on the RIPE website. So some work for you here. Maybe there is a poll at the Meet Echo. If you're online, you will see that pop up in your Meet Echo interface. If you're here in the room, I'd like you to try this out. You had an email this morning that had in the subject line your Meet Echo link. If you go to that email, there are two links. There's one online and there's another section where it says, if you're on site, click this link and then you will it will open the Meet Echo app in your browser. And Meet Echo is the platform that we're using here throughout the week, so it might be useful for you to play around with it a bit. I don't know, have you started the poll? Have you started the poll? Yes, it's going on. And so the question is, do you know the difference between RIPE and the RIPE NCC? We often blur, the difference there. Everybody kind of says RIPE. They mean maybe the RIPE NCC or RIPE. So we're going to tell you a bit more about this. But to get started, I'd just like you to fill in the poll. Do we see results coming in? Are you in there? Can you see it? Oh, the poll will end in 59 minutes. We're not going to wait that long, no. So I will wait maybe another minute or so if people have found their link. Do you have any problems finding the link? It's good for you to have that handy because I'll get back to that later. That's also a good way to chat with each other, to ask questions, to find to find other people that are also in the app, to communicate with the online participants. And so, yeah, it was just a little test if that's possible to find. We can close the poll, I think, and see the results, hopefully. Is it closed? Yes. Can we see, or can somebody read out the results? I don't know if you can see them on the screen, or if somebody can just throw the numbers at me. Ulka is going to read them out. Thank you.
Ulka Atle, RIPE NCC. And we have the poll results on the screen as well. I've lost my Eurovision moment, but we have certified the results. 28 yes and 12 no. Thank you.
Thank you. Thanks for showing the results and for reading them out. So some people know what the difference is, some others don't. So we're going to go through it and no matter what. So I'm going to talk to you a little bit about RIPE. And then later we have am I too close to the mic? Is there an echo? No, it's just me hearing an echo. And then we have the managing director of the RIPE NCC tell you more about the RIPE NCC later. So yes, let's start with the RIPE community. So RIPE stands for Réseau IP Européen, European IP Network, was started in 1989 by some of those pioneers that I mentioned earlier and some of the academic institutions and the national and research networks. It was always created as an open community. It's no legal entity. It's just an open group of people who come together with a common interest and a common goal. And that was at the time to promote IP. And that's still, to promote the internet and internet infrastructure, coordinate certain technical aspects that need to be coordinated in order to connect all these networks and make the internet. So that's still the main goal of the RIPE community. And plus a number of best current practices that the RIPE community writes and policies, for instance, on how to distribute IP addresses. Now, the RIPE NCC was formed a little later, and it was initially formed as a secretariat for the RIPE community to organize the meetings, host mailing lists, maintain the first RIPE database that would have contact details for networks and for IP addresses and how to find each other. And so the RIPE community formed the RIPE NCC as a secretariat. And then later, the RIPE NCC was also then accredited, if you will, as the first IP registry because it already existed. It provided great services to the community. The community trusted the RIPE NCC to also then become the first regional internet registry and fulfill that role, in addition to all the other secretariat services they already did. Now, the RIPE NCC is a membership organization. It's a legal entity. It has staff and an executive board that's elected by the members, and it provides services to members, but also to the community at large and to us here at the RIPE community. And it also has the function to implement the policies that are agreed and developed here in this community. So there's quite an intricate relation between the two organizations. Well, the RIPE community has different aspects to it. I mean, I'll get to the meeting plan and what you can expect during the week, but one important aspect are the working groups. So there are 12 working groups at the moment with various topics. As you can see here, you can also find the list of all working groups on the website, who the chairs are, what the charters are, what their main topic is some of the working groups are currently reviewing their charters. So that might be interesting to follow that discussion. And yeah, just find the working group that discusses topics that you're interested in. Our main communications channel in this community are mailing lists, because we started in 1989 and that's still what we use as the main communication channel, but also because, well, at least until recently, it's quite a reliable communication channel. It has archives, you can find things, and it's kind of fair. You can, find, you can subscribe, all the lists are open. You can subscribe to all the mailing lists there. We also have other channels. The RIPE NCC, for instance, maintains a number of social media engagements for the community. There's a forum, and people also set up other communication channels on the side that you can join. Maybe as a first start, you could subscribe to the RIPE list as a first step. That's kind of the overarching mailing list for anything related to the RIPE community as a whole, not specific to one working group. And it's open, you can subscribe. There's information on a slide here you can find to subscribe there. It's not a lot of traffic. It kind of comes in bursts. There are relevant announcements, and also from time to time, people kick off some discussions that are interesting for the whole community. Now, let's dive into the RIPE 88 a bit more. And you can see here the meeting plan. You probably looked at that before you arrived, but just in case, I'll quickly go through it. We'll have some lunch after this. There's actually some specific lunch reserved also for newcomers, so you get to know each other, and also some of the older community members, who will join us there. And then afterwards, we'll have opening plenary, some plenary sessions today and tomorrow with that is put together by the program committee that kind of fill Monday, Tuesday, and a bit of Friday. Then tomorrow afternoon, we'll start with the working group sessions. They go on until on Wednesday and Thursday as well. And then on Wednesday, you see a little darker green square there. That's the RIPE NCC membership general meeting that's only open to members. So you could have a free afternoon and enjoy this beautiful city here. Well, I mentioned the BOF before. BOFs are birds of a feather. Birds of a feather like to flock together. Is that what it stands for? I can never remember that. It's kind of not my language. It basically means people with the same interests or similar interests come together to discuss one specific topic. It's usually a one-off, like one session during a meeting to exchange some ideas. And so we have two of them today, this week, one today and one tomorrow. You'll find some more information on the website with a more detailed description as well. But it might be interesting to experience that. Then on Thursday, we also have a diversity and inclusion session. We've done it a few times. It's different every time. Sometimes there are presentations, sometimes there's a good discussion going on. Last time we had some lightning talks, and this time also we put together an interesting program with some kind of topics that maybe don't fit otherwise into the program, but they're really interesting. And we also like to hear from you what your experience is, and if you have any ideas and how to increase, the inclusion and diversity here at the RIPE community. Yeah, there are certain ways you can participate. I mean, certainly you online, you're following online. You are going to be in this MeetEcho app for most of the week. There is a queue. If you have a question, then you raise your hand basically, and then the session chairs can give you access to video or audio. I encourage you to also do that when you're in the room. It kind of helps with the queuing, especially if there's a lively discussion going on, and everybody's in the same queue, and it makes it easier for the chairs. But there's also a Q&A in the MeetEcho, and of course we have microphones here in the room for those of you who are here. You can use those. And there's a chat in MeetEcho that you can use to talk to each other and ask questions, other people might be able to answer. I'm also really pleased to see that we have local hubs again. We experimented with that last time for the first time kind of as a pilot. And we have 4 of them again this time. It's basically people come together in their hometown or home country and have a little mini RIPE meeting. Instead of sitting at home alone behind a screen, they come together in one place and have a bit of a community feel to it and then follow the meeting remotely. Not all of them will be there all week, but I hope we'll hear more from them later in the week. So if some of them are already online, I don't know, welcome to this meeting as well. Now you're all here, so you must have a motivation, a reason why you participate, but maybe just to give you a bit of an extra motivation, obviously this is a really great place to meet some of the experts, and some people have some great experience and great expertise. I mean, there's some people who are still around in this community who basically started the networking in Europe, and that's really good. I mean, if you think of it, the internet is still relatively young. And some of those first generation pioneers are still around. But overall, I mean, all of us here have like expertise in certain fields, and so it's a great way to exchange knowledge and then information. And it's also a good way if you're just starting your career to maybe get some help or advice and kind of form your career that way, find a job, find an internship. And then also, of course, for us, it's important that you participate to help us further develop this community and further kind of shape the internet the way you want it to look like. Yeah, as I mentioned, the RIPE plenary session is today and tomorrow and Friday, which is put together by the program committee that looks like this. These are all the people. I don't know if we have anybody here in the room from the program. Yeah, I see Clara and there's Wolfgang over there. So they're doing some great work in the background, putting together the plenary sessions and trying to make sure everybody gets a slot and has basically built this interesting program with them, a wide scope of topics. There are some elections going on also. You'll see some more information. You can select new people onto the team. And the pre-C and also the working group chairs, they would really like you to rate the presentations, because that gives them some good feedback about their work and about what topics you'd like to see, and if you like the way it was presented, or if you are interested in other topics. So if you go to the meeting plan or on the website, you can find the presentations there, and all the slides, they're usually uploaded before the session, so you can also look at the slides on your screen or before the presentation, and then there's also a rate the talk button, and you can give some feedback there. So that would be really useful. Obviously, we also have a code of conduct in place that you all should have seen when you registered for the meeting. Basically, this is quite a diverse community with people from all walks of life, with different nationalities, different backgrounds. And so we want to treat each other with respect and tolerance, and we want to make sure everybody feels safe and included. If you experience anything that you don't like, or you think it's something that's not right, or the breach of code of conduct, we have a great team of experts that form the code of conduct team. I've seen some of them here in the room. Vesna is over there. I don't know the others. Oh, there's Lume. There are posters hanging out in the hall also where you can see the faces. Not all of them are here at the meeting, but they all communicate with each other behind the scenes. And so you can also contact them online. There's information on the website and how to find them, and they have a secure way of communicating if you need that. Network here in this context, I think, means mostly social networking. So how you find each other, talk to each other. There are various ways to do that. I already mentioned that. But there's one other thing, and the attendees list might also be an interesting point of information for you. And you can see who else is here. And if the attendees have switched on their social feature, I don't know what it's called, then you can also see how you find them and find the email address and contact them and make a meeting, set up a meeting with them. Here on site, not for those online, unfortunately, but we have some social events lined up during the week. There's a meet and greet event later today, welcome session. Then tomorrow is a networking, like a party after the sessions. And on Thursday, we have a dinner. You can find all this information on the website. There's also a special session organized on Tuesday for those of you who have academic background or students, or you work in a research institute. There's an opportunity to meet with each other and kind of build a mini community within the community. But of course, we want you to also talk to everyone else. Yes, let us know what you like about the meeting also, and provide us feedback. There's a feedback form on the website, and there's also a lot of engagement on social media. Some information about, if you need more information than what I'm providing you here, or if you have any questions, there is a great meeting team and also a good technical team here on site. I think the best way is just go to the registration desk, or maybe even better, find those people in these red t-shirts. Do we have anyone in the room? Oh, Alistair here is also one of the meet and greet designated people, but usually whoever is on duty, they have these red t-shirts on, and they just know anything, everything you can ask them, where is the lunch, how do I connect to the network? They can point you then to the right place. So don't hesitate to ask any questions about anything about the meeting or the community. And then one last thing I want to point out is what a bit of a task for you maybe. The RIPE NCC is currently undergoing a project to update and modernize and upgrade their websites. They started with the main www.ripe.net. It has a new structure. We have a better way to find the RIPE community and the RIPE NCC. And they're also undergoing a project to do that for the meeting website. So the meeting website is a separate site. So if you registered, you end up at RIPE88 or RIPE.net, and then you see all the information there. And so since you've just done this mostly for the first time, the newcomers of you, we would really like to get your feedback also. So we have Phil Oldham, who's sitting right there. He's the main contact person for this project. And so if you have any feedback and anything awkward that you notice while you're going through the process, or anything that you think is missing or unclear, please let Phil know. Don't tell me. I have no influence on this. I'm just benefiting from the great services they provide. And that closes my part of the presentation. I would like to hand over to Hans-Peter Howland, who is the Managing Director of the RIPE NCC. Thank you. We'll have some time for questions at the end. If you have any questions for this part, remember them.
So thank you, Miriam. I woke you up now. I'm Hans-Peter Holen. I'm the Managing Director of the RIPE NCC. And I've been a member of this community since mid-90s, when I was working for one of the first ISPs in Norway, and I needed IP addresses. And therefore, I contacted the RIPE NCC. RIPE NCC, as Miriam said, was set up by the community, and it was formalized in 1992 as a project and later on as a membership association. It's run by staff. We're now almost 190 full-time staff, both in Amsterdam and in Dubai and in other locations. We provide services, and we're the secretariat for the RIPE community, and we implement policies set by the community. Our strategy is to support an open, inclusive, and engaged RIPE community. And we do that. And the community asked us early on, as Miriam mentioned, to operate a trusted, efficient, accurate, and resilient registry. That's the regional internet registry for Europe, Middle East, and Central Asia. And back in the days, you could come to the RIPE NCC to get IPv4 addresses. Today, we don't have that many left of those. There is a waiting list, and there are some small bits and pieces returned to us from time to time. But we still have IPv6 addresses. So if you haven't really thought about how to deploy v6 yet, that's something that you should. And we have content on the agenda that may be interesting for you in that respect. Now, the internet is connecting networks. Now, connecting networks actually needs network engineers to talk together, and that's why we also want to enable our members and community to operate one secure, stable, and resilient global internet. We're more than just a registry. We're more than just a phone book that some people would like to describe us on. Because in order to run this registry and defend this registry against governance, against big corporations and others that do not want to see a strong, collaborative, open, secure, resilient internet, we need to do more than just keep a record. And in order to do so, we need a stable organization with robust governance, and we need to attract, engage, competent, and diverse staff. We have staff from more than 42 countries in our organization. The RIPE NCC registry maintains the RIPE database, allocates, manages internet number resources, and we have a portal, the LIR portal, that you can manage your resources. But we don't only do that, we also investigate hijacks and policy violations because we want to keep the registry accurate. We support and facilitate the policy development process with the community. So Angela will be on stage later and talk a bit about that. And also we operate the RPKI service where you can sign a statement to which AS numbers can announce your IP addresses, your blocks. We have information services. RIPE Atlas, it's a huge measurements network with more than 13,000 probes all around the world. And you can run your measurements in there to see how your service looks from anywhere in the world. We have RIS, where we collect routes from BGP. And you can use IP map and you can use RIPE stat to look at these data. We also delegate reverse zones for your IP addresses. So some services like email, for instance, looks up your IP address in the reverse DNS to see that it's actually associated with the domain name that this email comes from. So it's an important part of the internet infrastructure. I already said the main driver to get the internet to work is people talking together. Yes, it's about routers and it's about protocols and it's about the right configuration. But in order to get all this right, you need to talk to each other and communicate. So we organize RIPE meetings like this. We have 2 a year. We do regional meetings in Southeast Europe, in Middle East, and in Central Asia. And we do other smaller events as well. We offer training courses, e-learning, and professional certifications. We contribute to the global public policy and internet governance discussions, not because we like to do that, but we do that to defend the RIR system and the open internet. And to educate the governments that is involved in the governance of the internet. We publish and curate articles on RIPE Labs. So if you have something interesting to share with the community, you can approach us to get it published on RIPE Labs. And we run the RIPE NCC Community Project Fund. To steer this organization, I have an executive team, and you will see most of my colleagues here. Felipe, my CTO, James, our Chief Registry Officer, Hisham, our Chief Community Officer. Eleonora is on maternity leave. I have a stand-in Chief Information Security Officer, but he is not here. He takes care of the security while we're here. Athena, our Chief Legal Officer, Caroline, our Chief Human Resources Officer, Simon Jan keeps track of all the money as our Chief Financial Officer, and Daniela keeps track on me and the board and the whole exec team. The executive board is elected by the members. There is a general meeting on Wednesday where there is a board election, and there are 2 seats up for election. So it's going to be exciting to see what new blood we will get in on the very important board that sets the strategy and approves the activity plan and the budget. Andrei Filip is the chair. Piotr is a local from Poland, so if you have any questions in Polish, you can ask them to him. Remco and Job and Raymond and Maria and Harald are all going to be here as well. We have a support desk where we have NCC staff available to help you. And this is your one-stop shop for anything related to RIPE NCC. And they really want to talk to you. General meeting I mentioned, it's a separate meeting taking place on Wednesday from 4 o'clock. And only members can participate. So you need to register separately for the general meeting, and members can also vote online. So those that are not present here, they can also follow the general meeting online and take place in the voting. And then with that, the guidance to the RIPE NCC in policies, yes, Angela, I'm just sort of keeping it rolling. Angela will now talk a bit about the policy development process.
Thank you, Peter. I'm Angela Dallara. I'm the policy officer at RIPE NCC for the last 4 years. I joined the organization 10 years ago as internet analyst. And I'm here, first of all, to welcome all our newcomers. It's always a pleasure to have new friends in the family. And of course, also the old comers. It's always a pleasure to see each other again. I'm a sort of a link between the RIPE community and the RIPE NCC for what is concerning the policy development. The RIPE NCC is implementing the policies that are accepted by the community. Everybody is part of the community, so you don't need to be a member, you don't need to be a network operator. You can propose a policy or have a good idea and propose it for the development in RIPE NCC in the community to be implemented by the RIPE NCC, no matter where you come from, which is your position. What I'm trying to do here is really to invite you to be part of discussion, make yourself acquainted with the policy development process. It is a process that is very inclusive, is working in already for a long time in the community. And for this time, I would like to you to focus a bit on the discussion that there will be in the address policy working group, because for them it's time to review the policy for the IPv6 IP addresses distribution. We have policies that are already something like 20 years old, so probably it's time to have a look at them and see if what we have now is ready and is fit to respond to the needs for the years to come. So I invite you to join the session on Wednesday morning, and also I invite you to join other sessions, eventually anti-abuse working group or database working group. Those are the working groups where you can find topics that can lead to new proposals. If you have any questions about how policies are developed, about the process, which are the phases, what happens, which are the different, how can I say, requirements for a proposal to advance through the policy development process, don't be shy, ask, and I'm going to be happy to help you in getting more familiar with the process. Just to let you know, lately we had a couple of policy proposals that got accepted, and they were proposed by newcomers. So, you know, again, try to be part of the policies. Last time I said you're all policymakers. I repeat the concept. We really look for your participation and to help you out in being in sharing your ideas and make them implemented if possible. And with this, I give you, Miriam, back the floor.
Thank you very much, Angela. It was very inspiring. Now, this actually concludes our session. Did you want to talk about that? Oh, that's for me. Okay, keep in touch. I was like, I thought this was Angela's part. No, but we already said most of that. So there is some ways to, of course, communicate with each other. No, but are there any questions after all this information that we threw at you? You have any questions about anything you heard, anything you expected that we didn't cover? You know what to do the rest of the week. You know who to ask. Well, seems so. If you don't have any questions, we have questions. So we'll have a quiz for you, and we'll hopefully hear. Did you want to say anything else, Hans-Peter? No? Oh, yes. There is a quiz that we prepared for you with a bit of fun. And I hope if all goes well, our quiz master, Gerardo Vivier, will be there in the background starting it. I see you.
Getting ready.
There you go. Take it away.
Sorry, sharing takes so much time. Welcome everybody to our Ripe 88 Newcomers Kahoot quiz. My name is Gerardo Vivier and I am your quiz master. We are broadcasting today using an IPv6 connection because 128 bits make me happy. Now, when you sign up, remember to put your registration number and your nickname if you want to get one of the prizes that I've been told that there are prizes. But anyways, we'll try to find you in any case. The goal of the quiz is to let you check your knowledge. Let's see how much you remember from everything that was said. Ouch. Now, let me tell you how to play the game. You can see this game pin 7070492. If you go to kahoot.it or use the Kahoot app, you put in the pin code, and then you put in your nickname, and then you are ready to participate. I'm going to show you about 12 questions about what everything that has been said, and let's see how much you can remember. We're going to give you a minute to sign up. Some people are still probably typing in their nicknames. And we're going to see if we can have a little bit of fun. So remember, there's 12 questions, 4 possible answers. The person who answers the right answer the fastest gets the most points. And the person with the most points at the end of the quiz wins the whole thing. We got 68 people signing up, 69 people. I can still see some people signing up. Let's give it a little bit of time. And before we launch, wow, I see a wave of people signing up. This is really fun. The more people there are, the funner it becomes. Yeah! So let's start in 5, 4, 3, 2, let's go. Okay, for the first question, for the newcomers quiz, it is, can you imagine? Who is the ripe chair? Is it the ripe chair team? Is it Neil O'Reilly? Is it Miriam Kuhne? Or is it Hans-Peter Holland? So who is the ripe chair? This is quite an easy one because the answer has been in front of you the whole time. So who is the ripe chair? That is right. Miriam Kuhne is the ripe chair. Together with Neil, she makes the ripe chair team. And Hans-Peter Holland is the ripe NCC CEO. Let's see. Scoreboard says Masud Nick at the front, Clara, Habib, Savas, and JD. Next question. What does the ripe PC do? Does it choose the presentations for the working group sessions? Does it select the working group chairs? Does it choose the presentations for the RIPE meeting plenary sessions? Or does it ensure that there are parties and celebrations at each RIPE meeting? One of these 4 things is what the RIPE PC does. And if you remember what PC means, it's not politically correct and means program committee. And that's right. It chooses the presentations for the RIPE meeting plenary sessions. All the great things that you're going to be seeing this week has been chosen by them. Scoreboard says Europa is at the front. Lala, Pavel, Clara, and Buster. Question number 3. Who makes RIPE policies? Is it Why Should I Care? Is it the ITF? Is it RIPE? Or is it the RIPE NCC? So the RIPE policies are proposed, discussed, developed, and accepted by whom? And if you choose the first answer, why should I care? You've got something coming for you. That is right. It is RIPE who makes the RIPE policies. IETF makes technical standards. RIPE NCC just implements the policies. And why should I care should not even be here. Lala at the front, Buster, AI or Al, I don't know. Clara, Joe, 10. Next question is, who implements the RIPE policies? And I just gave it all away. Is it a RIPE NCC? Is it a RIPE chair? Is it RIPE or is it everybody?
Initiate countdown.
No, we already did the countdown. Is it RIPE NCC? Is it the RIPE chair? Is it RIPE or is it everybody? I think everybody kind of follows the policies, but there's only one organization, and that is the RIPE NCC who implements the policies. RIPE makes them, RIPE NCC implements them. Scoreboard says Lala's still at the front, Buster, Al, WT15, and Elvis Vilea coming up. Question number 5. You need to become a member to join my fan club. Well, everybody can join my fan club, the RIPE meeting, the RIPE NCC, or the RIPE community. So in order to join one of these 4, you need to become a member. It's not so difficult. No, it's not so difficult. The right answer is, of course, you need to become a member to join the RIPE NCC. Anybody can join the RIPE meeting, anybody can join the RIPE community, and anybody can join my fan club. Details at the end. Lala, Joe, WT15, Al, and Mass 317. On to the next question. Working groups discuss RIPE policies on mailing lists. Is this true or false? True or false? False or true? Working groups discuss RIPE policies. They do. And they'll do it in a place where it can be all archived and registered, and that is mailing lists. So it's true. Working groups discuss RIPE policies on mailing lists. During the meetings, they also discuss, but everything has to go to the mailing list to make it valid. And Lala is still there. Joe, 10, WT15, Al, and Mass 317. Next question. Which of these is not a RIPE working group? So do we have the big data working group? Do we have the open source working group? Do we have the DNS working group? And do we have the IoT working group? One of these 4 is not real.
Oh, here comes trouble.
Oh, here comes trouble. So do we have an open source working group? Do we have a DNS working group? And do we have an IoT working group? And do we have a big data working group? And that's right, we do not have a big data working group. Doesn't make sense at the moment. But if you do think that this should be there, you can start it. Joe 10 taking the lead, Lala coming second, WT15, Mass 317, and BOFH coming in quick. Question number 8. Which of these came first?
Whatever.
Yeah, the first working World Wide Web browser, RIPE 1, Voyager 2 closest to Neptune, or the fall of the Berlin Wall. One of these 4 events happened in 1989, and it came first. So if you know your history, you should know this one. And if you don't, you'll be surprised. The right answer is RIPE 1 took place before any of these other historical things happened, and nobody was actually aware that something fantastic was happening. So scoreboard says Joe 10 still at the front, WT15, Mass 317, Al, and Sebastian coming into the scoreboard. Question number 9. Does RIPE have a secret working group? Now, the quizmaster has to die, which means me, so I hope this question doesn't bring me in trouble. And what is a working group? If it's a secret, we would never tell, and there are no secrets. There is no such working group. Does RIPE have a secret working group? And the right answer is, if it's a secret, we would never tell because we value our life so much. Scoreboard says WT15 taking the lead, Maz 317, Lala, Sebastian, and Joe 10. On to question number 10.
Why not?
Yeah, why not? Where can you find the RIPE NCC support desk? Is it at the coffee break area? Is it nowhere because it's in your imagination? Is it on Facebook or is it on WhatsApp? So if you need the RIPE NCC support desk during the RIPE meeting, where can you find them? Suspense. If anybody answers nowhere, oh no, that hurt. Of course, you can find the RIPE NCC support desk at the coffee break area. Go out there, talk to them. They are the most friendly people around. Maz 317 taking the lead, WT15, Sebastian, Joe 10, and DG 312. This is getting very exciting. Question number 11. Which organization was the first regional internet registry? First regional internet registry, RIPE NCC, ICANN, Internet, or AREN. So when we talk about regional internet registry, which one of these came first? RIPE NCC, ICANN, Internet, or AREN? And the right answer is the RIPE NCC. The RIPE NCC was the first RAR, and later came the rest. Internet was not an RAR, and ICANN is not an RAR. The only other one is AREN. So scoreboard says Maz 317, WT15, Sebastian, Joe 10, and DG 312. It didn't change much. Last question. What does NCC stand for?
Good luck.
Good luck figuring that out. Is it the Nerds Computer Club? Is it the Network Coordination Center? Is it the Nordic Construction Company? Or is it the Networked Carbon Copy? So many choices. Which one is the right one? So, Nerds Computer Club, Nordic Construction Company, Network Carbon Copy, or the right one, which is, of course, the Network Coordination Center. That's what NCC stands for. So, let's see what the top three are. Number 3, we have WT15. Number 2, we have Sebastian. And number 1, Maz 317. Congratulations, all of you. Now, thank you everybody for playing. We hope you had fun and learned something new. Enjoy RIPE 88, and remember, a day where you did not learn something is a day that was lost.
Well, thank you. Thanks, Gerardo, and thank you all for playing. That was fun. We'll hope the rest of the meeting will also bring a little bit of fun, at least, amongst all the serious discussions we're going to have. So thank you all for participating. I hope you have a bit of a better idea on how to get through the week and make the best out of it. We'll have lunch prepared. We're a little early. We have lunch prepared, and in the lunchrooms are downstairs. And there's no special table room for newcomers lunch. It says on the meeting plan newcomers lunch, but it's basically with everyone else in the same room. But there are special cards on the table if you want to sit at the newcomers table and get to know each other a bit more. But it's of course not a requirement. You can also sit with others. So I hope you'll make a lot of useful contacts during the week, and don't hesitate to speak to any of us that you've seen here on stage. So have a great week. Hope to meet many of you in person here during the week.
For the miners. Thank you. For the miners. Go down to joke.
I think. 2014 for you? It's been 10 years. Yeah, yeah. 2010. Yeah. Yeah.
Hello, how are you? Hello. Good. Down. How do I? Okay. Max. The one you like. Hello. Long time no see. Yes. I'm. I think there was some variation. Like it. Ciao. Ciao. I usually do the opening. Rollata. It's my fault. I love being fault. I love being guilty.
Did you notice because it was pointing on your screen like what happened?
No, no. Well, this is placed in the strategic position to kick.
Yeah. Yeah.
And on the other side, there's no. Max, read this. There is no limit. Exactly.
No, I assume the camera probably has, because of the cabling, maybe that's
I was in feedback from others.
you're going to be after me.
Yes.
Do I need, oh, is that already?
No. Yes. Matthew Kirkland. Would you come over? Oh, there you go. Okay. Sorry, you.
Good to see you. How are you doing? Yeah, on Thursday morning. Yeah, yeah. Oh, great. Okay, great. Oh, yeah, great. Okay, excellent. Thank you. Yeah, yes, yes. Just so I can settle myself a bit. Yeah, exactly. Yeah, that's good. Will there be time on Thursday morning before the meeting, or is it better to do it? Yeah. Okay, great. All right. Yeah, yeah. Okay, so I'll make it there in plenty of time. And yeah, maybe later this afternoon if there's a break, then I can try it out. Whenever I'll keep an eye out for this. Because it is better to. Yeah. Log in. Which one do you want?
Welcome, everybody. I see people still coming in. Find a seat. There's still enough space to sit. It's a big room. Welcome to RIPE 88. We're actually here for the second time in Poland. We were here in exactly 10 years ago, I think, for RIPE 68 in Warsaw. Well, not in Krakow, but we were in Poland, in Warsaw. So I'm happy to be back in Poland. My name is Miriam Kühne. I am the RIPE chair. And we also have Neil O'Reilly, the vice chair, in the room. I don't know where he is. He might still be talking to people outside. Yeah, you'll find us later. So, well, welcome everyone to this meeting here. Looks like we're going to have great weather. I heard there was a storm warning, but apparently it's passing, under us. So we're not going to be bothered by that. We'll have here a number of some statistics already. We had roughly 600 people who registered for the meeting from 49 countries, and 100 people, 100 newcomers are on site. And we also had, I think, roughly 300 people online. So we're still going to update the statistics during the week, obviously, and then at the end of the week, we'll have some more data. But I'm very pleased to see so many of you come to RIPE 88, and I also saw quite a number of registration from Poland, which is great, which is of course one reason why we're coming and to a country and why we're trying to move around the region also to allow people to participate that maybe otherwise wouldn't participate. I'm also pleased to see that we have local hubs again. That was an experiment that we did last time, or like a pilot, not an experiment. So we're continuing to do this. So this time we have 4 local hubs, which basically means that people got together in one location and have a little kind of mini RIPE meeting, if you will, and have the community feel and following the meeting remotely together, rather than just sitting at home kind of behind their screen. And I hope you'll hear more from them during the week. They might not all be there all the time, but you might see them online. Unfortunately, I also have to say again, there's a lot of conflicts and even wars going on in our service region, our region here. And I'm afraid this will undoubtedly have an impact on our communications in our community, our emotions. Just a reminder, treat yourself professionally and with respect, and be gentle to each other. And obviously we have a code of conduct that in a very nutshell, in a very small, basically says, please treat each other with respect and tolerance. We want to have everybody here feel safe and feel included, and we don't accept any harassment, violence, intimidation. So there's a longer code of conduct that you should all have signed up to or tick the box and read when you've registered. Should you experience any anything you don't like, any bad behavior or something you think is violating the code of conduct or you just feel uncomfortable with, we have a professional team of professional code of conduct team in place for the RIPE community. And not all of them are here this week in person, but they're obviously communicate with each other. And there are posters out in the halls, so you can find them, and there's information. You can also obviously contact them online. There's information on the RIPE 88 website and how to contact them. And they can also set up some secure communication channels with you if you need that. This is the page of all the faces of all the wonderful working group chairs that we have in place that are responsible for a bit more than half of this week. Actually, all the working groups, they have put together great agendas, and I'm looking forward to some interesting discussions there. I think most of them will be here this week on site in person, yeah, I'm looking forward to their sessions. We also have the RIPE Program Committee, and they are mostly responsible for the plenary sessions that will take place today and tomorrow, and then a bit on Friday as well. Just to quickly go over some of the sessions here on the meeting plan. This is the meeting plan you'll see online. As I said, today and tomorrow, they are mostly plenary sessions. And then there's tomorrow afternoon, there's already 2 working groups, and then Wednesday, Thursday working groups. And then Friday, a more plenary session and the closing plenary. We also have 2 BOF sessions, one today and one tomorrow. All the information is accessible through the meeting plan. So if you click through there, you'll find a lot more details also about these BOFs and about all the other sessions for the week. On Thursday, we have our traditional, I want to say, diversity and inclusion session again. After the community session, community plenary. Oh yeah, there's also a community plenary on Thursday. I didn't point that out, but you'll see that on the meeting plan. And I'll get back to that in a bit. So this diversity and inclusion session is it's different every time. Sometimes we have lightning talks, we have presentations, but we also had some great discussions. So please come and participate and help us to make this meeting more, or this community, even more diverse and inclusive over time. So maybe quickly going back to the meeting plan. There are some interesting discussions going on during the week. I mean, if you look at the plenary and also the working group sessions, obviously there are topics related to routing. There are some presentations on IPv4, the end of IPv4, deployment of v6. There are some policy discussions also related to IPv6 policies. There are some best current practices being prepared, and some of the working groups are being worked on, which I think it's really good development that we see more best current practices, because that's of course one of the product this community can produce and can be used, have some useful output. There's some research, and on some other topics you will find on the agenda. So one topic that might pop up throughout the week is the relationship between the RIPE community and the RIPE NCC and RIPE NCC services. RIPE NCC membership structure, and how the services are funded and so forth. And it might pop up in various places. So one of the BOFs tomorrow is related to that. The second one here on Tuesday, building a stable future for the RIPE NCC. Then there's of course the membership, the general meeting here on Wednesday, that little green square, where this topic will be discussed. And then we also have some time in the community plenary to maybe go over some of the details on what we can do as a community, as a RIPE community. Because even if you're not a member of the RIPE NCC, I mean, we all as a community benefit greatly from the services that the RIPE NCC provides to us as a community here. I mean, they organize these meetings. We wouldn't have these meetings without the RIPE NCC organizing them and sponsoring them also for a great part. And they also provide a lot of services to the wider community. And in fact, we have actually created the RIPE NCC some exactly 35 years. Well, no, that's not true. 35 years ago, the RIPE community has started. In fact, Wednesday this week, 35 years ago, RIPE 1 took place. So we have 35th anniversary this year. We might have some cake later in the week, who knows? But one of the things the RIPE community did quite early on is to create the RIPE NCC as its secretariat, to provide some secretariat service, like organizing these meetings, for instance. And then later on, it became also the regional internet registry. And many of you know this, but I think over the years, maybe we became a little bit complacent and kind of took it for granted. The NCC provides all these great services that we all benefit from. And I think we as a community have to also think about how we appreciate that and support the RIPE NCC and support each other, because obviously there's mutual support and dependence between us and the RIPE NCC. But before we just dive into some of those, serious discussions about routing and membership structures and IPv4 run out, and I want to remind us all, maybe especially in this birthday event of this birthday edition of the RIPE community, to also maybe stand still from time to time and think about all the great achievements that we have accomplished throughout the years. I mean, look, we have these 2 meetings a year, at the beginning 3, now 2 meetings a year, where we all come together. It's open to anybody who has an interest in networking, internet infrastructure. And we have a common goal that we work on together and have some technical coordination that's necessary to keep the internet running. And then, of course, obviously, we also have the community in order to build trust and social contacts and get to know each other. And that's, of course, also important so that we can rely on each other in case of crises, like, for instance, the pandemic, or projects like Keep Ukraine Connected. That could not take place or could not happen if we wouldn't have contacts with each other and people could just call and say, do you have some equipment or some, and help us out. So that's one important aspect, of course, to also the social aspect of this community. But I want us to be kind of proud also of what we've achieved and not kind of, the world around us is becoming more complex and hostile and polarized. And I think we might sometimes forget to also be positive and be proud. And we have built this stable and vibrant community. People look at us actually with envy sometimes for the self-governance that we have set up over the years, and also the tremendous source of resources that we combine and that we can also make available to others who are maybe joining the internet today. So while we further evolve and have these discussions, and also during the week, obviously, let's continue our constructive discussions and our traditions of consensus building and finding the best solution for problems that arise. And then, of course, also amongst all this, don't forget to have some fun. Fun is important, and we actually have social events scheduled for this to facilitate the fun. But obviously, you can also have fun without social events and can just with each other hang out, have fun. Actually, I had a great fun already today. We had the newcomers tutorial. It's always good to see new people come in. But just as a summary, so there's a welcoming reception today, and then there's networking event tomorrow afternoon, tomorrow evening. Great party tomorrow evening. And on Thursday, we have the Vibe dinner. And then last but not least, I want to actually thank all the sponsors that helped us out here. And that's Akamai is the host. And right after me, you will actually hear Patrick Busman, the representative of the local host, say a few words. And the Vibe NCC is the diamond sponsor again, and we have AWS as platinum sponsor. We have a number of silver sponsors, VeriSign, IPv4 Global by Hilco, and IPXO. And then Internet Society, Xenia, and Branac as bronze sponsor. And we also have SNet as connectivity sponsor. And last but not least, I'm pleased to see PL NOC as our community sponsor here, obviously, because we are in Poland. It's the Polish Network Operators Group. So thank you all for helping us out to organize this meeting. So wait, where am I going with this? Kind of skipped over this because I think this is important to show. I want to show it again. 35 years connecting people and networks as a Vibe community, obviously. And that's it. Thank you very much. So I hope you have a great week. Where's Patrick? There you are. Do you need to go to the end so they can change the slides, maybe? I didn't ask for questions, but you can ask me anyway if you have any questions, if we have time. Nope. No.
Thank you, Miriam. Dzień dobry, welcome to Krakow. That's about as far as my Polish goes, so don't try it over the next coming weeks. Akamai is very happy to welcome you to Krakow. In case you don't know us, we're this tiny neighborhood CDN security and cloud company that has distribution halfway decently around the world. We're highly engaged in RIPE, we're highly engaged in the operator communities all around the world. And with our new investments into cloud areas, we're also giving back to the open source communities. So therefore we thought bringing RIPE to Krakow would be a very interesting adventure. We love the city and we have a good history here. So you might ask why Akamai as an American company bringing everyone to Krakow. We have about more than 12 years of history here in Krakow and more than 1,000 employees. It actually is the third biggest office that we have globally. And just in case you're interested, we have more than 60 jobs open at the moment. So, gotta do a tiny bit of promotion here so that I can claim afterwards. So 2 or 3 highlights that I wanted to spot because I think they fit very nicely and represent how we're looking towards the community as well. Akamai for the last 9 consecutive years has been called a great place to work in Poland. We're very proud on that. We're starting our 7th iteration of Female She, the leadership program for women in Akamai in Krakow and Poland. With the Akamai Technical Academy, we have 2 cooperations with the local universities where we're bringing newcomers in. We actually have a good amount of them here throughout the week. And we have opportunities for job changers where we enable people who want to join the industry to get educated, to be able to join jobs in the IT sector, regardless of whether they then join us or other companies. Obviously, we have an opinion on that. On top of that, as everyone else, or the majority of the world, we're flex and remote first these days. So that's about it. As one does, going into a conference that we host, we thought about, we haven't had stickers for a long time, so we thought we'll go in and have a fresh, exciting, happy new thing. Everyone being excited. I was sincerely happy and looking at this. And then people had opinions. So if you go back and look at the stickers throughout the week, it's like we had debates on which animal family this is closest to, and we couldn't agree on anything. It's like we have separated groups, thought about creating work streams, sub-work streams, tasks force, And at some point I was like, we actually have a group of 600 people who are highly qualified to debate a topic over a longer extended time of work and get to a solution coming to Krakow. And I have an opportunity to talk to them. So I thought, that's too good to be true not to use it. So here is your challenge from me for the week. It's like find an Akamai representative, acquire a sticker, debate amongst yourself, debate on social media, and then vote which family this one is closest to. You can see the QR code there. You can see the Slido number down there. We'll post it on social media, and you can ask every Akamai employee for the links. In case you're wondering who that is, we have a good amount of them around here. They're here to help you, give you stickers, talk to you. A good amount of them is Polish, so they can help you with restaurant ideas, recommendations for where to go in Krakow, what to avoid in Krakow, and which interesting sites and ideas to have. I can, by experience, tell you they have good ideas. And with that, thank you for being here. Thank you for giving us the opportunity to host you. Enjoy Krakow, enjoy the conference. Have a good week. Thank you.
Thanks again. Next up on stage, as you can see, Hans-Peter Hollen, the Managing Director of the RIPE NCC, give you some more information about the meeting and about the RIPE NCC.
Thank you very much, Miriam. So my name is Hans-Peter Hollen, and I'm the Managing Director of the RIPE NCC. I've been so for 4 years now, but as many of you know, I've been part of this community for a long time. So just to repeat to all of you why we're here in the first place, the RIPE community set up the RIPE NCC in 1992 because they needed somebody to organize practical things between the volunteer work in the community. It's a membership organization from 97. It's run by my staff, and I have an executive board that supervises me, and the board is elected by the members. And many of you are members, so please come to the GM and exercise your right there to vote on future board members. We provide services and we implement the policies, but we need you to be engaged and give us input in the working groups on how the services are performing and what features you would like to see in the future, and to develop policies for us. And as Miriam said, we should be proud of what we have achieved together. We have, as the RIPE NCC, supported the community for 32 out of the 35 years this community has existed. And we have done great things together. And let's continue to do great things together in the future. A number of challenges are ahead of us. We have talked about political challenges in the years past us, and we're now also facing challenges of how we're going to finance the RIPE NCC in the future. The services working group and the GM on Wednesday, this will be discussed, and there is a BOF tomorrow also to look at how to build a stable future for the RIPE NCC. Because we've done great work for 32 years, let's figure out how to do great work for the next 32 years as well. And it's not that I think that change isn't needed, but I'm very mindful that we should review what we are doing and have been doing with respect for those who are doing it, but we should also be self-critical and take input and see how can we do better together. That's really important for me. And all changes that we do, we need to be really mindful that we don't break anything that shouldn't break. We all want the internet to work, and all of us needs to work together to make sure that it continues to do so. And that's why the RIPE NCC, the Network Coordination Center, is here. Logistics. Meetecho is the main platform for remote participation, but also for on-site participation. You can log into this on-site and enter the speaker queue, or add your Q&A questions to be read out if you don't want to go to the microphone. There is a live transcript available there, so if the field on the screen here is not big enough for you, you can get it on your device in front of you to follow the transcript there. And there is also a live stream on the RIPE NCC web stream if you want to have it on your big living room TV if you're not here. And then all the sessions will be recorded and chat archives are published afterwards. In Meetecho, you can click on the audio or video queue if you want to line up to ask a question. You can type in the questions if you want that, or you can chat in the chat room. The questions in the chat room will not be read out as questions, obviously. And then again, stenography. It's a really good tool for those of us who are not native English speakers, or if we don't get all the dialects of the native English speakers. So it's one of the things that I've learned to appreciate myself over the years here. You know, maybe in the future we will have some AI robot that can translate this into all our languages as well. The bubblefish thing from Hitchhiker's Guide comes to mind, but we're not quite there yet. Your badge is important. We've gone digital or partly digital this time, so there are now QR codes on the back instead of paper that will just be wasted afterwards. Please scan your QR codes for the meeting plan or on-site information or the Wi-Fi. If you do not want your picture taken, and I see some of you have already gotten the yellow lanyard, so that's the signal to our photographer or any of us that takes pictures. Put on a yellow lanyard and our photographer will do his best to not take pictures of you, and we will also be mindful to each other on this. And here is also a picture of our photographer that is running around here so that you know who he is when he puts a big camera in front of your face. RIPE NCC at RIPE 88. So we're here as the diamond sponsor, but we're also organizing the meeting. We have a meeting organization team for all times RIPE 88 related. Please contact them and they're happy to assist you. We have a tech team that makes all these wonderful technology like the internet that we take for granted and so on to work. We have a support desk. We can do assisted registry checks if you want to have a check on your accuracy of your registry. And please speak to any of the RIPE NCC staff. We're also giving a lot of presentations here, and I've added pointers here to where you can find us. Jad has already talked about RPKI in a tutorial this morning. Tomorrow, Robert will talk about Atlas, and Maria at the same time will talk about illegal content on the internet and the RIPE NCC's role in that. Angela and Marco in address policy will talk about policies and how the RIPE registry works. Martin will talk about DNS and in particular the future of ns.ripe.net, the secondary service for enada.arpa. There will be several presentations in the services working group as usual, also on RPKI this time. And then Romain will talk about EU regulations and the status there in cooperation. And Andre will talk about how to map v4 addresses into v6 addresses in the IPv6 working group. And Vesna and Natasha are presenting in the BOF regarding the what's it called, diversity and inclusion session at Thursday. And then, of course, one of the best and most exciting presentations at all is the tech team report at the end of this session, because, you know, all the things that happened in the network or behind the scenes is always interesting to hear. If you have an interest in our website or meeting site, please talk to Philip. He would love to hear from you on thoughts on how to develop those. Evelyn is here and is doing user testing on our academy, training courses, webinars, and certified professionals. Stephen has done a lot of work together with his team on the user experience and user interface of Atlas, so he would love to hear from you through testing of the new user interface. And Michaela is also really interested to hear about you and hear from you about your use of RIPE Atlas. And that was me. Questions? Take them to my colleagues. Thank you.
Thank you. And now we start with the actual meeting. I'd like to hand over to Max Stuckey, who is the chair of the of the program committee that is responsible for the plenary program. And Max has his That's the old slide deck still. You have a new logo. Anyway, take it.
I took it from last year. And I have to be honest, everyone on the program committee looked at the slides and they didn't say anything. So we didn't catch anything as the whole program committee. So first of all, let me start with a selfie because this has become a tradition. So, come on, Jan. Come on, Jan. Yeah, we should do a couple of them and to catch everyone. Okay, now on more to more serious things. I'm the chair of the RIPE Program Committee, which is the team that decides what you will see during the next few days, or part of it actually, not all of it. So what do? We compile the program plenary, the buffs, and the tutorials. We prepare the agenda. So there is a well-oiled machine that goes on and looks at what the content is and thinks, okay, when is this best placed? We sometimes work with the submitters to adjust or improve their presentations. We've tried to do it more and more over the last couple of meetings. And then last, this is what we do with me and Jan, but you will see many of us during the week, we chair the sessions. So we make sure that the presentations are uploaded, the speakers are here, they know how to present, they know how to look at the time, and we keep track of the time and the questions. Now, who are we? There was already Miriam already presented it. I didn't have the picture from Pavel. I'm sorry about that. But it's a nice group. We've worked together in the last few months to bring you the agenda you see these days. And what did we get? You see that we got, for plenary talks, we got 31 submissions, which means about 15% of them were accepted only. But 100% of the BOFs were accepted. We had 2 submissions and 2 passed. We had a little bit less for the tutorials because only 2 were accepted out of 3 submissions, and we still have space for the lightning talks. Now, what were the main challenges and issues? Because this is where it gets funny. We had time zone problems. So for the first time, I decided to send out invitations for the calls earlier in the year so that everyone could organize to be there, and we missed it completely in the end because when I booked the meetings, DST was not was up, and so people joined at different times for the calls, but we managed to get everything done. And then the second part was scheduling. This is more serious, and we've seen this issue raising in the last few years. The sessions on Friday, we get a lot of requests from speakers not to be put there. And this creates a big issue for the program committee because we really struggle to find content for that session. So this is something that would be discussed in the, we have a lunch on Wednesday, and we will discuss it there. And yeah, and after the meeting, because we always have also a session with the RIPE NCC during the lunch, but also after that to see what issues we have and how we can fix them. Now, we still have space for lightning talks on Friday, but also maybe one for tomorrow on Tuesday. If you have an idea, talk to us, me, Jan, or the other people on the program committee, and you can still submit. Please include some slides, even if basic, and we will have a look at them. I know some of you are still waiting for an answer from us. There's a session tomorrow for which we'll send out notifications in a moment. Last but not least, we have elections coming up. My term is up, so I will run again for election, but there are 2 seats up. The other one that's ending as term is Wolfgang's. And you can nominate yourself until tomorrow, and then voting takes place from tomorrow until Thursday. And then Friday morning, we will get to know who will still be on the program committee. Now, if you want to know more, talk to us. We're always available for explaining what it means to be on the program committee. and I can give you a very basic glimpse. You have to review the talks, rate them, tell the rest of the team what you think. It's a very open group, and we only usually have 2 calls for which you need to be on there and before every meeting. So it's not too much work. It requires a bit of concentration. It requires being critical and being open to discuss with your peers. You can email us if you have any questions, and that's it. So I'm not going to steal any more time. I think I'm at the end of the presentation. So if you have any questions, we're here. But after me, I see we need a big applause for Matthew Kirkland, who was going to be the very first presenter today and is going to tell us about how Facebook removed IPv4 from part of their infrastructure. So give him a warm applause. It's not easy to be the first one.
Great, thank you. Good afternoon. My name is Matt Kirkland. I am a network engineer at Meta, and today I'm going to be talking about how we are removing IPv4, addressing from Meta's edge network infrastructure. It's actually my first time presenting at RIPE, and I thought to myself, like, surely when I was doing the submission, that surely I'll just get a nice slot on a Wednesday after the social, but it was not to be. Okay, so I'll be going through why we wanted to do this, what approach we took, and what lessons we learned along the way. Okay, so at Meta we operate 4 main network areas, starting with data center networks, which are the data halls in our large data centers. These are connected together by our core network called Express Backbone, and its primary purpose is to carry machine-to-machine traffic. We've also got a management backbone that connects all of these together for management purposes. And then finally, the edge network, which is what I'm going to be talking about today, where we have our POPs at third-party facilities like Telehouse that also contain our compute for CDN. These are then connected back to the data centers from what we call our classic backbone, which is a kind of like an ISP network. Okay, so our internal traffic, more than 99% of that is served over IPv6 already. This number on the left actually is wrong. I didn't upload the new slide, but as of today, there's 39% of our traffic is served to the public on IPv6. The rest is IPv4. So this is a simplified diagram of our edge network. Starting from the bottom, starting from the bottom with our servers, which we already moved to v6 addressing and v6 BGP. Then our top of rack switches connected to the rack aggregation layer, and a metro aggregation layer, which allows us to physically separate peering from compute in a metropolitan area. So from there, connecting to our peers over IPv4 or IPv6. So in between each of these layers, we actually have a full mesh point-to-point links dual stack and running IPv4 and IPv6 BGP sessions between those. So why would we want to do anything different? Why not just keep operating as we have before? One of the major reasons is simplification. So today we run, as I said, IPv4 and IPv6. So having 2 distinct topologies within the network is added overhead. From scale, as I said, we've got a lot of point-to-point links just within one POP. Larger POPs have many layers. And then, of course, these POPs are spread across the world, so we have quite a few of those. As we grow, we're going to start. We are running into limitations with our IPv4 space, which is limited. Okay, so we started this project actually last year by starting to test it out in our lab, just between the rack aggregation and metro aggregation layers, followed up by a small rollout, followed by production rollout. At the same time, we started last year to roll out to our top of rack switches and the rack layer. So where we are today is we finished our rolling out to all of the other layers, and we're going to start on the peering layer. So I mentioned dual stack a few times, and I'm sure everybody in this room knows what that is. Having two IP addresses on an interface, one being IPv4, one being IPv6, and then having separate BGP neighbors for each address family, carrying prefixes with the next hop in that address family. So we'll be moving to RFC 5549 or 8950. And for the rest of this talk, I'll just refer to it as 5549 because that's what I've been doing for the last 18 months. So under that, we've got a single IPv6 address on an interface and a single IPv6 BGP session carrying IPv6 prefixes and IPv4 prefixes, the IPv4 prefixes having an IPv6 next hop. So this doesn't seem that hard. We're just removing IPv4 addresses from interfaces and changing over some BGP sessions. Sounds easy, right? Nope. We ran through quite a few challenges, many of them being platform or vendor dependent. So one of the first challenges we had was actually when we were consulting with partner teams and what was going to happen with trace route, because people are used to getting an IP address associated with an interface or their trace route. So in the present, in an RFC 5549 topology, you only get a reply from the loopback address, v4 loopback address. So in parallel, we have been working with our vendors to implement RFC 8335 and 5837, 8335 being a probe utility for interfaces, and 5837 extending ICMP to include interface and next hop identification. The first technical issue we ran into actually was with ECMP. So referring back to the earlier topology diagram, having a full mesh of circuits, full mesh of BGP sessions, any one of these devices should have 4 paths to a given prefix. So what happens is, with the one of the vendors that we use, is that in the presence of v4 and v6 next hops, they don't get put into the same ECMP group, and as a result, that OS only installs the prefix with a v6 next hop. So that makes it a bit difficult to plan migration, since the first BGP session that you migrate will then start pulling all of the traffic for that device. So we had to do some BGP traffic engineering to balance the load during the migration. We actually I went to and discussed this with some of our other vendors. Sorry. And one of them does what we would expect, which is equally balances between v4 and v6 next hops. And the last vendor actually did the exact opposite of the first, where they will only install the prefix with a v4 next hop. So if you ask 3 vendors the same question, you would get 3 different answers. So when you're moving your BGP sessions over to IPv6, it's important to remember that these platforms will need to have additional configuration to allow forwarding of v4 packets out of IPv6 only interfaces. On some vendors, this is a global command, and others interface level commands. But if you miss it, it's hard to catch. You'll be silently dropping those packets. Even within some of the same vendors, there's differences in how this is implemented between platforms. So, because we want to be able to catch any issues with v6, we wanted to have per address family counters, which is supported, but differently again between each platform. So, with one of our vendors, you could get only egress on one platform, but ingress and egress on a different platform. And another vendor still would only give you IPv6 counters, and it's up to you to take the total, subtract IPv6, and hopefully that's your IPv4 traffic. Okay, so when you're moving to a single BGP session, in our case, we had different BGP policy for v4 neighbors than we did for v6 neighbors. So what you need to do is then move all of your v4 policies into the same, or policy terms into the same policy as your v6 neighbors. So as in the picture on the right, be specifically addressing IPv6 prefixes and IP prefixes for v4. One of our vendors allows distinct policy per address family on the same neighbor. So you can have an IPv6 neighbor, and when you're enabling a v4 address family, you can have its own BGP policy. Okay, so now we've migrated all of the other layers. The final layer is the peering layer, which is different because the other layers we're using just IP forwarding with BGP. And the peering layer we have, excuse me, we run an ISIS level 1 domain in single topology mode with ISIS SR segment routing. So one of the hurdles we have here is that one of our vendors is perfectly happy for you to remove the v4 addressing from a given link and not change the topology of ISIS. So leave it in single topology mode. It'll bring up an adjacency. But another vendor requires you to move to multi-topology for IPv6, which then imposes that requirement on the other vendor. So that makes migration a bit more painful as we have to change from single to multi-topology in a maintenance window. It's more impactful. So I mentioned we're using segment routing in that part of the network, and there was some concern about how this would work. Luckily for us, as expected, we get a IPv4 packet from the LER on the left, gets a label pushed onto it from SR, goes to the LSR, pop label, and because we're using implicit null, it forwards the packet to the final router. What I found out subsequently is that if we have, the LERs are one vendor and the LSR is a different vendor. So if we had the same vendor for all three, same as the LERs, on that LSR pop, before it forwards the packet, it does a header lookup and compares the address family on the outbound interface, finds out that it's not an IPv6 packet and drops it. So we got lucky there. Okay, so with once we have that done, where do we go from here? We would like to remove v4 from the link addressing within our CBB core network. Unfortunately, because we're running RSVP TE, there are no implementations of RSVP that run on IPv6 today, despite it being in the earliest of RSCs. We actually went to 4 vendors to ask who, if they would implement this, and some of them actually told us that no one had ever asked for IPv6 RSVP, which I find pretty incredible. So not all bad though. What we can do is we'll be removing the v4 BGP sessions and moving our BGP mesh to RFC 5549. So throughout this, RFC 5549 just works. We did not have any issues with interoperability or implementation for the BGP side of this mission. A lot of testing was needed to find all of the things that we've uncovered so far. So yeah, testing is very important. And lastly, is it worth it? Yes, the overhead from running 2 distinct topologies in the edge network, reducing that, and not having to plan for future IPv4 needs has been worth it. It's the end of my.
Okay, good people from the internet. Have any questions? I think Peter was first.
Peter Hessler from Zayo Europe. Several times in your presentation, you mentioned vendors did things differently from other vendors.
Yeah.
Do you think that is something that needs to be clarified in the RFCs, or do you think that is something that the vendors kind of ignored or misunderstood from the existing RFCs?
I think it's just a choice they made in the case of the vendor that installs only the v6 next hop. We had to talk with the engineering team, and it was not following an RFC or anything. They just said, well, we just thought this is the better way to do it. And so they've actually changed that in a more recent release. So that was good feedback, I guess.
Thank you.
It's Antonio, then Jen.
Hello, Antonio Prado, a random BGP guy here. So it's quite the same question, but just to understand if you did open a dialogue with vendors and if you came up with a solution.
For which part?
For your issues.
Yes. Yeah, I mean, the feedback was received differently in each case. So as I said, the next top problem that was well received, they'd agreed to fix it, and I believe it is being fixed in a recent version. Issues with things like the counters on different platforms. They explained that some of this is hardware related, so like an older chassis may not have the right resources for enabling both ingress and egress counters. So there's nothing I can do about that if it's a hardware issue. But yeah, I did take all my findings back to vendors.
Okay, I see there is Jen in the queue.
Yes, I'm in the queue. Not anymore. Okay. Thank you very much. Very interesting, very exciting. I just want to say that I feel your pain. I've been talking to vendors about getting RSVPT working over v6. So there is at least 1 or 2 vendors who have customers asking for this besides you.
Yeah.
So you are not alone
I'm sure,
in this
yeah.
fight here. Unfortunately, in most cases, what I've heard was the answer, why would you need this? Now we have SRv6, which is horrible, right?
I mean, that means I have to re-engineer CSPF. So.
Okay, I'm cutting the queue now. So the queue is closed. Tobias?
Hey, so Tobias Fiebig, Max Planck Institute for Informatics. What are your eBGP plans?
I'm sorry, I didn't catch it.
eBGP, external.
Yes. They're all dual stack. Is that the question? Sorry.
Yeah.
Yeah.
When do you make them 8950?
Oh, I was thinking about that earlier today. That's gonna be a much longer tail, as you know, involves discussing the matter with each peer.
Okay, thank you. We should maybe chat.
Yeah.
It's Dmitro, then Daniel.
Hi, Dmitro Kochmanyuk, Postmaster.va. Well, we run something like you, but of course on a much smaller scale, and we had just few experiences with, well, multi-protocol. One question, the ISIS multi-topology, was it really necessary? Because you kind of skimmed it on it. And I guess that maybe requires its own little presentation.
Yeah, I mean, that surprised me. I mean, basically, one vendor telling me that you have to change to multi-topology, and the other one saying you don't have to change because it's just a single topology. So I don't know what the answer is, the right answer, but yeah, that's just where we ended up if we wanted to interoperate between them.
Well, thanks for your effort. Thank you.
Before we go to Daniel, we have a couple of questions from the queue here on Meetecho. What from Vyacheslav Adamanov? What vendors are friendly for a mix of V4 and V6?
Oh,
It's a broad question, I know.
I don't know if I should answer that.
Yes, you should.
I don't want to be in legal trouble.
Okay, well, the next one from Nico Braud-Santoni from FF Graz. Overall, would you say the main challenge was inconsistent support across vendors or even product families for links addressed in V6 only? Did you encounter any of these issues in the free and open source software network stacks and routing daemons?
That's a great question. Well, because the network that I'm changing is all vendor hardware, I did not look into any of the open source BGP daemons. But the actual implementation of 5549 was not an issue between the vendors that I found. It was everything surrounding it, like forwarding and reporting that where there was inconsistency.
Okay, thank you. And I think we go to Daniel.
Daniel Kallenberg, old network guy. You know, in the good old days, we had bake-offs. We just put all the vendors in one room and their engineers and said, make it work.
Yeah.
I'm wondering whether people with the buying power that you have might team up with people who have similar buying power and just make them do that. And basically say, you guys are responsible for, even though you are competitors of each other, to be in one room and make this work for us.
Yeah.
Otherwise, we won't buy from you again.
Yeah, and I think that's fair. Like I say, one of our vendors did fix what we saw as an issue, and they didn't think was an issue with the ECMP groups. But when it comes to things like the V6 RSVP, which has been a problem for many, many years, and more people have asked for it, as Jen said, it's difficult to make them shift on it if the combined ask of Google and Meta is not going to work.
Yeah, my point is kind of, you know, you are doing all the work there.
Yeah.
What actually the vendors should do. So I think you should band up with people like Yen or others and basically beat them into submission. Thank you.
Thank you.
Thank you. Please.
Hi, I'm Michael Takeuchi from Indonesia. It's quite a nice presentation. Actually, I'm curious about the CDN impacts after you implement this kind of migration, like maybe some miss CDN that impacting the latency, like maybe you're located in Krakow, but you take the CDN from any other country, far away country. Is there any impact to the user experience or something?
Well, so I'll start off by saying that we broke this down into a number of phases, right? So we only worked on between 2 layers at a time. And for the first part, we didn't have to like take traffic away from the CDN cluster. For the second part, which was changing the actual top rack to rack aggregation BGP session, those we had to drain the entire cluster CDN. And from that perspective, you would see an increased latency during the maintenance window, but we have not seen any increased latency after we've shifted the traffic back. That makes sense?
Okay. Thank you.
I think we have another question.
We have a couple more questions from Meet Echo. So the first one is from Sasha Kovacevic. Does IPv6 bring new security challenges that need to be addressed, such as specific attacks on IPv6 infrastructure? That's a broad question.
I don't feel like I can accurately. I'm sure there will be. Yep. Nothing that I know of right now.
And the last one I'm going to read is from Anna Nikolic. Are you thinking about introducing segment routing v6, SRv6?
Sorry,
Are you thinking about introducing segment routing v6?
Oh, in place of RSVP.
Mm-hmm.
We've talked about it, but the challenge, as I mentioned, is that you've then got to re-engineer something to replace CSPF, which is a bigger project than this.
Okay, I have a very, very last one. This is interesting. So 99% internal and 38% public traffic on v6. Will these go to 100 and when? So you can take out your sphere and then give us some numbers.
We have internally, we have some random projects that still use v4. It's that very, very long tail of trying to find stuff to move over. As for externally, that's completely out of our control. We offer v6 to all of our peers.
Okay, thank you.
Thank you.
We're done.
Thank you very much.
Thank you.
So, Max, who is next?
Next, we have Thomas Weble from Flex Optics.
Okay, Thomas, the floor is yours.
Perfect. Hi, thank you very much. Thank you very much for the intro. My name is Thomas Weble, co-founder and CTO at Flex Optics, and I brought a topic with me where I think is going to be a game changer in optical transmission in the next couple of years. It's about coherent optical transceivers, and I separated the presentation to sections. The first one is going to be a little bit about theory, and the second one is going to be how we did a practical implementation together with DKIX in Germany on their Nokia gear. So let's first start where we are coming from and where are the limits. So when we look at the ecosystem of 100 gigabit, there are limitations, and I'm pretty sure quite a lot of you got in touch with that issues, that there are a lot of form factors around providing 100 gigabits, starting with the well-known CFP. It's a big plate, taking a lot of power, a horrible interface to implement, and it dissipates a lot of heat, which is in some circumstances quite good, which you will see later on. And there were some other form factors in that family, like CFP2 and a well-known CPAC. I feel very sorry for all of you who implemented CPAC, because it's basically not there any longer. And maybe I ask a question about CFP4. Who has ever got a CFP4 in his hand? Wow, one person. Who plugged it into a router and switch and is still operating it? It's a 100 gigabit transceiver. Sorry, forgot that one. It's fast. None. Okay, so you see there is a huge variation of transceivers for 100 gigabit, but they had limits, and especially in terms of the ratio of the power consumption to the size of the form factor. For sure, if you have a CFP, it can draw a lot of power, but it's a horrible bad form factor. Now the QSP28, for example, is a nice form factor, but on the other side, it has power limitations, and so on. And for sure, their focus when they were when the specification was made, they were mainly intent to do inner data center links, let's say up to roughly 10 or 25 kilometers, but not beyond that. And that's something which is targeted now by Coherent. So for the 100 gig world as well, when we were talking about DWDM, long distance links in metro or even long haul transmission, there were transponder cards holding a DSP, a digital signal processor made out of chip. And this chip was produced in 28 nanometer structures, for example. The card itself is quite big, and typically you had a transponder system. Now with the time and what we gathered in knowledge in terms of building small chips and small structures down to 7 nanometers chips, we are able to build a really tiny digital signal processor which does all the magic and place it on a nice form factor called the QSF PDD, and it can either power it, for sure, and also hold it just in terms of the size. And that's where we are today, doing 400 gigabit with a DSP inside of a transceiver and providing coherent technology. So where are we coming from? So let's first have a look at our basics of our 10 gigabit and past, basically. We were, and we are still doing it, I'm pretty sure, doing direct detection transceivers. That's an on-off keying mechanism, an on-off keying modulation, and it's quite straightforward. So you have a 0 and a 1, light on, light off. And what you see here is on the top one, that's basically how the transmitter transmits the signal on a time basis. That's a timing diagram. So on the top, you have the 1, and the bottom, the 0, and it's a rectangle shape. Pretty nice. On the receiver side, it's not a rectangle anymore. It's more a sinus curve or something between. Because while the signal is traversing on the line, it's going to be disrupted by effects like the length of the fiber, for example. Now, if we would just increase now the speed, which is basically increase the frequency, you will see something like this. So we densened the frequency, we get a higher frequency. The signal on the transmitting side is getting better, but on the receiver side, you see something like, oh, actually the amplitude is getting smaller, for example. So it's getting harder for the receiver to detect between a 0 and a 1, and that's what we want. We want zeros and ones. And then if we increase the frequency even more, then you can see on the right corner, the diagram, actually it's just ones, so the zeros are not detectable any longer. So we're talking about light, and light has not only one property, the amplitude, we have more parameters within light, and that's actually what coherent technology makes use of it now. So we were talking about frequency and amplitude, but we have phase and polarization. Let's start with the easy one, with the polarization. All of you, oh, I hope so, quite a lot of you use those privacy screens on your laptop so that your neighbor doesn't support your work while you're here on that conference. How does this work? It's a filter. It only allows certain directions going through that filter. In coherent technology, we do the same. We have two directions basically, and that's the DP standing for dual polarizations. We make use of two polarization directions and we filter between them. How would that look like? So we did a simulation in the company within MATLAB, and we have two planes. We have the X and the Y plane for the polarization. And what you see here at the moment, it's a 16 QAM modulated signal. I will come to the 16 QAM later on. It's the X plane of the polarization. And now when we move over to the Y plane, it's a totally different signal, but so far they look pretty much the same. And now, when we combine them, that's where the magic happens. That's actually the real signal which hits the receiver, and it's calculated by the DSP and ended up in zeros and ones at the end of the day. These are in total roughly 160 bytes we encoded there, a typical text message, and that's how it would look like, just for the polarization. Now, moving on, as I said, we have phase, we have amplitude and polarization. Now looking at the phase, for example. At the beginning, I introduced the timing diagrams with that frequency on the time. And this is also the foundation when some of you might have seen an eye diagram of a transceiver. It actually looks like an eye where you can distinguish between 0 and 1s. Now for coherent, the timing, we get rid of it first for the moment. We just want to look at constellations. You can think about stars. If you look at the sky, there are a couple of stars lighting out. And let's start with an easy example, a simple example. The constellation of an on-off keying mechanism, like what I showed at the beginning, 1 and 0. These are the two stars on the left of this constellation diagram. And you see on the x-axis, this is the in-phase component. So on-off keying mechanism is all in phase. There is no phase shift. Now with 100 gigabit and beyond, PAM4 was introduced. It's a 4-level pulse amplitude modulation. It's all modulated on the amplitude, but we are still in the phase. But we have now 4 stages or 4 symbols, and each symbol is carrying 2 bits. So we can increase at least now, or double the bandwidth, just we can encode now 2 bits. And as you can imagine, as it is a diagram, and we have 16 squares now there, with 16 QAM, which is 16 quadrature amplitude modulation, we have a 4x4 matrix now, making use of complex numbers. And complex numbers in mathematics typically belongs out of the real part, which is the x-axis, and the imaginary part, which we see here on the y-axis. Combining them together, we have 4x4 constellation points, ends up in 16 different constellation points, which are distributed all of this diagram. And the biggest challenge there is, it is the, no, is there a pointer? No. In the middle, the center is quite important because the DSP, what it does, from the center of the diagram, where the zeros meet each other in the middle of the diagram, it does calculate a vector to each constellation point. And the vector consists of an angle and a distance. And with that, you can differentiate between all those 16 points and get a signal out of it. So we can now encode, as you can see, 4 bits for each symbol. And that's compared to the on-off keying mechanism where we were only able to encode 1 bit, quadrupled basically. So we have 4 times more bits within the same frequency. A real-world example, some of you might know that, is an optical rotary encoder. Don't get confused. This is not part of an optical transceiver. Would be funny though.
Would be cool.
It is. It's used in servo motors, for example. So you have a photodiode typically, and which detects the slices of the slice disk, and then you can, depending on the speed, how fast this disk is rotating, you can detect a signal. Now, when you place a second diode with a certain distance, you get a phase shift. And when the distance is correlated to the speed, you have, for example, 90 degrees of phase shift. And you detect always at the same time. That's the most important thing. You detect always at the same time. And then it will look like this, and that's how you get your phase shift. So when the real part is at a 0, it is still at a 0 and it's going up to a 1. The imaginary part is at the beginning of a 0, and so we encoded two phases actually. Moving on, within coherent technology, one measurement is becoming very, very important now. It is the signal-to-noise ratio. Signal-to-noise ratio is something quite simple to explain. You get the noise level of a signal, like here in the audience, it's very quiet, and talking me as the desired signal to you, and the same applies to a transceiver. So there's a desired signal in the ratio to the noise level on the line. So, and we need that measurement. It is important to have that measurement. It's measured in deep decibel, and like this one is on 25 dB. This is still capable, the receiver is still capable to detect a signal there. How would that look like? And we compared different signal-to-noise ratio levels. Like on the left side, you see the 30 dB, and that's actually comparable like talking here to that audience. It's a really good signal-to-noise ratio, which is clear. You see the constellation points. The receiver can really easily detect them. Now, getting, if you guys would cheer now a little bit more, to 20 dB, it's still doable to hear me because the audio is quite good. But doing the same talk in a football stadium, this would end up in a signal-to-noise ratio of 5 dB. The constellation points are distributed all around, and it's really hard for the receiver to calculate the vectors to which section actually does my desired signal belongs to. So in other words, on the right side, you have a lot of bit errors, you have flapping links, and it won't work at all. In the middle one, it's still somehow doable, but you have a lot of bit errors on your line. And depending how picky you are, you might have flapping links. And on the left side, this is a perfect link. That's the theory part. Now coming to the practical one, and to show you why this theory is so important now in these days when you look at your operating system of your switch or router to understand, hey, why is my link making trouble? I have perfect power levels, light levels, but it's not working at all. So what we did, we were just running one command. So first of all, we were plugging in the transceiver in a Nokia gear, QSFP-DD based, enabled the port, configured it, and then we run a show port command and looked how Nokia did this, and we ended up with 3 different sections returning us, or maybe we can do some analysis on it. And yeah, for the setup, it was a 15-kilometer span where we did the testing, and these are the metrics and the measurements we did so far. So on the first page, this is roughly the physics about this transceiver, the specs. So it's a fully tunable transceiver from the starting frequency of, I don't read the entire number because it's very long, megahertz, which is not very common. Typically, we say it's terahertz. So it's 191.3 terahertz, going up to a max frequency of 196.1 terahertz, or even easier, channel 13 to channel 61. That's where we can tune that transceiver. It is currently tuned to channel 23, and it does support a couple of grids, well-known 100 gigahertz, but we can also slice it down to a 50 gigahertz grid. That's all done by the DSP. That's pretty amazing. Moving on, diagnostic monitoring. I'm pretty sure everyone is familiar now with diagnostic monitoring, looking at the temperature, the voltage, peaks and power levels. And I highlighted the temperature because for coherent modules, the temperature is becoming crucial and critical. And when you look at the implementation of your switch and router gear, you will find out there will be some high power ports which provide enough power to that port. But the more challenging part is getting rid of the power, because all the power we feed into an optical transceiver, and especially when we are talking about optical communication, only 0.001 watt, which is roughly 0 dBm TX power, is converted into light. And the rest, what we feed in there of those 17 or 18 watts of power for one transceiver is heat dissipation, and we need to get rid of that one. I will come to the heat later on again, and let's move on with the coherent parameters. And I highlighted, in my opinion, the most important one, which you should know when you operate your link. So these are coherent specific parameters, and let's start with the RX channel. As I said at the beginning, it is, or when I introduced the characteristics of the transceiver, it's a fully tunable. And typically, when you talk about tunable transceivers, you think about the transmitter. You tune the transmitter. Now for coherent, this is still doable. I didn't highlight this one. You do the TX frequency as well, but you can also configure the receive frequency. And that's really, really important. Depending on the hardware you're using, there is a local oscillator inside which locks to the frequency, and you need to do this also for the receiver. If your transceiver has 2 local oscillators, there were some CFP2 modules out there which have that. And the great thing is, if you're having this, you can do a single strand transmission. Means the TX is, for example, on channel 23 and RX is on channel 25. You can transmit on one single fiber. For the QSFP-DDs, we see in the market at the moment, there's only one local oscillator inside. You use an optical splitter, and he's feeding the TX and the RX. So you can't change the RX frequency there, or it needs to be the same like the TX one. Dispersion. As I mentioned, the DSP is quite capable and powerful. Dispersion is a critical measurement, and we have 2 types of dispersion in an optical transmission system. In the past, until 100 gig, without DSP, you needed to compensate dispersion. What is dispersion? It is the change of the signal while it's traversing on your fiber, and typically it's dense, basically. So you start your signal itself on a timing diagram, and then while it's traversing to the receiver, you will dense it and dense it. And then there is a certain thresholds you can't distinguish again between 0 and 1. With the DSP inside, we can compensate this up to 2000 picoseconds, which is quite powerful. And on the bottom, you see also the actual measurements. So we can measure how many meter per kilometer. You can do the reverse mathematics and calculate the length of your span. So this would end up in 22 kilometers if we do the reverse mathematics. Our one was 15. We couldn't find out where is this offset coming from, this offset of 17 picoseconds. We made a proof. We used a back-to-back link with 2 meters of jumper cable, and here we are. There we had the 70 picoseconds. They appeared. There are some ideas that it might come up from the plugs, but I'm not convinced that where is this dispersion coming from. Moving on, and as I said at the beginning, we have polarization now. We also need to take care about the dispersion which can happen on the polarization direction. So, and this is called either the polarization mode dispersion, and the measurement is the different group delay. Here we had 2 picoseconds of the delay, so that's the difference of our y-axis and the x-axis, the direction basically, how they differ with each other. And again, the DSP can compensate it up to 10 picoseconds, or depending on which standard or specification we are following, up to 20 picoseconds. And finally, OSNR, the signal to noise ratio. We do have now for both polarizations, we do have an OSNR measure or an SNR measurement. This link was running perfectly fine with 34 dB. And there is the forward error correction, this prefab value bit error rate. And this is important because every DSP inside also does a forward error correction, and it's required to have the forward error correction. Otherwise, you will end up with flapping links. And the RxQ margin is correlated to the forward error correction. And some vendors also call it the Q factor. It is actually the gap, how capable the FEC is to correct errors. So when this margin is even up down to 0 dB, the FEC is not capable any longer to correct errors. A back-to-back link had roughly 4 dB of margin left for the forward error correction to properly work. And finally, you might have heard about the term OpenZR Plus, or those specifications, OIF. Each transceiver, each coherent one can follow certain specifications. But the interesting one is we configured it. This is the config section in Nokia Gear to the OpenZR Plus with the OFAC 1. But actually, the transceiver itself was not capable to follow that specification. Looking at the first section, this transceiver was only capable to follow the OIF specification, which is a different one, which I show on the next slide. And so you need to be really aware of what you configure and what is your hardware capable to do. There are simple no checks, at least when we did this last year in October. Maybe it has changed, but so far I haven't seen any improvement there. Having said that, and mentioned already the OIF 400ZR, which is a little bit the older specification, and later on in the industry and in the community well-known OpenZR Plus, these are the two different main specifications today. They don't differ that much in the TX and RX power, as you can see, but they differ pretty much in the chromatic dispersion, or it's all about dispersion, and the OSNR tolerance. And especially the OpenZR Plus, I would say it's the latest one, is more sensitive, is less sensitive on the chromatic dispersion. You can build at the end of the day longer spans. OpenZR Plus does differentiate between a couple of substandards, but they have two to point out. It's a 60LA. The L is a low power edition, let's call it this way, with a TX power of minus 10 dBm. And the current one, which everyone is looking and aiming, is the 60H, the high power solution, doing 0 dBm of TX power and give you roughly, depending on your OSNR and your requirements on the speed, of 12 dB or much or more power budget. Brings me almost to the end of my presentation, a little bit of an outlook. And as I said at the beginning, this coherent technology is a game changer in optical transmission. I showed up just with raw compute power inside of a transceiver, we can now, let's say, quadruple the speed of what we do to transmit data. And here is a little bit an outlook where we're going to. It's you see the green circle is a PAM4 modulated signal, and when you quadruple it up to the 8x1, that's a dual polarized 16 QAM signal. And just with the DSP, we did it 4 times more, and we can end up and build a 1.6 terabit transceiver there. The current implementations we see so far is the red line actually for the 800 gigabit solutions. It will be PAM4 still, but also with a higher baud rate and a higher frequency on the electrical and optical side. So we are running there now 8 times 100 gigabit. It's PAM4 modulated, so this is roughly a 50 gigabaud signal on the electrical side. And last but not least, thanks a lot for listening and watching. And from our side, it's very interesting to see how other manufacturers and vendors. So we did now a test with Nokia. I got some feedback from customers running it on Arista and Juniper now. I had a really interesting look on Cisco in our NX OS, very interesting. We even claimed the bug report, and it's still ongoing. If you have other gear which implement the coherent parameters, talk to me. I'm really interested to have a look at it and also support you with some testing gear. Thank you very much.
So there's no people running to the mics. There is a question in the queue from Nico Brown Santoni. Are all coherent optics agile in terms of color wavelength? Do they require optical filters for WDM, or can they handle incoming signals containing other carriers?
Okay. There are different solutions out there. There's things like the colorless solutions, but for the moment, where people aim to build it, it's requiring a filter and typically a flat top filter to get through the 100 gigahertz. Thank you for the question.
Yep, we have people at the mic. So.
Blake with Zeo Europe. Thank you very much for doing this. This has been my life for the last 3 months, so very much appreciated. Have you seen much progress on the front of having like an optical vendor be able to actually get data out of a router in monitoring this, so that like you can, present to your kind friends in your optical team the data from your router in a way that they can see it and manage it in their Shiny managing and monitoring system?
That's a really good question. And thank you for raising that one. What I showed today is really like the tip of the iceberg, what is a coherent module is capable to do. It's really the tip. It helps 99% of the engineers here to troubleshoot their links, but a coherent module itself or the coherent technology itself is way more capable. And there are way more parameters to show and to represent it. And I think that's the big challenge. The DSP can do it, but the software isn't ready yet. That's what I see. I think we will see in the next couple of years more and more emerging, and it won't end up with only 3 pages of configuration. You will end up with, let's say, 4, 5, 6 pages then. But for the moment, I think it's covering a lot of cases.
Thank you. Second quick one. Do you have many customers using the standard bog standard OIF 400 ZR in unamplified mode?
Yes.
Cool. Thank you.
Hello, David Adlizo from Ionos SE. So we've been running coherent optical transmission for about 5 years now, and I was just wondering if you have any plans on expanding your portfolio to CFP transceivers. We're running lots of OTU with on Orion shelves with CFP transceivers, and getting Flex Optics as a vendor would be really nice. Do you see any future in this standard, or?
Honest answer is, I personally don't like the CFP. I looked into the specification at the beginning when it came up 8 years ago, and it's a nightmare. It is over-engineered, to be honest. This is 300 pages plus. It is capable to handle a lot, but it's way too much. In my but that's my Thomas personal opinion, because I had to go through those pages and it was not a lot of fun. So the answer is I have some influence in the company. Sorry. Most probably no.
All right. Thank you.
Will from CITES. Thank you, Thomas, for the really insightful talk. I was wondering, my problem as a guy who recovers a lot of second-hand hardware and so on, I also recover crappy fibers and so on. That will be a problem for me, I suspect, having totally fresh monomod fiber that came from you know where or wherever, because obviously the signal will be really affected if I try to do coherent on that. What's your thought about that? Will I need to measure that with a special OTDR or something to be sure that I can actually go and do anything on this fiber?
Okay.
Maybe we can take that after on.
Typically, I would, but you were talking about single mode fiber now.
Yeah.
Yeah. Typically, for sure, you get a measurement from the guy who brings out the fiber. You get a proper OTDR measurement in at least two frequency or two wavelength, hopefully. This should do quite a lot of it.
Yeah.
Yeah.
Okay. Thank you.
Welcome.
Okay. I don't see anyone queuing anymore. So thank you, Thomas.
Thank you for having me.
So this concludes our first session, and we are like a few seconds, no, 15:30 right now. Perfect timing. One request from the PCs, please rate the talks. Let us know if you liked them or if you didn't like them. And then we see you again in half an hour. Enjoy the break.
Good afternoon. If you could all take your seats, please. We will kick off with the second plenary session. So my name is Brian Nisbet, and along with Clara Wade, we'll be chairing this plenary session, and we've got some really cool talks for you all. So if you could please take seats or your conversations outside, that is your binary choice. So first up, we have Kamal Sancha from 1,000 Eyes talking about the surprising effect of 1% packet loss. Thank you very much.
Hello, everyone. My name is Kamal Shanta, and I'm a principal internet analyst at Cisco 1,000 Eyes. It's awesome to be back at Tripe. It's been a few years since I was there last time, and every single time it's much better and better. So today I'm going to speak about the surprising impact of 1% packet loss, which is the research that we did, which we thought that might be interesting for specifically this audience. So TCP has been with us for a couple of decades at this stage, and its intricacies are very well researched. As part of that, we know how it works, we know what the problems are, we know some of the solutions and stuff. In fact, it's so very well researched that today, if you are going for network engineering integrating loop, it's very likely that one of the loops is going to be dedicated to TCP. So now, as part of all of that experience that we have with the protocol itself and its research, we realized that packet loss has negative effects on flows. And at Cisco 1,000 Eyes, we often publish various outage analysis, as part of which, more often than not, spike in packet loss closely correlates with drop in application performance. It's pretty obvious. However, even with all of that research and experience that we gained over the years, impact of the packet loss is not something that we often quantify. So in fact, it's like really hard to quantify the impact of packet loss. And within the network engineering community at large, we tend to look past the small amounts of packet loss, let's say 1% or 2%, especially if it's something that just spikes and goes away, like temporary spikes, right? Now, if countless TCP dumps and Wireshark sessions taught us anything, it's that TCP has multiple different ways that it uses to handle packet loss, as part of which we are speaking about the duplicate acknowledgements, timeouts, explicit congestion notifications or ECNs, selective acknowledgements, but pretty large part of that has been dealt by congestion avoidance algorithms. And those are going to be one of the main topics today. So when it comes to that, given increased popularity of the internet and rapid Ethernet speeds growth that we observed over the last few decades, network engineers observed that earlier congestion avoidance algorithms such as Tahoe and Renault are quite slow at utilizing available bandwidth, especially in the higher bandwidth networks, right? And something needed to be done about it, and Cubic was invented effectively. And Cubic at this time and age represents the default congestion avoidance algorithm on pretty much every single major operating system, be it the Linux, Windows, BSD, macOS, and so on. So how it works. There are a couple of different aspects when it comes to congestion avoidance algorithm that we need to take into consideration. And the first one is congestion windows adjustment. Cubic employs the cubic function, which researchers found that it has like really nice characteristics when it comes to that, to adjust the congestion window size. And initially, the congestion windows is increased aggressively during the slow start phase, which is pretty ironic if you think about it. It's called slow start, but we are aggressively growing. It's kind of does not go hand in hand, but that's what we call it. And then it goes cautiously during the congestion avoidance. It reduces the congestion window sharply upon the detection of the packet loss. And it's quite, when I say sharply reduces congestion windows, that's probably an understatement, as we're going to see it a little bit later on. One of the functions is also window scaling. So it adjusts the congestion window size based on the current network conditions. It utilizes TCP timestamp for fine grained measurements on round trip time, which helps it estimate the available bandwidth and adjustment of the congestion windows accordingly. The main function is obviously congestion avoidance, hence congestion avoidance algorithms. When Cubic switches to congestion avoidance, once it switches congestion avoidance mode, it increases congestion windows slowly and gradually, probing for the additional bandwidth, trying to avoid undue congestion, right? And once packet loss happens, it reduces the congestion window sharply, and it implements this additive increase multiplicative decrease method to adjust it dynamically. Now, what did we test as part of our research? Well, we were interested in real-life scenarios, and unlike bandwidth, which represents the maximum capacity of the channel, the throughput reflects the real-world performance and efficiency of the data transmission process, and that's what we were interested in measuring. Therefore, we measured throughput. For this particular research, we took 5 different Linux hosts. We deployed Ubuntu 22.04 on each of them, and using system control, we configured them for packet forwarding. Each of these hosts had 1 gigabit network interface card, and we tested throughput in 2 different topologies, and we're going to show which were those. Given the fact that devices had single network interface, we needed to utilize the concept of sub-interfaces to achieve what we wanted to achieve, which meant that some additional configuration on the switch itself was required in a form of VLANs, and for this particular purpose, we utilized Cisco 3750. And then we measured the throughput using iPerf3 in following topologies. So we had symmetric and asymmetric network topology, as part of which symmetric one was as part of which forwarding path is exactly the same to the reverse path. Why did we test in this topology? Well, enterprise networks today very often implement symmetric topologies, and they are doing that for the simple reasons of ease of troubleshooting, because if there's a problem on the forwarding path, it's going to affect the return path on the exactly same point. And the other thing is that implementing security features such as firewalls and IDPs and stuff like that is significantly easier in the symmetric topologies. However, we also wanted to test stuff in the asymmetric topology, so we had this topology down below, as part of which return path is completely different to forwarding path, and for this particular purposes, we utilize that concept of sub-interfaces and VLANs on that particular switch. Now, this closely reassembles the majority of the flows on the open internet. So the first thing that we did is we measured the throughput in those 2 topologies without any packet loss. So we wanted to establish a baseline, and as part of that, in symmetric topology, we achieved 804.67 megabits per second, and in asymmetric topology, we achieved 864.13 megabits per second. So it's reasonable enough. Those were 1 gigabit interfaces, so that pretty much worked as expected. So given the fact that we utilize Linux, we used TC, or traffic control utility, on Linux boxes. And TC has capabilities such as shaping, scheduling, policing, and dropping. But it also has this really neat enhancement called NetM, which stands for network emulation, which allows you to introduce the packet loss, duplication, delay, and stuff like that on the interface, on the packets leaving a specific egress interface. And that's exactly what we did. So the first thing that we did was to introduce 1% packet loss. And on this particular plot, what we are looking at with the orange line is the baseline throughput that we achieve, which is 806 megabits per second in symmetric topology. And as indicated by the blue line, we can see that we were getting 235.5 megabits of throughput at 1% packet loss. So on average, 1% of packet loss causes 70+% of decrease in throughput, which is pretty remarkable regardless of topology that you are testing. It's kind of mind-boggling. So more specifically, what we achieved is 235.51 megabits per second in symmetric topology and 222.49 megabits per second in asymmetric topology, which gives that 1% of packet loss cause 70.7% a decrease in throughput in symmetric network topology, while in asymmetric topology it resulted in 74.2 decrease in throughput, which is pretty remarkable. We tested up to 10%, and as visible here, at compounding negative effect of packet loss actually in cubic enabled topologies happens really early on, as part of which we see that even at 1% we were down 70+% in throughput, which is really remarkable. This slide shows two different plots, as part of which we are visualizing achieved throughput in these two topologies at various levels of packet loss. And here, as visible, most notable thing is actually this white space in between the orange line and pretty much everything else at the bottom. So the next thing that we asked ourselves is whether there's anything else that we can use. And fortunately enough, there's BBR. BBR stands for bottleneck bandwidth and round trip time. Is the congestion avoidance algorithm developed by Google, and it's designed to optimize network utilization and throughput by continuously probing for available bandwidth. Now, if you think about it, over the last 10 years, there was this pretty large trend at hyperscalers such as Google to go towards the white boxes, so to move from the vendor equipment towards the white boxes. So it does not surprise that actually this came out of Google, given the fact that white boxes usually have higher bandwidth interfaces, such as 100G interfaces and stuff like that. However, they have the shallow queues, which represents some of the challenges. So how BBR works? There are a couple of different things that it does. Most importantly, it's estimating the bandwidth by measuring delivery rate of packets. And it uses the concept of pacing to ensure steady flow of packet without causing undue congestion. Probably the most important functionality of the algorithm is round trip estimation, because it maintains the estimate of minimum RTT of connection. And this is important from the fact that BBR utilizes RTT as a sign that queue is getting filled. And whenever that happens, essentially the algorithm itself scales back when it comes to sending rate and drops, which maximizes the amount of throughput that can be achieved through that particular channel. And when it comes to bottleneck detection, it identifies the bottleneck link in the network path through various techniques, such as probing for increased delivery rate and utilizing RTT feedback, just what I said. Obviously, as any congestion avoidance algorithm, it adjusts the sending rate by maintaining two parameters, spacing gain and probing gain, and it actually prefers the low latency operation over pretty much everything else. Now, when it comes to differences between cubic and BBR, we categorize it in a few different areas. The first one is congestion windows adjustment. So cubic adjusts congestion window based on the cubic function, as we said, and it reacts pretty sharply at detection of the packet loss. When I said pretty sharply, it literally cuts down the congestion window size by 1/3 whenever it detects the packet loss. BBR, on the other hand, dynamically adjusts sending rate based on the bandwidth in RTT estimations, avoiding unnecessary loss. When it comes to bandwidth estimation, cubic relies on the packet loss as an indicator of the congestion, which is that's a pretty much legacy thing from way back when. And when it comes to BBR, it actively probes for available bandwidth and adjusts sending rate, minimizing latency. Latency-wise, cubic prioritizes throughput over latency, as a result of which sometimes there's increased latency under heavy congestion, while BBR maintains low latency, continuously monitoring network conditions and adjusting congestion control parameters accordingly. And lastly, implementation-wise, cubic is, as I previously said, default congestion avoidance algorithm on pretty much every popular operating system these days, while BBR is developed Google for their use in their data centers. And as I said, it does not really surprise that it came out of one of these hyperscalers that moved towards the white boxes, given the fact that they usually come with the shallow queues. Now, when it comes to enablement, the good news is that it's fairly easy to enable BBR. It needs to be done just on the sending side of the connection, so only on sender. And in this particular case, we are showcasing a few commands that you need to execute to enable it on Linux. First one is getting proc file system, as part of which we are finding out what's the full congestion avoidance algorithm that's configured. In this particular case, we can see that it's cubic. And then we are echoing two commands, one for fair queuing and the other one for the congestion avoidance algorithm to enable BBR. We are applying changes by syscontrol -p command. And lastly, we are verifying that it has actually been configured successfully by getting the proc file system. It's quite easy to do it on Windows as well, as part of which it requires additional step of reboot. So we did exactly the same thing with BBR as we did with Cubic. We first established a baseline and we achieved 868.50 for the symmetric topology and 827.20 megabits per second for the asymmetric topology, which is pretty much in line with what we were getting for the baseline in the topology that was using Cubic. Now, this is where the pretty significant difference happens. So on average, once we started introducing the packet loss using TC or NetM functionality or enhancement from the TC, on average, 1% packet loss caused only 8.5 decrease in throughput, while using BBR, which is a stark difference of to 70.7 decrease that we achieved using Cubic. So it's an order of magnitude difference. So more specifically, on average, we were getting 794.06 megabits per second for in symmetric topology and 763.42 in asymmetric topology, which gives that at 1% packet loss in symmetric network topology using BBR costs 8.5% throughput decrease compared to 70.7 throughput decrease in the same topology while using Cubic. And in asymmetric topology, we saw 7.7% throughput decrease compared to 74.2 decrease in throughput while using Cubic. So it's really an order of magnitude difference when using those two algorithms. And this is probably the most striking plot that I'm going to show today. In fact, if you look at this, what we are indicating here is achieved throughput using BBR and Cubic. BBR is shown with the blue color and BBR with the Cubic with the orange color. And it almost looks like that we are comparing Cubic at the baseline and 1% packet loss, which is not the case. In fact, this is these are two congestion avoidance algorithms applied in the same topology at same level of packet loss, which is pretty remarkable. So we also tested up to 10%, and interesting thing here to note is that even at 10% packet loss, we were getting 750 plus megabits per second, regardless of the topology type that we were testing in, which indicates that even at 10% packet loss, Cubic is so much more effective at dealing with packet loss compared to Cubic at any kind of percentage of loss. When it comes to production testing, there are some really good articles that were published by different vendors out there. So for example, Dropbox actually published a really good document indicating performance of BBR in single POP. They effectively went and enabled in Tokyo, which is their NRT POP. And interestingly enough, they compared performance between BBR version 1 and BBR version 2. Now, at RIPE 76, Jeff Houston from AppNix spoke about some of the problems that were observed from BBR v1, as part of which BBR v1 was crowding out other sessions such as Cubic and Renault enabled sessions, which was playing to the unfairness of the protocol, and it was actually a significant problem. So if you mix BBR with Renault and Cubic, it would lead out to starvation of the other flows, which was a significant problem. When it comes to those results that Dropbox actually published from their production level test, it indicates that bandwidth allocation in BBR v2 was scaled down, which made it much more fair compared to BBR v1. And even though we are speaking about smaller amount of throughput achieved, that's actually a positive thing given the fact that it was more fair to the rest of the flows. There were other problems with the protocol, such as the fact that it did not, in version 1, had the ECN, explicit congestion notification. Google actually went ahead and fixed that by implementing DC ECN with protocols. There are other problems such as problems with performance with the aggregated links and stuff like that, but all of that was pretty much put to bed in version 2 of the protocol. So Dropbox test also compared the performance, production performance with Cubic and Renault, and similarly to what we observe in our research, they are pretty remarkable as well. So overall results indicate production readiness. Spotify went ahead also and they tested protocol on subset of their customers. The good thing here is that it's, as I said previously, it's fairly easy to enable BBR, and you can do it on the operating system level, such as we did in this particular research, or you can do it actually for the sessions. So effectively, that's what exactly Spotify guys did, as part of which they just enabled it on subsection of the already established sessions, and their results also indicate production readiness. Google, well, there's no surprise there. After all, they invented the algorithm itself. Google went ahead and publicly announced that they are using it for all of their flows in GCP. They are using it at YouTube and search. So if it's ready for them, I guess like it's pretty much ready for anyone. Google also publicly spoke about working closely with Netflix on porting the code to FreeBSD. It was even in version 1. By this time, that has been already done. There are multiple different reports that indicate that Netflix is using BBR, but Netflix itself, they never published any kind of article indicating that explicitly. When it comes to networking vendors, Cisco Catalyst SD-WAN, upon the enablement of TCP optimization, actually enables BBR on the both ends of SD-WAN tunnels, which is really interesting because in this particular case, you are getting benefits of BBR bidirectionally, and that's really a proper way to go. So in conclusion, what we saw is that even the smallest amount of packet loss has extremely negative consequences on throughput. We saw that at 1%, regardless of the topology, we saw 70+% decrease in throughput, as I said, regardless of the topology it's configured in. This indicates importance of monitoring and addressing even the minor levels of packet loss, especially given the fact that Cubic, as of right now, is the congestion avoidance algorithm by default enabled on pretty much every single modern operating system. And we know that these are the things that network operators don't usually change. Packet loss outcomes significantly differ based on congestion avoidance algorithm, as proved in this research. We saw that at 1%, we had 70% decrease in throughput using Cubic, and only 8.5 or even 7% decrease using BBR, which is an order of magnitude difference. And BBR showed significantly better results at any packet loss percentage, as part of which the interesting note here is that it was so much better at dealing with loss that at 10%, it outshined a Cubic at 1% packet loss by enormous margin. So the last question is, what's preventing you from deploying BBR either for testing or production environment? Thank you so much.
Yeah, John Linkova, someone who hasn't been paying attention to transport protocols. I am curious. Just true. So I'm curious. So you tested it with packet loss. Have you tried adding jitter? Because I remember that some time ago BBR used to have problem with that. So it would be interesting how both of them behave, and is there any conditions when actually jitter would affect BBR or badly?
I haven't tested it with jitter. Also, I haven't played with latency, which is where it really shines. So spikes in the latency is where BBR really outperforms pretty much everything. The purpose of this test was to test BBR in a very controlled environment to exclude noise. So we actually kept like complete environment, completely vanilla, so to say, just to test like how it's going to perform in this like isolated case. But that's something that we could research for sure.
Yeah, because I was just thinking there are like I would expect two cases of jitter. It's if you have wireless infrastructure, and second, actually your latency might start changing if you have like LSP optimization go in other paths. Your latency will change and so on. So, thank you. I'm looking forward to another presentation.
Thank you so much, Jen. The other thing is that when speaking about jitter, it would be actually quite interesting to see the effects on choppy voice in the voice over IP application using BBR. So it would be quite interesting for potentially any kind of researcher in this room to figure out the best methodology to figure out like what's the direct correlation of jitter and choppiness in voice over IP applications using Cubic and BBR.
Thank you. Alexander.
Alexander Zimov, Yandex. I have one comment and one question. You mentioned that to enable BBR, you at Linux, you have to use two knobs. One knob to change
pair queuing and
disk, and another one to change the congestion control. In modern Linux kernels, you need to change only one knob because pacing was moved from the disk to the TCP stack itself. And so in a modern kernel, you just need to enable BBR, you just need to change the congestion control settings. That's all. And the second question is, have you measured the performance of BBR3? Because 2 is already outdated.
We haven't. We kept it by default on the kernel itself that was deployed with 2204, and that was purposely done. We just wanted to see it like, so there are other kernel enhancements with the newer kernels, obviously BBRB3 being just one part of the story, but also if you think about the other measurements tools such as SS-TNI, for example, to see like sockets and performance of the sockets, you get significant benefits of doing that. We wanted to see what's out of the box performance given default kernel version in Ubuntu 2204.
So just another comment, I would be very glad to see your measurements for BBR3 in both flavors, because it has two flavors for data center environment and for external connectivity. Thank you very much for your report.
Thank you.
Thank you. We'll move over to the queue here.
Daniel Karnberg, old network guy working for the RIPE NCC. Thank you very much for providing measurements. You only know things when you measure them. What I'm curious is about the interactions between multiple flows using different congestion control protocols. Are you aware of any work where you basically have a link that's shared by multiple flows and the link has degradations just like packet loss jitter and stuff like that? Or are you planning to do work like that?
So we can do, for sure we can do that. The Dropbox research that we referenced during this talk actually has exactly that. It was known that BBR version 1 had the problem as part of which it used to crowd out Renault and Cubic flows, and it was really bad, right? It would just like completely shutter those flows. So that was one of the most important improvements of BBR version 2. It's already taken care of. It's when it comes to flows, it still significantly outperforms, as I shown here, Cubic, but at least it's much more fair when it comes to bandwidth allocation. It does not kill them.
Yeah, it would be really nice to have published research on BBR2 and 3, because we can all be selfish, but crowding out the other people is not such a nice behavior.
Perhaps that's a good talk idea for the next RIPE.
By all means, please.
Thank you, Antonio.
Hi, Antonio Prado, a TCP guy passing by. Congrats on your research. I just would like to know if you did consider or maybe use the Mathis formula, which relates the probability of losing a TCP segment during your test.
Thank you for your question. It's a really good one. I think Mathis actually contributed to development of BBR. Other notable people include Van Jacobsen, which is the original out of Renault, as far as I know. I haven't applied the formula on BBR. I know that it has the, so at the start of the talk, we actually spoke about for qubit congestion windows being maintained by the cubic function. I suspect that Matty's formula applies given that mathematical probability. I'm not sure how well it's going to translate to BBR, but that's something to check.
So just have one, it's a comment, not a question, from the from Meet Echo, from Randy Bush, IU Research and Arpicus. BBR competing with BBR and competing with cubic tells a much more nuanced story.
Sure it does. So cubic versus cubic, version 1 to 2, as I said, version 1 was really unfair to the rest of the flows. It was just crowding out Renault and BBR. When comparing BBR versus BBR version 2, we saw that it achieves lower throughput. But in this particular case, and this is one of these rare occasions in our world where less is better. We saw the less achieved throughput, but it's much more fair to cubic and Renault. Awesome to see that Mr. Bush is looking at these meetings.
All right. Thank you, Kamal.
Thank you.
And next up is Ashbjørn with hardware offloaded IP forwarding in the NIC.
Thank you. I will talk about some stuff I've done work with hardware offloading, routing of normal residential internet access in hardware. So we are a smaller ISP in Copenhagen where we do FTTB. So we have normal 10 gig access switches in the basement, and then we have just VLAN tagging going out from there. Yeah, we have 35,000 connected households at this time. And yeah, so if you look at a small model of a simple ISP network, then we have some PNIs, IXPs, and transits, where in this setup we use it as a one-armed router. So we have it going into a layer 2 switch, and then up to a router because, yeah, router ports are expensive. And then we have an internal layer 3 cloud where the end users are connected, and we also have some internal caches. So we used to have some big equipment. Then we replaced it with some other big equipment. And then we just did a soft router. And we could get away with that for some time. And then in 2021, we upgraded the NIC in it. And then we also started doing some static offloading. So this is just a short presentation about one router on a stick, if anyone is unfamiliar. Basically, we have all the different external links going into the router as a VLAN tag. So the router basically just shuffles the packets around, and therefore we can get away with just having one port on the NIC. So we have this feature that NVIDIA developed as part of a solution for OVS and containers and so on, so that when you have virtual ports on a NIC with SIOV, that is then has its own hardware queue, then you can program the NIC to say that this IP address or this MAC address should go straight into this queue for this virtual machine, and thereby bypass going through the hypervisor and go straight to the virtual machine. So this is their main marketing case for this feature set. However, it's also possible to use it with sending the packet back out again of the network port. In the future, it might also be possible to go between the ports if there's a dual port NIC, but at the moment it's not possible, but there are some hints that NVIDIA might make that possible in the future. It's possible in DPI, but each driver can limit it if they want. So this is done using a default Linux API that they've upstreamed. And that's done through Linux TC traffic control, as was also saw in the earlier presentation. So TC contains chains and priorities, and then each rule can also have handles, so you can have multiple versions of the same rule installed in the same priority in a certain chain. The hardware offloading can be installed in 3 different ways. It can be installed opportunistic, which is the default, or it can be skip software or skip hardware. So in the opportunistic case, it tries to install in hardware, and if it cannot, if the hardware says it's not supported, then it'll just do it in software. And then the skip software version is just where it's only installed in hardware, and if it cannot be installed in the hardware, then it will just fail with the insertion command and give you an error of why it couldn't be installed. And then the skip hardware part is where it's only done in software. The opportunistic part is also used for some of the offloads. For instance, if you have some tunnel encapsulation offload, then it might be able to not do it on the first packet, but then it'll fall back to the software and process the rule there. And then it'll make sure that the hardware have the rest of the components that it can do it on a second package. So that's the 3 main points of the different types. It's very vendor agnostic-ish because it's like you have to look at the source code, what is supported in each driver. It is mostly coherent, but there's always a few differences in the implementations, unfortunately. And for instance, some drivers, they only allow you to hardware offload rules in chain 0, and otherwise it'll just give you an error. So just to give more of a graphic overview of how these chains and rules tie together, that you can, in a rule, you can go to another chain and continue processing there. I haven't seen any performance degradation from doing that, but it might differ with other hardware. I've only tested on NVIDIA ConnectX cards. You can also drop a packet, or you can trap it, which means just send it to the CPU, or you can redirect it, which is used for sending it back out of the incoming interface, or sending it out through another queue to a virtual port. So if we are going to use this for forwarding, what do we actually need to do in these rules? So we need to change the VLAN tag so that it goes back out as part of another layer 2 network. We need to change the MAC addresses and decrement the TTL. Fortunately, there are commands for all these things. The update checksum is optional in most of the implementations. It's not optional in the software path, but in the hardware path, in my experience, it's optional most of the time because it's always done either way. And then you can push it back out with the redirect target. So if we look at how these rules look, then you can, this is a simple example of how to add a TC flow rule, where it checks on that it's a VLAN tag packet and changes the things we just talked about with the VLAN tag. It updates the MAC addresses and decrements the TTL. And then updates the checksum because this is an IP4 check. And then it mirrors it out of the egress port of the incoming device. If we then look at how this looks if we show this rule, then we can see that it's on line 6 that it's in hardware, and it has a reference count of 1. If we had bonding and stuff like that, then we could have it been installed multiple places. And we can do that as these 3 actions. And then if we look at the statistics for this, sorry, that's the next one after this. Here we just, this is on the previous one, the actions were compressed into single lines to fit on the slide. Here they are expanded, so you can see what the actual output of the command is with the details of these actions, with how it does the macro placement and so on. This is one with where it shows the statistics output, where you can see that it has access to the hardware counters of how many packets and bytes have this been applied to. And therefore you could also use this for prioritizing which rules are installed or remove some if they're not needed, if you'd rather do some processing in hardware or some in software path. We have been using this for 3 years by now, something like that, where we have done this just purely statically because all of our addresses of our own address space is known. We know that the next destination is layer 3 router, so that has static MAC address. We know that if there's power to the system, that is always going to be true. And therefore, we could do this statically for some time for half the traffic or half the packets. And so we have done this in a shell script where we just set up the rule set in a static manner and then simply match on if it's going towards our own address space, but it's not used for any link nets, then we can just send it directly to the layer 3 router without going through the CPU. So the thing we do here with TTL is that if the TTL is expiring, we do send it to the CPU so the CPU can send back an ICMP packet. So because we could not really do this anymore, or it didn't scale well enough, we wanted to also be able to do it on some of the outbound traffic, where we couldn't just do it statically, but where we needed BTP integration with it. Then we have developed a small daemon that can talk netlink and can take in all of the knowledge from the host system with the interfaces, the neighbors, the routes, and match it all up into a TC rule set. So we have written it where it's like only does that and just talks to netlink and learns it from a separate routing table so that we don't have to offload the full DFC, but that we can just offload the minimal set, or we can do it in stages so we still have some control over how much we are depending on it and what can go wrong at what time. We have, with this, we have used BERT so all of our BTP is running BERT, by the way. So we have set that up to inject a small subset of the routes in so that all of the hot paths can also get hardware offloaded. So if you have a small block diagram of that, we get all the links, neighbors, and routing table information into the daemon, and then it generates the rule set, and it has BTP and BERT feeding into it. If we look at the BERT configuration for this, then we have all the BTP sessions feeding into the main table in BERT. For this example, I've just done for one address family, you can think of it being duplicate, because we also have it for V6, both V6 and V4. But all the BP sessions and their routes go into the main bird table. That also goes to the main kernel table, so the router can do the full table and knows where everything is at. And then we have a pipe protocol in bird that then has a filter of which route should go into the offload table in bird, and then we synchronize the offload table into the kernel with netlink, so that we can then in flow route take the table back out again from the kernel and feed it back into the kernel with TC. In order to get stability, we also actually have two pipe protocols, just so that we can update the filter on one and refresh that one, and before we refresh the other one, so that we don't have flapping routes in the offload table. So I was a little bit puzzled when I first tried to deploy this. I saw that the more rules we put in to the hardware offload, the more the performance dropped. Or more, this graph is just showing the package processing software. So the rules were being processed, but we got higher CPU usage on the software path, because all of the rules that were not processed in the hardware used more CPU. Because that whenever a packet comes into the Linux kernel, it checks this flag for whether or not this rule should be used, or if it should skip the rule because it says skip software. But that flag was on the individual rule and had to do all of the matching in software to figure out that it was this rule that it should look at the flag for. So what I've done in Linux 6.10, which is coming out in July, is that I have made a bypass so that if the amount of rules installed in the kernel is the same as the amount of rules that have the skip software flag, then it can be assumed that any rule will have the skip software flag, and therefore it can be bypassed. And then we could reach 3 million packets per second on this software setup. The reason that the graph still goes down around 70 rules here is because that is the point where the hardware cannot keep up anymore. So if we look on the scalability of how many hardware rules we can install, then if we look at the hardware forward-running performance, then we can do, at this test, I was only able to generate around 37 million packets per second, and therefore the graph tops out at 37 million packets per second. But I could clearly see that the more rules that I installed, and these are installed with a single chain, and then a lot of rules that doesn't match with different priorities, and then a final rule that matches. Then it's clear that it's expensive for the hardware to go on to the next rule that doesn't match. But if instead of doing this with priority, I did it with handles, then it could keep up. And I haven't done the full testing on this, but this graph is just to have the same similarity to the previous slide. It's limited at 100, but I have gone up to around 900,000 before I saw it starting to drop. But I need to do more testing on that to see if there's some cache stuff playing into that. But yeah, so the numbers can go higher. The issue is that on these ConnectX cards, whenever it runs out of memory on the NIC, it does DMA over PCI Express to the host. So therefore, it will report to the kernel that it can do full 32-bit in ranges in both rules and handles and so on, and chains. But in reality, there's a performance cost at some point. But I haven't had enough time to find what the top end of it is, because those tests were running quite slow when I had to set up so many 100,000 rules. So future steps and this code base is to get some better tooling, so it's easier to drop some netlink message, dump the netlink state of a production server, and then simulate how the rule set would be generated if you were to deploy it on that production server. Some other things is also that I haven't done the reverse path filtering on it yet. In our setup, we do that at an earlier stage, and therefore we don't need it right at the edge. And we also have done offload directly to directly connected hosts, but we want that for tested up in our hackerspace. So that will come soon. And then we also need to use TC handles so the rules can scale better. And then we also need ECMP support. NVIDIA had a proposal at NetDev in 2020 to introduce a new Flow API for ECMP called Hash, but there was some pushback on the mailing list for that, and therefore they have dropped that more or less at this point. And we'll see if we can get them to resurrect it. But other than that, we also need some API support for MTU differences, because we have some internet exchange connections that have high MTU, but we need the routing needs to know if it's safe to throw a big packet out to a small VLAN. But at the moment, there's no way in TCFlow to check the size of a packet. So we have a small project of getting that in there. And then we also have stuff like verify that bonding works. From the code that I've written in the kernel, it should just work, but let's see. So the setup that we have planned in our hackerspace is based on one of these thin clients. Ben might be familiar. And it has M.2 E-key, meant for some Wi-Fi or something. But yeah, it can be converted into talk to 8x dual 25 gig NIC. And then it can run, since this thin client uses 3 watt normally and can use 5 watt, and then the 7 watt from the NIC, and then 1 watt for a fan or something, then we can reach something like 25 gig wire speed routing at around 15 watt of power usage. So I think that's nice for running in a hackerspace, or if you have an 5 or 7 connection, something that you need a router for. Yeah, so that's more or less it. Patches are of course welcome. This is one of the first implementation of this API outside of IP Route 2. The next updates on this will be that we'll do a blog post about the setup in our hackerspace when we get that done. Hopefully that will be around the release of Linux 6.10 in mid-July. And then I'll have a talk at BornHack as well with updates about that.
Okay, thank you very much. So, do we have any questions? We do. Excellent. Please don't fall over.
I'll try not to.
Hi, Ben from BGP Tools. I didn't quite catch the initial motivations for doing this. Is it energy efficiency, or I'm curious mostly if you implies my next question. Have you looked into things like VPP and the
Sure.
sort of not quite hardware offloaded, but it gets quite close to hardware offloaded?
Sure. So the reason that we had, so we started doing this statically in 2021 or something like that. And so we have had the idea of doing it this way since then, but also in the right now we use this with ConnectX-6 cards, but with newer versions we can also do 400 gig or 800 gig.
Yep.
So it scales quite well, and it is a bit of an underappreciated feature of these cards because there's more or less no documentation. The only available thing is the OVS documents, which then also have pseudo examples of TC commands that have never worked, like wrong keywords and stuff like that.
Sure. It's probably also worth pointing out that the Mellanox switches, or I guess they're now NVIDIA switches, also have these same functions where
Yes.
you can use the same flower. I'm a user of the exact same TC flower APIs as you are.
Yeah.
Not on the routing side, but on the ACL side, and they're particularly good.
So there's two different main drivers. So there's MLX5, which has these ConnectX-6 cards, and then there's Mellanox switch, which follows some of the same things. There's a little bit different what is supported in Flow API in each of them, but
very similar.
But yeah,
It's really cool. Thank
but
you.
the thing with the hackerspace is definitely power consumption. That we can do it without spending too much on electricity.
That makes sense. Cool. Thank you.
Please.
Hi, Michael from Indonesia. Thank you. It's a quite of interesting presentation. Well, actually, the PC router that we built, like using Bird or maybe like other platform like Viata or something else, is also quite popular now in Indonesia. My question is, how resilience of the router itself? I mean, you mentioned before that you start it from 2021, and I mean, how the uptime of the router, and I mean, how the efficiency of the latency is pretty good, or maybe in some issue with the BGP update sometime. How long it will take if we have the full routing of the BGP table. And I think one more thing.
We have to.
Sorry, it's interesting topics, you know. And how big the potential of the traffic that we can carry based on the kernel limitation. I mean, we don't care about the hardware, and how it will be the potential of this kind of projects. Thank you.
So when I did the testing for the benchmarks here, it was before there was someone that found a lock contention issue in the bypass patch that has been fixed in the kernel since then. But therefore it was a bit slow and that's why I haven't done all the benchmarks yet on how many hundred thousands of rules I can install using handles. I mean, in the man page, there's no information about these kind of things, so it's good to do a presentation about that. But it's also, and I've seen some papers that say that you can install quite a lot of rules quite quickly, but I couldn't really reproduce that. But then there was also someone that found a bug in the code. So it might be fixed now. I haven't done the testing yet.
Okay, thank you very much.
Okay, we have time for really only, I think, one question, which was over here first, sorry. But we'll be around. You can ask more questions. Sorry, please.
Sebastian Schrader, TU Dresden. Have you looked at also the NVIDIA Bluefield NICs? Because they offer something very similar, which they call host-based networking, which they basically, like, they do something similar that Cumulus did. They offload to the same internal ConnectX NIC. But it's proprietary. Your stuff is obviously open source and nicer.
So basically, Bluefield is just an embedded computer that has 8 ARM cores, and then it has the same NIC. So it has a ConnectX-6 DX embedded in Bluefield 2, and Bluefield 3, I think, is a ConnectX-7 TX, but yeah, it is just an embedded computer that you can then run Linux in the Bluefield NIC as well. So then you might be able to manage it from Windows and run Windows in the main host. And I don't know.
Yeah, but have you looked at it? What they are doing? Are they using Flower or are they using?
They support using Flower underneath because it is just straight up the NIC placed next to some ARM cores. So they are using those kind of APIs internally, and it is just Linux running on the ARM, and therefore because Linux supports the Flow API, then they can do it over to the NIC as well.
Okay. Thank you very much.
Yeah.
So now we move into our lightning talks, and remember, there may or may not be time for questions and answers after these. And please, Gailey from MLabs, to tell us cool things about MLabs.
I'm gonna start by lowering the mic because. Okay. Hello. Hi, everyone. My name is Lai Olson. I'm here on behalf of Measurement Lab, where I lead the research and data program. Today, I'm going to be talking about how you can measure your network openly with Measurement Lab. So just the main takeaways I'll just start with. These are if you walk away from this with anything, know that one, MLab is seeking new server-side vantage points for our open global measurement platform. And two, our new options make it easier to do so, to contribute than it has been in the past. But first, I'll just give a bit of background about MLab for those of you who are not familiar. So our mission is to measure the internet, save the data, and make it universally accessible and useful. We were founded in 2008 as a way to think about how to scale internet research on the so-called real internet. We run a platform of servers globally in interconnection or off-net networks and cloud networks worldwide. I'll speak more about this later on. But on these servers, we host what we call measurement services, each of which measure a different aspect of internet performance. Our most well-known and used service is Network Diagnostic Tool, or NDT, which measures a single TCP stream's bulk transport capacity, and this is more, commonly known as a speed test, which I have feelings about. I'm sure we all have feelings about. There are multiple definitions of speed, of course, but this is the way that NDT measures it. And NDT is integrated into Google Search, and so from that we are able to collect a lot of different measurements from different users all around the world. And with all of that data, we collect it, archive it, and publish it for open use in BigQuery. So it's free and open to access. And as of today, we have about 6 billion rows of measurement data and about 4 million new measurements come in per day. I should also mention that we also, for every NDT test, run a trace route from the server back to the client. And in the next year or so, we're going to launch a reverse trace route being run as well. So lots of data. This data is then used by researchers and policymakers. So one example of this is that one of the telecommunications agencies in the US, NTIA, uses or integrates NDT into their indicators of broadband need map. And this is alongside Ookla and Microsoft and other tests to help demonstrate areas that need more investment. There's also efforts by smaller regional community-led organizations that are using MLab's data and tools to create maps of their communities and provide data-driven evidence of where connectivity is insufficient. So there are also a number of academic publications that cite MLab data in their studies and how the internet is improving or not improving over time. Maybe interesting in relation to the first presentation, we ran Cubic for some time until 2020, and then we transitioned to BBR v1. So there's potentially some interesting comparisons to be done there. We have a tool that actually called, I don't have a slide for it, but Measurement Swiss Army Knife that allows you to configure the congestion control algorithm as well as the number of streams. So there's some interesting opportunities there as well. So that was just a crash course in MLab. It actually sort of pains me to not go into a lot of details about some of those things, but I'm going to focus on the evolution of the platform and, as I mentioned, different opportunities for contributing infrastructure. So again, measurements come from all around the world. They are integrations of our open source clients, and they test to our servers. So this map, shows the geographic element of that, where are the servers geographically, but of course, the question is also, where do they sit within the network? Because as we know, that fundamentally changes what we're measuring. So historically, as I've mentioned, we've placed our servers in interconnection points or in off-net networks outside of the user's access network. In 2022, we started measuring in cloud networks, and we did this primarily to provide an updated perspective of the user's experience of the internet and pathway to content. With these new options that I'll be talking about for contributing vantage points, we're now looking to measure in both what we would call off-net or on-net and off-net networks. And again, with the goal to diversify the vantage points that we're providing and the vantage points that are essentially representing the internet within our data. Our original motivation to place servers in interconnection points dating back to 2008 was to measure the degree to which ISPs are peering with one another, and we still remain invested in measuring that component of the network, but are also motivated to provide new vantage points and a more diverse representation of the user's experience, and to be able to compare and contrast pathways. I'm particularly interested and excited about the idea of being able to measure from a single user to different points in the network and maybe be able to identify bottlenecks in that way. So here is an overview of the options that are now available for contributing a vantage point. I'm going to go through each one of these one by one, but essentially there are now options for MLab managing the hardware and the deployments, and then there are host managed options, and within both of these they can be physical, virtual within a cloud network, full scale, or minimal. So the full-scale deployments are our sort of bread and butter historically. So this includes 4 servers and a switch, IPv4 space, IPv6 space, and a 10 gigabit uplink. This is historically, again, managed by MLab, and this is how we sort of built out the initial platform. This is still available. It's been available since 2009, but this is one of the options now instead of the only one. As I mentioned, we're also now offering cloud deployments. So if you wanted to contribute a server within a cloud network, if you are a cloud network, you could donate credits, and allow us to run servers within your network that way. This is also a good option, maybe less for people here, but often we just get contacted by folks who just want some representation in a specific geographic region. And so this is an option. They can just sponsor a cloud network, or sorry, a cloud server in a network that has a presence in that region. So this is a pretty straightforward way, I would say, to contribute to the MLab network and have more presence in a cloud network of choice. And this is, for us also, we're really interested in diversifying the cloud networks that are represented, and being able to have a, again, representational view of the user's perspective of the internet. Now, this I'm particularly excited about. This is a long time in the making. This is a minimal site deployment option. So often we would get interest from networks that wanted to be able to have their network represented in our data set, but we're not able to provide the full deployment. So we've now enabled an option where you can just donate a single server. And so this is a lot less of a lift, and is particularly relevant to networks in more developing environments where it's just, again, going to be more resource intensive to donate that full 4 servers and a switch. So now you can donate a single server, and this can be managed by MLab, or it can be host managed, which I'll talk about next. And so lastly, this is also a development where basically if you are already running an NDT server or any one of the measurement services, you can then continue running that yourself, do whatever it is you're doing with the data as well, but that can be archived, or that can be pushing data to our archive and being published publicly. So this option works well for if you're already running an NDT server and want to contribute that data to the open MLab data set. So again, here's an overview of the options: host managed, MLab managed, and within that you can contribute virtual or physical. They can also be minimal or full site deployments. But the takeaway really here is that these options are just kind of the way forward into being able to diversify our vantage points, and be able to have a more nuanced and representative perspective of what the internet is for the user, which of course involves many different pathways. So our new options enable that. If you're interested, there's a form that you can fill out to express your interest in donating infrastructure and being added to our platform. You can also go on our website, measurementlab.net, and there's a tab that says contribute, and all this information is there in much more detail than 10 minutes allows today. And there's my email if you'd like to reach out. Thank you.
Thank you, Lei. We have no time for questions right now, but next up is Christian, who's going to tell us about Community IX.
The clicker. Yeah, so this talk is about Community IX, and I try to explain you how it can simplify sponsoring and how it speeds up communities. I'm Chris. I'm working for System.de, and today I'm here for my non-profit organization, Individual Network Berlin, where I volunteer for since 24 years now. And now I would, thank you. And yeah, Community IX is a connectivity platform for non-profit organizations. It provides free IP transit and is powered by In Berlin, which is a non-profit organization by itself. And we started it in 2016 on the RIPE 72 meeting. We, that is Theo Voss from Inter.link, and me when I was working for Strato. We both have sponsored some non-commercial organizations since some time now, and it's always a lot of work to connect a new peer. As you know, you need some things, and we tried to simplify that for sponsors. We currently have about 100 to 100 gigabits of traffic. You can see the peers later. And we also talked to some commercial IXPs, and some of them are also connected to our platform. So we can connect our connected communities to the peering LAN of those IXPs. What makes it special? Well, it's a layer 2 platform like every other single IXP, but it's for IP transit and for non-profits only. And we try to reduce the effort for both communities and sponsors to connect. Because when a sponsor tries to do things for non-commercial communities, we need a cross-connect, we need a router port. Router ports are expensive, they need transfer network, they need to set up BGP sessions, they need documentation and so on. And with Community IX, from the point of view of the sponsor and the community, everything is available behind a single port. They just connect to the layer 2 platform and can connect to all those connected parties. And yeah, they need just one cross-connect, one documentation, and only BGP sessions to the route servers if desired. Some sponsors don't want to peer with everyone, but then they can just set up BGP sessions to the peers they would like to sponsor. But there are some exceptions, because everybody is sending full tables, and there are many paths with the same length, because they are all good connected carriers. And you know how big full tables are, and some sponsors are in multiple locations, so we have roughly 15 million IPv4 paths and 3 million IPv6 paths. And if we send those paths to every peer, some of the routers might crash because of too many paths. We are using bird route servers, but they currently cannot limit the number of paths to peers. But there's an IETF working group draft that may solve this issue, because when it becomes an RC and is maybe implemented in bird, it can reduce the number of paths that are being sent. For example, 4 or 8 paths may be enough. But if we don't use BGP add path, if you don't send multiple paths, we just overload single ports to sponsors. So this is how it currently looks like. There are 2 organizations. We have community AX in Germany in 6 locations. And in Switzerland, there's another organization. It's communityrec.ch who copied our idea and do it in Switzerland in currently 3 locations. There's currently no interconnect between the countries. So we have one layer 2 in Germany and one layer 2 in Switzerland. Yeah, it could look a bit better, but that's how it currently looks like. In Berlin, it's colorful and diverse. Some people connect with single mode, with multi-mode, with direct attached copper, with BiDi, whatever they like. These are our connected communities in Germany. You see a lot of similar logos. That's Freifunk organizations and also some others like Chaos Computer Club, Amateur Radio Network in Berlin, Digital Courage, and so on. And also Measurement.network, who are also presenting here at RIPE. And then we have a list of our awesome sponsors at Community AX in Germany. You can see there are several IP transit sponsors, several connected IXPs, and also some sponsors for transport, rack space, hardware, and so on. I did not use logos here because of company logo policies. I do not want to violate them. So what are our policies in Germany to connect? We are currently just connecting nonprofit initiatives and community-driven projects. We are not connecting individuals. In Switzerland, they are also connecting individuals, but that's their local policies. Everybody can do their own policies. And yeah, you just need an ASN, some IP networks, and the ability to connect physically. We don't peer via tunnels. Yeah, what do you need to build a community AX? Yeah, first of all, someone who is willing to do the work. You need some resources. You need the projects. If you don't have any projects, you don't need a community AX because, yeah, for whom you are building that. Then you need IP transit sponsors or data center location, hardware, cross connects, and so on, BGP route servers to make it easier. And you could use IXP Manager. I suggest you to do, but it's not mandatory, but it helps a lot. And yeah, we did it in Germany, but we don't know the situation in other countries. Maybe it's good to build something similar in your country because you know who the nonprofits are in your country, where the data centers are, where they are connected, and who the sponsors are. And maybe it's an idea to take this initiative to start a community AX in your country for your communities and support the local internet community in your country. So we build it for Germany, and maybe you build it in your country. That's it. Thank you.
Thank you, Christian. We have 2 minutes for questions. The first one is online from Nico Braut-Santoni. He says, great work. Did you look at the Dragon route aggregation algorithm, routeaggregation.net, to avoid sending downstream users massive routing tables?
I didn't get this, sorry.
Did you look at the Dragon route aggregation algorithm, which is on route-aggregation.net, to avoid sending downstream users massive routing tables?
No, we didn't look at it yet.
Okay. All right, so no more questions. Thank you, Christian.
Okay. Thank you.
And next up, we have an online presenter, Vladimir Vasilev. Can you hear us, Vladimir?
Hello, can you hear me?
Yep.
Yeah, so I'll be quick. I'll just try to see if it's easy to manipulate this. Yeah. Okay, so I'm presenting mostly the work that is ongoing in ITF in the benchmark working group. aiming at standardizing a young netconf interface for a network tester. It's mostly layer 2 and 3 network tester, and we have specified young models for configuring the transactions, and this tester is useful for running tests and validation routines and standardized benchmarks like RFC 2544. So there is a link in the presentation. You can find the draft with the contact information, and if you're interested in the topic, you're very welcome to participate in this work. So I'll go to the next slide. This is what network testers look like today, and they're not compatible. You cannot take one of these testers and replace with another one and reuse your script. That's a problem. So I have a quiz question to get some attention, like which two of the 5 network testers below have standard-based management interface and protocols? And yeah, it is, well, the A, B, and E have quite a lot of work behind and good support. They're not based on standard, like the models, the interfaces, they're all documented proprietary by the companies that stay behind them. C is like using Skippy, which is a serial configuration algorithm, very similar to what was standardized back in the 80s. Like it's still very good and it's still used. And this D picture, this has like acrylic box and 1 gigabit SFP interfaces. This is like open source and open hardware switch that implements the draft that we're trying to standardize. So this is using only Young and netconf according to that draft. So network tests are simple. The testers are simple in their like intent. It's like something that you should be able to send packets in a defined way that you can control and timestamp, and you should be able to receive and figure out if packets were lost and delayed. Pretty much that's it. Like a more complicated case is when you have asymmetric network, then you have to have 2 testers on both sides, like you see in this picture. And so network test management solutions that these other tests in the picture had was like the command line Skippy over TCP or GPIB. Cisco T-Rex, this is something new. It's mostly for software testers that generate more or less not very deterministic traffic, but it is open source. Keysight just open sourced a lot of their like models and software, and they did that in 2023. And you have Spirent and Cisco, which have a high-level test application programming interface, which is pretty much calling functions, doing complicated things. And there are other interfaces like Xena, which was on the picture as well. Now bought by Teledyne. So now we're introducing something which I think is a good solution, at least for a subset of the problems. It's using Young and netconf to control your network tester the same way you can control your router, switch, or any other equipment. And it saves a lot of time. And if you start using it, you will never go back to anything else. That's what I say, at least. So this is like a set of wish list requirements that I just had in my mind before starting with that work. Like, what should a test and measurement instrument have as an instrumentation and automation interface? It should have a interchangeable interface. That's very important. That would allow us to buy either of these test generators and run the same test and see if you get the same result, because test generators get complex And sometimes you can spend months trying to figure out the problem in your application, in your implementation, and it turns out the test generator has a strange behavior. So this was done for the network, for general instrumentation, measurement instruments, standard called Ivy, back in the 70s, 80s maybe. And it was based on devices that have GPIB interfaces, and they made classes, and a company called WebView made tons of money because they could guarantee that you can buy different signal generators, oscilloscopes, and they will be replaceable, interchangeable. And the same thing can be done in young netconf. If you have a young netconf interface, you have the thing called SDN that allows you to buy different switches from different vendors and replace them and just have the same software running. In most cases, we probably have some issues, but the idea is good. That's where we're going. So the second is be scalable instead of complex. And I'll just go faster because we don't have that much time. Have a transactional management model with hierarchical tree-like configuration. Most of the generators and analyzers actually do that already. They just don't use young in netconf. Model that does not put constraints on the precision of the implementation. So if you have to choose if your traffic generator will take packets per second as an argument, or bandwidth, or interframe gaps, if you look into the implementation, the best is to use interframe gaps, because a second doesn't contain integer amount of packets, and there is a clock shifting and things like that. So there are different reasons, but actually, if you make a model, you have to have some experience and know why this implementation is much simpler, and the design is, you have to choose that. So 5, model that does not limit reusability of implementations. Have model with optional features and a mechanism to announce them. This is handled by the Young library, so you can connect to your instrument, figure what it supports automatically. 6, management model has to have a compatible and simple command line manipulation syntax. This is because you don't want people who do the testing to be XML object programmers. They use command line, and Young is good because it can be converted to command line, and someone has already done that. So 7, model has to be deterministic as it can be. So there are some things that come up with netconf and Young, like NMDA, which is not good for instruments. Like if you have something that you do a commit and you expect that it's generating packets, but it in the same time delays that, and after 1 second tells you it's still in the process of configuring it, this is not going to work. It has to be fast and it has to happen immediately. So a bit different than what routers do today. So there are some other requirements, and just skip a bit, but you can read if you're interested. And 12, a commit should take 10 milliseconds. This is not a router with thousands of routes. It is doable. We managed to do it, so others should also manage. And there's some chronology, which I'm not going to go in details. It's interesting read. You can check it out in the presentation. One date that is interesting is in 2022, the ITF benchmarking work group adopted the draft that we presented after several years and some reference implementations. And the draft was supported by the chair at the time, the late Al Morton, and even with some Cisco representatives like Rob Wooten. So it is being checked by people who understand the fabric. And it's a big project with small different domain tasks, which we have taken over and gone pretty far. what you're seeing is like even open source hardware. So you have this Open Source Hardware Association certification that has gone through. We have these IDs, this Norway 0006, this like a GPS synchronization board, which is added inside, so you get synchronization. So you can implement this asymmetric network testing. And you have a lot of links here. So if you are into firmware, you can find how we do the FPGA programming. It is also a useful platform for other open source things. It's like a net FPGA alternative for newer generations of FPGA, which is not a PCI Express card though, but it's a standalone one unit. So you can do a lot of useful things with that. So just to make sure that people are aware of what the RFC 2544 benchmark is, I have published the code for it, and it's only 407 lines of Python. This is how it started. It looks pretty much like what you would pass to the proprietary parent high-level tester API. But it is open source, and it's Python, and it's using netconf to connect. So you see a config.xml file, which is built after ITF model, ITF networks. And you specify the nodes, which allows you to address them. Yeah. So
Vladimir, yeah. Sorry, unfortunately, we're gonna have to stop you there. Unfortunately, we are out of time.
Yeah. So the message was sent through. So if people are interested in network testing, they can take a look at the drafts, participate in the mailing list, and walk into the implementation.
Cool. Thank you very much. And yeah, all the slides and lots more information is on the website. So that is the end of our session. I will just ask you again to consider rating the talks. Also consider volunteering for the program committee if you wish to do such a thing. At 1800 CEST, there is a BOF from the Internet Society and the ISOC Pulse piece in this room, and then at 1900, there is the welcome reception in Hanan B, which is downstairs. So look forward to seeing lots of you at those. Thank you all very much.
Everyone, welcome to this buff. It should start right now. So in this buff, I'll be talking a little bit about how to read the Pulse based on the Internet Society Pulse platform. This is a buff for two reasons. The first one, that's what the program committee recommended. So well, there's not much a chance or choice in that. And the second one is that I thought this would be a good opportunity to start a discussion on providing a high level and easy to digest layer for the data and measurements that we all access, we all see. Some of us collect, some of us are run probes and measurement platforms and so on. But not many of us are exposed to the users of these data at a high level. What I'll be talking about is very quick brief about what Pulse is, the areas of focus, and then I'll focus on the internet resilience, the Internet Resilience Index and what it's composed of, some use cases, and then we'll jump off to a discussion if that is good with you. So Pulse is a platform that was launched by the Internet Society 4 years ago. And the main purpose of it is to curate internet measurements and data from reliable resources and make it easy for people to understand and gain deeper understanding about the internet and its health. We rely on big array of trusted sources for the data, and we hope that, or the goal of this platform is for policymakers, researchers, journalists, basically anyone interested in understanding anything related to the health of the internet to be able to rely on this platform and the data that it provides in their work. Now, a very quick overview of the focus areas. So I categorize them into two main areas. The first one is the internet shutdowns. And the second one is more on the health of the internet. Yeah, that slide shouldn't have been here, but yeah. So we document cases of artificial internet limitations that result in limitation of access to the internet or shutting down of the internet. And in 2023, we recorded 124 shutdown events from 18 countries. The total duration of these interruptions to the access of the internet is 2,370 days of disruptions, not hours, days. We also track the trends in the shutdowns and try to work with other organizations on campaigns to prevent them from happening again. What are shutdowns? So for everyone in this room, shutdown of the internet is just disruption of access to the internet. But what we do is we focus on the artificial disruption, artificial internet limitation, which are disruption to access that are based on a decision that someone made somewhere. Because the other part, misconfiguration, hurricanes, unintentional cable cuts or whatever, is considered anyway natural causes for disruptions of the internet. It's part of how it works. So we focus on the artificial disruptions. Why do governments shut down access to the internet? There are many reasons: civil unrest, conflicts, elections, and exams. Not many people understand or know that in some areas, some regions, some countries, they do shut down access to the internet because of exams. If you have any of your measurement platform, I invite you to monitor the status of the internet in Iraq tomorrow between 6 a.m. and 8 a.m. local time and see what happens. Because tomorrow, a new series of exams will take place, and we understood that the government is preparing to shut down access to the internet then. So that's 2 hours, 6 a.m. to 8 a.m. local time. You cannot say good morning to your beloved ones online, or you cannot, order a taxi over WhatsApp or over any application. You cannot do any banking transactions. You cannot do anything online, basically. Now, to make the data more relevant to the decision makers, we looked at the economic impact of these shutdowns, of all these artificial internet limitations incidents. And we developed the net loss calculator, which anyone can use. All you need to do is select a country, start date, end date of the shutdown, whether is it total internet shutdown or specific service blocking, and it will give you an estimate of what would that shutdown cost per day. So again, this is because of the mission of the platform in providing high-level, easy to digest, relevant information. The second aspect of the data that are provided on the platform relates to the health of the internet. We track the health and resilience of the internet in multiple areas. So people in this room would, if we start talking about the resilience of the internet, would start talking about the hardware, the links, right, and the software that runs the internet. So it's basically routers and cables. But for us, we try to also, again, make it relevant, and we started looking at different aspects that also affect the resilience of the internet. So far, we have areas that track the implementation of enabling technologies for a secure internet. We have tools or data about the concentration of services provided on the internet. And we have the Internet Resilience Index. They are all compiled with some spices added from other measurements to produce the country reports. What we are working on right now is Internet Exchange Point dashboard, the 50/50 tracker, or the keep it local, keeping traffic local tracker, and ability to navigate through historical data, as well as a new and improved API. So the enabling technology is very simple. Anyone just goes there, they will be directly faced with some numbers that represent key technologies, in our opinion, that needs to be implemented and adopted for a healthier internet. Pretty simple, pretty straightforward. Then we move to the concentration and market concentration, country market shares within the jurisdiction, market history, and so on. And then from there, we expanded And we took into consideration 30 different sets of data that are available publicly to produce the Internet Resilience Index. And this is the key thing that I want to talk to you about today. The Internet Resilience Index combines data about different pillars, 4 pillars, in producing single numbers that give an indication about the health of the internet in a specific country or region or economy within these pillars. The first pillar is the infrastructure, which looks at the existence and availability of access. As simple as that. The second one is the performance, the ability of network to provide users with reliable access to the internet. Security, the ability of the network to resist intentional or unintentional disruptions through the adoption of best practices related to security. And the last one is the market readiness, which is the ability to provide the ability of the market to self-regulate and produce affordable prices or make internet available at an affordable prices through maintaining diverse and competitive market. Now, what data that goes into producing these numbers or data for these pillars? For the infrastructure, we look at the cable infrastructure. One of these is the 10-kilometer fiber reach or fiber reach within 10 kilometers as related to the population. We look at mobile connectivity, network coverage, and spectrum allocation. We looked at the enabling infrastructure, IXPs and data center, and so on to produce all these contribute to the pillar that's related to measurements of infrastructure. This is what it does look like for a country like Poland. As you can see, it's high level. Yeah, for example, Poland scores 66% in relation to the infrastructure. This is very easy to compare or to use to compare between countries, and very easy for you to convince the people that you work with that we need to invest more in infrastructure in this country. And if you dig deeper into the different areas that reduced this pillar, you can easily see that, well, there is much need to focus on enabling infrastructure for Poland, not enough data centers, number of IXPs is, we're not sure if it's enough. And well, these areas would definitely help the infrastructure index for Poland. The second pillar is the performance. We look at fixed networks, mobile networks, the latency, upload, download speeds, and jitter for each of these types of networks. Again, this is what it does look like for Poland. This is again how it fits within the mission of the platform, of the Pulse platform, that it's easy to digest, easy to understand, and reliable, as we hope, because it uses comparative data across the board. The third pillar is the security. We look at the secure web traffic. We look at the IPv6 adoption towards reducing the enabling technologies part. We look at DNSSEC adoption, DNSSEC validation to produce the area related to DNSSEC. And we look at manners score. Some of you may be familiar with that. Plus the upstream redundancy for the routing hygiene, DDoS protection, Global Cybersecurity Index, and secure internet servers according to the World Bank towards the security threat measurement. And this produces something like this for Poland. So you can easily see that, well, there's an issue. There's no issue with DNSSEC adoption, but there is an issue with DNSSEC validation. There is an issue with IPv6 adoption. Fix these and, well, the school will fix itself very well. The last pillar is the market-led readiness. It looks at the market structure through the affordability, market concentration, AS hegemony, the traffic localization, peering efficiency, domain count, and e-government development, development index. Yes. So basically, it looks at what data is available for people to use locally, and in a way or another, looks at how much of these data is available locally. Again, for Poland, this is what the results look like. You will see, well, there are internet exchanges, but the peering efficiency is low. So this needs to be addressed. Some intervention needs to be done when it comes to traffic localization. At another level of work, we need to work with decision makers that to produce policies that provide better market structure. We have some issues with upstream provider diversity. As you can see, it's very easy to digest, to understand, and to use in as a high-level explainer for different people. So, well, we didn't stop here. We looked at these and thought, well, maybe we need to produce yet another level that combines all the data that we have, all the measurements that we have, the index that we produced, into something that's even easier to look at. And then people can drill down from there. And then, hence comes the country reports. For Poland, this is what it does look like. If you open the pulse, you will see that there are some extra explanations there. I removed those to make it more legible here. So you can see that the internet resiliency score is just one box of this section of the country report. It doesn't end here. There's again this section that focuses on the globally connected infrastructure in relation to Poland, how many networks are there, IPv6 adoption, addresses, and so on, and then the security and trustworthiness of the internet. Plus, towards the end, if we had any blog posts or discussions that are related to this country, it will be displayed down there. So, how can people use that? Decision makers can just go in and see the data that many of us in the room collect and find an easy way to make use of it. They can easily compare situation between different countries, and they can easily see which areas needs more focus or more work in. Journalists can do something similar, perhaps also focus on the internet shutdowns and try to convince decision makers that it is not effective in most cases. People who are in charge of network provisioning and people who are in charge of implementing enabling technologies. This can provide you with a strong case to present when you want to work on implementing specific technologies, or you want to work towards provisioning of various network components or various connectivity technologies in different areas within your network and beyond. Now, there's an API available right now, and a new and improved API will be available to access very soon. If you are interested, you can send us at this email address expressing that you are interested in the API, and you can have access to all the measurements and underlying numbers under the index and the country reports. You can produce your own reports based on that. You can validate other measurements that you have, and you can find mistakes that we did not see. We would appreciate, of course, if you told us about anything that you would find. Now, that was mainly the presentation part. Now, as this is above, I want to see if there's any interest in discussing that. But before, I want just to go very quickly on some of the challenges that we have faced. And well, if you had any suggestions in this regard, it would be more than welcome. So the frequency of the data update is an issue for us because we combine different data from different sources. They are not all updated within the same frequency. Some of them are updated annually, some of them are updated daily. So there's a challenge for us in finding a sweet spot where we are able to provide, well, updated data in a way that still works with each other. For some countries, we are moving towards global coverage, and for some countries there are some missing data or some lack, basically, in some of the aspects. We did use some academic methods and statistical methods trying to address that, but still, it's not enough. It is still very difficult for us to validate the data. Of course, RIPE Atlas and UNI are doing a great job in that. And well, we have to thank them for that, but still more is needed. As we produce the index, some of the data goes through processing, normalization, weighing that sometimes affect it in a way. But the advantage is that it is reproducible. So at the end, the key feature of the index is that it provides a way to benchmark different countries and see areas where there's need for intervention. So I'll come to this later. So now if I would like to hear from you, if you have any suggestions, any comments on what you have seen, and if you think there is also a need to start looking at how can we provide a better high-level, easy-to-digest layers for the data and measurements that we collect. Okay, yeah.
Does work? Yeah, I have this one question. You were focusing on DNSSEC as the ultimate method of safe domain name resolving. I think there are several alternatives or other measurements. Is that was it just an example, or is this what you think should be done?
So for now, we do focus on DNSSEC because again, the data is available for globally. It's easy to compare, but there are some methods that go through other measurements, so they are available, but indirectly, as with the manners, for example. But if you have any specific suggestions, yeah, please tell me what
there's
other
DNS
things.
over TLS, there's DNS, I don't know, the stuff that browsers are incorporating in their own.
Yes, so the thing about those is that it's not easy to measure, and they are related more to, at the different layer.
Hello, working? Yes, Michelle from Lukix in Luxembourg, one of the smaller countries. And I was wondering how far the size of a country or let's say, the historical appearance of central infrastructures in a certain country maybe has an influence on data or comparability of data between countries?
Yes, definitely. So the data, as I mentioned, goes through a normalization weighing process to make it comparable across countries. But definitely, many countries perform less, for example, on the 10-kilometer fiber metric, because they had some, well, older infrastructure that is still reliable in a way that's still useful. And also, again, because of some countries are massive in size and implementing and doing implementations that would affect such measures positively is just not justifiable economically, for example. While for some countries where it's very small, like if you look at the results for Qatar, for the fiber connectivity, you will see it's very, very high because the country itself is very small. So it's very easy to deploy fiber to almost everywhere, you see. And some countries came late to the game. So the technology that they used is more recent than others. So definitely there's an effect there, but we try to weigh it in a way. And yeah, as we said to many of our friends in some governments, we're insisting that they should be the first in everything, in every metric. Well, your country is huge. There's no way for you to be the first in this specific metric, or your country is very dependent on this technology at the moment. So you need to really invest more to become the first in the world. Yeah.
Caitlin with the Aaron Advisory Council. So I was looking at the map online that you guys have that kind of summarizes by percentage the resiliency of each country. And I was a little bit surprised to see that nobody seems to have cracked even 75%. And I was just curious, do you consider, is there like a goal percentage, or is that good, or I'm just curious.
So because the index is comprised of so many individual metrics, more than 30, no one has any perfect score in any. So it's very, very hard to do that. And also, if you looked around you, there's always room for improvement. So yeah, the result is that we could have did some magic with it for like the highest to be 100% curve or something, but no, we kept it as is to be able to compare it historically over years. Hopefully, within few years, someone will reach the 100% threshold. I don't think this will happen soon. Yes, Robert.
Hi, we have a question remotely. Vyacheslav Adamanov would like to know what could influence more adoption of IPv6 in Poland?
So I'm sure there are many people in this room, not to mention in this conference, that can answer that much better than I do. But yeah, people just need to start using it. Sometimes you think that there's no reason for people not to use it. A few years ago, there were some issues with, compatibility with some services and so on. But well, I think most are solved now. So there's basically you just need a will to do that. Okay. Okay. If no one else wants to talk, or if we need a few minutes to think, I want just to give you a sneak peek about something that's upcoming, the IXP dashboard. We've been working on it for some time. So far, we have data for Africa only. And yeah, we are trying to find a way to support the development of the rest of it in a way. That's how it looks like in a way. It may change. So that's how it looks like so far. It may change at any time. It provides another easy way and comparable way to look at IXPs, different IXPs around the world, basically by members, by country of registration, by type, historical data related to the count of visible AS numbers, and the count of visible IPv4 memberships, capacity, and development of these. So yeah, again, if there are any suggestions that you would like to contribute to this, you are more than welcome to do that. Okay, so my last question would be, since this is above, how do you think we need to work? And this is targeted specifically at people that collect data, collect measurements. How do you think we need to work together in developing such indices or such ways for people to actually to make it easier for people to use the data that we collect? Okay, yeah.
Hi, Lai from Measurement Lab. I mean, the way that we think about it at MLab is thinking of these data sets as complements to one another. So for example, top 10 questions I get asked on a daily basis are what's the difference between NDT and UCLA, for example? And it's a fair question. They're both called speed tests, and that's confusing, but we like to think of them as just two different ways of measuring speed and them being complements as one another. And so I think in terms of working together, having a sort of effort to have unified definitions or unified understandings of what each data set is able to measure and is able to say about a network, the more that we can work on harmonizing those definitions, the better, I think, and also understanding that they can diagnose different perspective or different characteristics of the network. This is something that OECD is interested in as well. They've been talking a lot about harmonizing internet measurements too, but I think in active efforts to harmonize definitions and complementary data sets is what I would say.
Yeah, that's great, to having more harmony and being able to complement each other's work. Okay, so there are no more questions or discussion points. This is some of the actions that you can take right now. You can subscribe to the Pulse newsletter if you wanted to learn more about that. And if you are interested in some of the things under the hood, you can review the Internet Resilience Index methodology. There's a white paper there, and you can always send us to contribute, send us to fix things here and there. And thank you. There is a reception in 25 minutes downstairs if you'd like to enjoy that.